Yes, right here. I'm sorry. Yes, you do have that. What I meant was you don't have, except for this, you don't have the keyboard.
But we'll be able to
Yeah,
see the,
that's
and this is the moving forward.
Yes.
Yeah, that will work.
Because what I did, we had on Monday, we had a meeting, our multi-state meeting, the very first event. And I said, let's do it here to make sure the darn thing works. You know what I'm saying? So I wanted to make sure for you, even on Wednesday, the darn thing works. So it does, it works.
So I think it's better to come here
Yeah.
and you go back to your. Yes.
And then Susan,
Endowed professor and the University of Minnesota Department of.
okay.
So let me get you. We should have access to those.
And then Susan, and then Rob, what's Robbie's last name?
Okay.
Motar?
Motar, yes.
How do you spell it? M-O-H?
M-O.
Go ahead, you're exactly right. I'll find an empty chair at some point. You might want to be probably maybe indoors.
So where do you would like us to sit?
About. Your name is Shaughnessy, correct?
O'Shaughnessy.
O'Shaughnessy?
O'Shaughnessy.
Ah, I think they left off.
Oh, did they?
Anyway, O'Shaughnessy, okay.
Yeah, son of Shaughnessy. Yeah.
Okay, I think what you,
Should
if you
Irish.
scan, if you scan, I'll give you, this is, we have the program here. If you scan it, that will be.
Come on. Here we go. There we go. Okay, got it. I can see it.
So I'm gonna introduce you, I'm gonna give some overview, and then we'll take from there. We have just. Sure, we'll do. Yeah, just. Right. Rabia. I think with this next back.
Oh, okay.
Forward, back. No, yeah, we'll try over. You're the glue. Thank you. Yeah. Howdy. Good morning, everyone, and welcome to the third day of this conference. Can't believe it. We made it the third day. How did your night? Good. Did you have a good night's sleep? All right. Okay, so we're looking for a strong day to finish. Finish strong, as they say. So we'll do that. So it's my pleasure to kick off this day, introduce to you an esteemed panel of experts and different area of water and around it. So we'll have this panel for the next we'll have 1.5 to 2 hours almost. It's about water, AI and water. And my colleague, Dr. Jeff Veitel, he's an associate professor, Oklahoma State University. He brings a great overview, point of view. He's an economist, so an economist who's interested in water. So we have a very balanced panel as such. So Jeff, please come and take it from here.
Thanks, Robbie. Good morning, everybody. Welcome. I want to begin by saying you all have a little bit of an assignment. I teach at Oklahoma State. So your assignment is to listen attentively and come up with some really good questions, because I personally think that the issue of water is important to all of us. I know we're in Texas right now. I mean, maybe it's a bad day to have this because it's raining, right? We probably should have had like during a drought, which we've had in Oklahoma and Texas for the last 2 years. But I think everybody in this room knows how important water is, wherever you're from, especially if you're from the Southwest. So please listen attentively. And then, especially for the AI experts out there, think about how the water specialists, the experts, can use AI, because it's probably new to their field. It really is. And that's why we asked all 4 of the panelists to come up and to give a short presentation, which maybe isn't the norm for a panel, but we think it's appropriate here. And by the way, we asked them 2 related questions. One is, how is their project using AI? And within that, we'll probably get into maybe some difficulties getting it off the ground. And then second is, could they imagine that there's some things that they're going to be able to do that only AI is enabling them to do it? And really, that's why we're here, because we see the power of AI. And so again, we all need to really work together, think together about how we can use it. So again, your assignment is come up with some good questions for the discussion that we'll have, probably 30 or 40 minutes from now. Also, I want to mention, I believe we have on the Zoom at least 2 other experts, Dr. Frank Ward from New Mexico State and Dr. Larry Sanders from Oklahoma State. Both have been working, well, I hate to say this, but in water probably longer than a lot of you young people have been alive. I hate to say that. Sorry, Frank and Larry, but they're experts on it. And of course, New Mexico has incredible problems with water. Larry's been working on them for a long time. So they'll be listening. Hopefully they'll come up with a question or 2, but it's mainly up to you guys to have a really good, lively discussion like we had yesterday during lunch. All right, so I'll stop talking. I'm going to go through, we'll go through all 4 presentations. They're going to be great. I'm going to start out with Dr. David Mula from Minnesota. He'll introduce himself and talk about the work he's doing on his project in Minnesota. David, the floor is yours. Yeah.
Good morning, everybody. How did you find the session yesterday? Was it good? Excellent. Okay. We're going to have another good day today. And I'm David Mulla. I'm a professor and Larson Chair for Soil and Water Resources. I'm at the University of Minnesota in the Department of Soil, Water, and Climate. And I'm also on the executive committee for the newly funded AI Institute called AI Climate. It stands for Artificial Intelligence for Climate Land Interactions, Mitigation, Adaptation, Trade-offs, and Economy. It's a big mouthful, but it's an easy acronym to remember. And today I'm going to be talking about an overview of some AI tools that are being used in our institute, with example applications in agronomy and in water resources. So just to start out, what is machine learning? It's a subset of artificial intelligence. It focuses on development of algorithms and statistical models. And these models can perform, tasks without explicit instructions. They are based on data, ground truth data that is used to train and test the model. And instead of being explicitly programmed to do a particular task, these use the data to learn the patterns and make decisions or predictions. And so you need ground truth data. You need to clean the data, transform it, curate it, prepare it. You have to select the proper variables or features that are going to be used to train the models. So those could be soil moisture, or it could be crop yield or whatever. And then you train the model to minimize your errors. You test it with another data set that wasn't used in training. And then you deploy the model to make predictions, hopefully at unsampled locations where you need that model to work. The very first kind of, AI model that most people were familiar with is artificial neural networks, ANN. And so this basically has an input layer that receives the initial data. It has a hidden layer that performs the computations through weighted connections between neurons. And then each neuron gives you a kind of a nonlinear transformation of the inputs and passes the results to the output layer. The output layer is your final product. So you might be wanting to predict crop yield as your final output, and your inputs might be, things like fertilizer rate or something of that nature. So this was really kind of the first, neural network model structure that was developed. And I should say that one of the big drawbacks of this approach is that it is a black box. There's no interpretability. There's no causality, that you can really discern. You can get spurious results if you put in the wrong variables. So there's a few drawbacks here. The next step kind of in the evolution was deep neural networks, which are a type of artificial neural network that has multiple layers. So you have these, hidden layers, 1, 2, 3, 4, which gives a lot more power as the information flows through the network. And each layer typically applies different nonlinear transformations. And this allows you to really do a better job of identifying patterns and relationships. And so the main difference with DNN and ANN is that the depth of the hidden layers is much greater in DNN than ANN. And you can deal with more complex representations of input-output relationships. There are a couple of different cases of DNNs that I want to mention here. One is convolutional neural networks, or CNN, which is generally applied to images from remote sensing, and recurrent neural networks, RNNs, which are generally used when you have time series data like, stream flow or soil moisture or weather. So let's go and look at recurrent neural networks, which really applies very nicely to some hydrologic problems that I think the panel will be talking about today. So the RNNs are designed to handle, observations that happen over time. You have soil moisture on day 1, day 2, day 3, day 4. You have weather on day 1, day 2, day 3, day 4. These are all, time series. And so the state of the system on day 2 depends on the state of the system on day 1. And so the order is important and the memory is important. So here you have the same basic structure, as the deep neural nets. You have an input layer, you have an output layer, you have a hidden layer, but you have also the time factor. And so the model, for the hidden layers progresses from the previous time step to the current time step to the future time step, and you have an input and an output for each time step. So you have this sequential processing, one element at a time, and that relies on what you had in the first time step. And so that's why it's called recurrent. And the recurrent or hidden state serves as the memory, and that memory is updated as you go through this process. So these are trained using back propagation through time. In other words, you have to parameterize these models based on not only the current state, but also the past state that was evaluated. And so the network learns to adjust weights and parameters to minimize differences between predicted outputs and the ground truth data. Okay, now here's another type of RNN that is very powerful. It's called a long short-term memory, or LSTM RNN. And it's designed to overcome one major limitation of the recurrent neural networks, which is that the recurrent neural networks sometimes forget what was done in the previous time step, or in time steps that were many, days ago. It's called vanishing gradients. And so you can actually have both short-term and long-term memory that affects the current state. And the LSTM introduces a memory cell to carry over information from long ago states in order to do a better job of representing the relationship between inputs and outputs. So again, these are really important in hydrologic time series where you have to predict, the stream flow of a river, or the soil moisture status, which, evolves after you have a rainfall or an irrigation event. So here the structure is a bit different than in the recurrent neural networks. You have a cell state, which is up here at the top, that carries over information from previous times. And you have an input gate, which gives you, the chance to access current information at a given time step. And it selects which information is really important in developing the relationships between inputs and outputs. You have a forget gate, which allows for discarding information that's not really relevant. And so this helps to reduce the computational efforts that the model needs. And then you have an output gate, which controls how much of the cell state is used to produce the output. So the output depends on the memory as well as the inputs. And there's some computational forgetfulness here to make sure that you're not overburdening the computer system. All right, so let me give you an example of an LSTM that I've worked on with my colleagues in computer science. We wanted to develop a model that predicted the types of crops being grown in the Central Valley of California well before the USDA's National Ag Statistics Service results come out a year later. So we basically are looking for real-time methods to identify what crop is being grown in California, in this Central Valley region, which has hundreds of different crops. And, you can use this for many reasons: for predicting crop yield, for estimating fertilizer inputs, for estimating water requirements and irrigation, because those are all crop specific. And so we, downloaded a huge database of information from the Central Valley on different crops and where they were being grown, and used an LSTM model, which has inputs for weather and remote sensing images at different growth stages of the crop. Each crop has a specific growth stage. Tree crops lose their leaves. Perennial crops stay green the whole year. Corn crops are planted in the spring. Tomato crops are planted multiple times of the year. And so each crop has a different phenology and a different reflectance pattern that shows up in the remote sensing images. And so we use Sentinel-2 images at multiple time periods during the growing season, and then developed an attention module which eliminated images which were, obscured by clouds. So, and we also, this attention module allows for different crops to have different weights at different times of the year when their phenology is distinctive, so that you can distinguish corn from almonds, or almonds from pistachios, or tomatoes from strawberries. All of these things are built into this model in a very elegant way. So the bottom line is that a model like this works very well. we have F scores that are always like above 70%. And a lot of these crops here are considered very minor crops by USDA, and the algorithms that USDA uses to identify crops in their cropland data layer is really, really good for major crops that have a lot of support. I mean, a lot of ground truth data. But for crops that have, low acreages like alfalfa here, in this particular Central Valley, we had only 1.5 million pixels of data, whereas for something like rice, we had over 6 million pixels that were used to train the model. So the support really is an important feature of training models. The more data you have, the better you can train your models. But anyway, overall, you can see we have an accuracy of about 84%, which is a big breakthrough because this can be done in real time. All right, so now moving on to a different kind of recursive neural network. It's called gated recurrent units. This is very similar to the LSTM in some ways, but what it does differently is it combines the forget and the input gates into a single update gate and merges the cell and the hidden states to a reset gate. So it is designed to improve the computational efficiency when you're dealing with big data sets. That's the basic difference between GRUs and LSTMs. It's easier to train, it's easier and faster to compute. You still have kind of the same structure. You have the memory, you have the inputs, but the way in which the forget and the hidden state interact and the way in which the input and the hidden layers interact is different than in LSTMs. And so basically, the reset gate determines how much of the previous hidden state should be ignored. And then there's a candidate activation network that updates the hidden state based on the current input and the hidden state. So this is a pretty sophisticated model. It works if you have a lot of support to train your model. And it makes, the computational efficiency higher. Now let's get to something that is, I think, really relevant to the hydrologic types of research that will be discussed later today. That's physics-guided machine learning. So again, this is a different sort of permutation of the machine learning techniques. PGML integrates physics-guided information like conservation of mass directly into the neural network. And in the traditional, machine learning approaches, you train models based solely on data without constraining them. So you can get what's known as hallucinations, which is a term that computer scientists use to indicate that, the model is not operating properly. It's giving you figments of your imagination. It's doing things that don't make sense realistically. And so PGML is an attempt to constrain the model to reality and to give it better interpretability. An example here is if you're trying to predict stream flow from weather inputs and soil, water, or snowpack, you can put this mass balance here where precipitation minus evapotranspiration minus stream flow equals your change in soil water storage. That's the mass balance. Inputs minus outputs equals storage. And so you go through your recurrent neural networks, and these take into account time series variations in weather, water, snowpack, and you model the fluxes, and then you look at an output and you compare it with a process-based model operating on the same data that gives you the actual mass balance. So you're running a physical model in parallel with the neural network model, using the physical model to check the accuracy of the output from the neural network, and then adjusting the parameters if mass balances are not being met. So this is a very big improvement. And so here's the kind of architecture that is being compared here. You have your recurrent neural network for streamflow that's based only on weather inputs and no constraints. You have your a kind of quasi-physical model where you take some states that you know are constrained by mass balance, such as soil water, and you input them into the recurrent neural network, and you get an updated measurement of your stream flow. So that's a quasi PGML model, but the full PGML model is this version that I described in the last slide. So we have these different stages that can be evaluated. And here's an example from this paper that was published a few years ago, showing that if you incorporate physics-guided machine learning into streamflow predictions, you can do a much better job of predicting the outputs than if you just use a typical recurrent neural network model with no constraints. You can see that the Nash-Sutcliffe equation on the tested data set is about 0.57, which is adequate. It's an acceptable model. But if you add in a physical property that has some constraints like soil water, and you use that in addition to train the model, you increase your Nash-Sutcliffe equation accuracy. And then if you do the full PGML with the mass balance constraint, you get up to 0.76. And so the accuracy improves the more physics goes into the model. The last part of this is a bit technical. I might skip over this if we don't have too much time. But another big area of advance is what we call UNet encoders and decoders, which are really helpful when you're trying to deal with large remote sensing data sets. And basically the encoder processes input data into a fixed size internal representation called a context vector, or a latent representation that has lower dimension, but still contains all the essential information that's needed for decision making. And the way it does this is by downsampling the original imagery using convolutional neural networks, which I didn't talk about in detail. That reduces the spatial dimensions of the imagery while increasing the number of channels or wavelengths that are being described. And then there's a contracting path as you go down this process where the spatial dimensions decrease while the number of channels increases, allowing you to capture more and more context about what's in the image that's relevant to the problem you're trying to solve. And then at the end, you extract the primary features. These might be wavelengths that are highly correlated with, for instance, soil moisture, or highly correlated with crop yield. And you basically take that part of the remote sensing image out, and then you pass it to an encoder, which is the next step, that builds back the full remote sensing image that you need in order to do the modeling. So the decoder takes information from the encoder and then upscales it back to the original spatial dimensions of the remote sensing image. So it increases the spatial dimensions while reducing the number of channels. It's just the opposite process. It fuses features from the maps in different, spatial contexts in order to get to the final product. And then it gives you an output, which is an image with the same spatial dimensions, but it helps you to really predict, the output that you're interested in developing rather than a lot of other extraneous information. So for instance, we've used this encoder decoder strategy in Morocco. We did a big project in Morocco where we planted 8 million olive trees on 75,000 hectares of land. And 10 years later, we came back and we said, okay, how many of those trees survived? Because we wanted to know how much carbon had been sequestered. And the government, doesn't track the trees that died or that were eaten by animals or whatever happened. So we used, Planet Lab data to collect images for the area that we had planted olives. We knew how many we had planted. We knew the acreages. And we used this UNet architecture with the encoders and the decoders to extract the information from the remote sensing images that were really needed to separate olives from other types of land uses, whether it's legumes or whether it's pine trees or because really there's no map in Morocco of olive trees by themselves. So we had to create this map. So here's the map that we created. We published this a few years ago. Actually, I guess that's not a few years ago. That's this year. It seems, yeah. Anyway, you can see that, we were able to estimate the acreages that were actually still in existence, and we compared those with the acreages we had planted, and these are very close. So not a lot of trees died, which is a good thing. And we estimate that we sequestered 230 million metric tons of carbon with this project. And then if anybody knows what that means, that is a gigantic amount of carbon. The last thing I want to talk about is something really new. It's called spatially varying physics guided network. So it's an adaptation of the PGML model I talked about earlier. And it incorporates not only the physical laws, but also the spatial variations in how the parameters of those laws differ from one place to another. And so this is really advantageous for people who are interested in process-based modeling. So you can start with, imagery, encoders, and you can extract information. If you know the governing laws, like Richard's equation for soil moisture movement in the soil, you can put Richard's equation into this, update module, and it'll estimate the parameters of the Richard's equations and then give you a prediction. And then that'll go to the decoder. And then on the other side, we have a convolutional neural network that tries to estimate the residuals from the process-based model. So you have your ground truth data, you have your model predictions, and then you have a difference between ground truth data and model predictions. That's your residuals. And we use the convolutional part of this to estimate the residuals and do a decoder process on that as well. And then we add the residuals back to the output from the physical model, and that gives us our spatial and temporal variability in soil moisture, for example. So this is very, very powerful kind of information that I think a lot of people are probably unaware of. I certainly was unaware of this before I became involved in the AI Climate Institute. A lot of tools are available. This slide summarizes what I've talked about. It shows the strengths and the weaknesses of all the different tools. And so I think this will be very helpful going forward as people are trying to, make advances in machine learning and apply those to agriculture and hydrological research, where we need to solve problems that are very complex and very difficult to address. And if you're interested, there's, a nice review of some of these hydrologic models and how they're handled in this LSTM framework. Thank you very much for listening, and hope to talk to you all later. Thank you.
Well, thanks, David. That was really great. A lot of fodder for questions later on, I'm sure. And let's go on now with the next presentation. Susan O'Shaughnessy from USDA ARS from Texas, right?
Right.
There we go. Okay, great. There you go. The Panhandle, where you know the importance of water.
That I do. Good morning, everyone. First of all, I'd like to thank Ali and Jeff for the opportunity to talk to you about different projects that I'm involved with in terms of integrating AI into irrigation scheduling methods. And so with the co-authors that I have listed here, I'm lending my expertise in irrigation scheduling to them, and they're lending their expertise in AI modeling to me. So just a little bit of background information. Bushland is located about 12 miles west of Amarillo. So I live and work there. It's a semi-arid region. It's a region that suffers greatly from high ET demand because of the high winds, high temperatures, unpredictable rainfall, and unpredictable drought periods as of late. So producers have some hurdles in managing irrigation scheduling and managing crop water productivity. But irrigated agriculture is very important to this region because we're supporting the beef and dairy industries. And without irrigated agriculture, a lot of producers would lose their farms. We have been using irrigation scheduling methods, precision irrigation management methods, whereby we couple sensors with variable rate irrigation systems. And I'll show you a slide on that in a moment, with the purpose of improving crop water productivity. We have shown that this works. It helps to sustain yields and save some water. However, we know that with the system is not enough. We have low adaptability. A lot of that has to do with the cost of the sensors. The fact that it takes a lot of labor to install the sensors, maintain, excuse me, the sensors themselves, maintain the data and interpret the data. So before I give a brief description of the 4 projects that are integrating AI, I just want to define integrated crop water productivity. So it's the ratio of economic yield to the irrigation amount applied during the season. And so with conventional precision irrigation management that we've been using, if you will, we've been focusing on reducing the irrigation amount applied by applying scientific irrigation principles. And that is applying the right amount of water at the right time in the right location. And also looking at applying water at critical growth stages of the crop as a way of saving some water. Reducing false positive irrigation scheduling triggers, that's important when you're using sensor feedback, and also reducing over irrigation. So we believe that AI can help us out in this manner. So the first project, we're augmenting our own system, irrigation scheduling SCADA system that we've developed at Bushland. And with this image here, it might be a little bit difficult to see, but we mount wireless canopy temperature sensors on the center pivot itself. So we use it as a moving platform. So canopy temperature measurements are taken of the field as the center pivot moves across the field. We're also time stamping and geospatially stamping this canopy temperature data and using soil water sensors to prevent over and under irrigation. However, we know and we've developed some artificial neural network models to predict canopy temperature, and that's with the help of Dr. Manuel Andrade. using the inputs of micrometeorological data and historical canopy temperature data within specific fields, irrigation levels, because we use our systems to apply irrigation at different levels. We have also incorporated spatial water received within the last 5 days. That's helped with the model. And to address crop development, we incorporate days after planting, so that the output from the artificial neural networks has been spatial prediction with spatial canopy temperature data. And with that, we're able to derive crop water stress indices in specific locations. And then that is helping us to build the prescription maps when we're missing the data from the wireless sensing system, but also when the moving irrigation system does not have time to move around the entire field in a timely manner. We can also provide a prescription watering map based on, again, the predicted spatial canopy temperature data that's used to derive the crop water stress index. In the second project I'm involved with, it has to do with working with scientists from South Korea. They're just starting to get into AI. They have a national mandate to do smart irrigation farming. And they are developing machine learning algorithms to predict canopy temperature. And so on the graph on the right-hand side, you see they're looking at ways to predict canopy temperature based on specific weather parameters. And they've found that air temperature, solar radiation, and relative humidity best predict canopy temperature in their region in South Korea. If we were doing this in bushland, we'd have to incorporate wind speed, as you could imagine. What they plan to do long-term is to use modeling, AI modeling, to predict when orchards, specifically peaches and apples, when the trees become mildly stressed, and so that they can signal to the producer when to irrigate. They've already used artificial neural networks, as have many other scientists, to estimate ET. So with this, they have the irrigation scheduling method that they could propose to their producers. So the benefits in AI long-term would be to possibly reduce the amount of sensors. In the image here, this is of a small plot cabbage farm, kimchi. And they have a single unit weather station, probably an Atmos 41. And then they have a sensor system here that's measuring canopy temperature, as well as soil water sensors. So if they can reduce the number of sensors, that would reduce the cost to their producers. And if they could simplify the recommendations for irrigation scheduling to their producers, that would also be beneficial. So the third project has come about because of a seed grant that was awarded by NIFA to Dr. Manuel Andrade, University of Nevada at Reno. And that is for him to, with Auburn University, to develop a prediction yield forecasting tool for alfalfa for producers in the Western United States. And I'm participating in terms of lending historical alfalfa data and ongoing alfalfa data. We have a project ongoing at Bushland for using alfalfa under different manure applications. So Dr. Andrade and folks from Auburn University are looking at classical autoregression and different types of neural network models based on information that they're getting not only from us at Bushland, but from other entities in Arizona and California. They're looking for irrigation scheduling, the timing, the amount, the crop variety, the crop growth stage, and the cultivar type. And so the benefits of using AI in this type of application is that they're looking to be able to forecast irrigation levels and timing so that irrigated crop water productivity across the entire season is maximized. So for example, with the first cutting, maybe the model would suggest meeting full ET demand, but with the second cutting, maybe 75% ET demand, and so on and so forth. If this prediction tool is accurate, it's possible that producers could schedule irrigations, could manage alfalfa without using any sensors in the field. And the fourth project, well, it involves a smart dual camera that detects crop water stress. But not only are we using this to detect crop water stress, but to better estimate ET. And the main PI on this project is Dr. Joaquin Casanova. He's with ARS out of Pullman, Washington. And so the device itself consists of a RGB camera and a lepton or thermal camera that's wired to a single board computer. We're using a Raspberry Pi at this time. And so the images are taken one after another every hour. And what Dr. Casanova has done is use computer vision to do object identification of components that are of interest. So that would be the shaded and sunlit vegetation, soil, residue, and snowfall. And so in this central picture here, this is an image of the dual smart camera, and it's located very near one of our large wane lysimeters. And so after the RGB image is segmented and classified, it's registered with the thermal image, and in that way the temperature of the different components can be extracted. And so we can use a multi-source energy balance equation to better estimate ET. So our idea is to take this dual smart camera, modify it, and make it into a smaller module and put it on the center pivot system. And so with computer vision, you get much more detail than you would on the spot infrared thermal sensors that we're using. And again, we could improve precision irrigation management or improve crop water productivity. And with this next slide here, I'm showing an example of the raw RGB image, and that's on the left. And you can see that the dual smart camera itself is putting the shadow within the image, but that allows us to show that the image segmentation is very accurate in terms of separating sunlit soil from shaded soil, and it's also very easily points out the residue. So the graph on the right there is just a qualitative way of assessing quickly whether that thermal image is providing temperatures that make sense. And so in summary, the 4 projects that I'm working on, we're just at the cusp of using AI algorithms. We have not tested them yet. We're going to have to find a way to take the results from the cloud computing and put them into the controlling system that's at the control panel of our VRI system, at least in those terms. And with all the projects, the success is going to be when we do the field experiments. But we do see the benefit of using AI. It's pretty hard for a person who's worked with sensors for all their all their career to kind of give that up a little, but that is the future. and we're willing to delve into it. So thank you for your attention.
Well, thanks, Susan. That was great. I think you can see the difference already in the two different scales at which people are working at. Susan with the farmer, and I think David more with the regional level and more from maybe that regional planning, and Susan at the farm level, getting the efficiency. That's great. Also, being willing to give up some of your, right, previous tools and methods. That's great. Okay, so we're gonna move right along. Robbie Motar, probably know him from Texas A&M. We're kind of running out of time a little bit. So, yeah.
Good morning. Thank you for a great organization for this session and for the whole conference at large. I will talk about a challenge, not necessarily an application. And I'm hoping that next time we meet, there will be some solutions for this challenge. So today we're going to talk about not necessarily the seen or the visible water. We're going to talk about the invisible water, that water that's responsible for 2/3 of the food that we consume on a daily basis. And there are some hypotheses, and because of time constraint, I will have to skip some of those hypotheses that is behind some of the research. So I'll talk about integrated environmental modeling, some of the challenges there. In particular, I'll focus on water and food security and the need for dynamic soil characterization. I understand that many of us in this room are not soil scientists, not soil engineers. So I'll go a little bit, maybe take a step back. Why do we need dynamic soil characterization? Why it is very critical, and why it's a challenge for this community to tackle from a food security standpoint. I'll talk about some of the models and new paradigms to tackle the modeling part, but then the big challenge remains, which I'll close with: how can AI help? I was very happy to hear about the new technique that David's mentioned earlier this morning that incorporates some of the physics, but I think we're far from reaching the solutions that I'll for the challenge I'm talking about. So the challenge in coupling soil processes, including biological, geological, chemical, and physical processes modeling in organized, and I'd like to bold and underline organized soil system. Soil is structured. Soil is a system of organizational hierarchy that we need to recognize. And that's really at the core of water and food security. So we're looking at three different fundamental questions that I'd like us to raise. One is, what is the appropriate soil topology to be used in representing the system? And we'll dig a little bit more on that. Second is, what's the soil water model to be used in this coupling? I'll start maybe from the end, that most of the models that we use today in hydrology and climate modeling do not recognize soil as a structured medium. We use still technologies that are 60, 70 years old, including the soil maps that we are using today, need to be updated. The third fundamental question is what's the thermodynamic conditions of life that we offer by the soil medium of living organisms? We did talk about carbon management. We talked about food security and biological processes, but we have not really dug deeper into how do we represent that structure that house these microorganisms that I'm going to call here pedoclimate. So in here, we'll talk about two different scales, and a lot of my presentation will focus on the pedon or the sub-pedon scale, which is the representative elementary volume. Most of us engineers, modelers, are really fascinated with representative elementary volume. But let me share an observation that the representative elementary volume, the way we know it, even Richard's equation, assumes that that volume that we're using is fixed, which is not the case. Many of us here in Texas know that the volume change and the swelling and shrinking properties need to be represented. And all the way on the right, you see pedological maps with the spatial distribution primary soil. In between, there's a lot happens in the scaling, upscaling, and downscaling. And without proper characterization, we fail to do justice to the soil. So I list here some of the the processes in soil that I'm not going to list. We could read them, including biological, carbon and nitrogen cycling, and plant processes. All of these processes are controlled by green. And for those of you who are not in this space, green water is that water, which is, by the way, the soil physicist has not agreed to quantify that yet, but at least the Wikipedia definition is that water that goes into that stays in the soil after a rain and after all the gravitational water goes in, and the blue water is the one we fight over. Even though the bulk of our soil, the bulk of our water pool is in the green water space, and that is the one responsible for the food supply, the food production, and I think this is way ignored in our space. And I think the focus of this challenge that I'm going to close with is how do we reach that characterization so that we can actually predict and quantify this green water space and manage it so that we can improve our food security. I'm not going to go much detail in this because of time constraint, except that I'd like to mention that there are scales in hydrology looking at the smaller scale with soil hydrostructural properties, and I'll talk a little bit about that, all the way to hydrology, and in between we have the hydropedology domain that is connecting these scales. And all of these processes need a structured representation of the soil so that we can connect these scales, and that is not acceptable. So this is the space we are working with, and it's an integrated modeling looking into the typical cycle of how we operate. Sampling, we've got a lot of sites and samples, and we've got the characterization, which I'll talk a little bit about. And that's a intensive laboratory exercise. And then we do mapping, we do modeling and prediction, and we do an expert system. And I'll highlight some of the challenges that we face in the soil water modeling space. One, parameters of the hydrologic system are mostly empirical. Sorry to tell you that, but yes, they are mostly empirical, and ignore soil water and soil structural interaction. And we need to take that into consideration. The second challenge is that hydrologic models simulate rigid medium, a medium that, again, is represented by the representative elementary volume. And what volume we're talking about if we have a soil shrinking and swelling properties. It does not reflect the dynamic soil medium at the swelling and shrinking phase. Linking the micro and macro scales is not explicit in most of these processes. Accordingly, models do not allow for scaling the processes and transferability of information across media. And that's the hypothesis that I'd like us to leave with. So here is a representation of a soil. And if you're looking at the axis 1 and axis 2, the evolution axes and the structural or structured medium, that plane is what we call the pedologist plane. If I may ask a question, do we have a pedologist in this room? Yeah, we have one pedologist. I remember the days when we had tens of pedologists among us, and those are now a rare entity. And I'm going to come back to this because that's very critical to the AI discussion and the challenge I'm gonna raise. So we don't have too many pedologists. I know one pedologist here at Texas A&M, which Felipe, I haven't seen him here. Anyway, so that pedology plane that represents the information about soil is disconnected from the modeling plane, which is that functionality axis. And one's single representation of that disconnect is what I talked about, is that volumes and the lack of representation of the structure and volume change into these models. So we end up modeling an entity that is not represented in the behavior and characterization of the soil. So what we need is an integration of the pedology plane with the functionality plane, with the modeling plane. And this is what we're talking about, is instead of having a representative elementary volume, we need to look at mass as being the entity in which we have a structural representative mass. And anyway, we need to rederive the whole constitutive equations. And we've done quite a bit of that. And as a result of intensive measurements, we have now 15 parameters that represent accurately the soil water dynamics. It represents the soil water interaction, with the water potential. It also represents the structure. The challenge that I'm raising here is that this is an intensive process of measurements. Are we able to do it nationally? No, because it takes a lot of time. These come from 4 simultaneous and continuous measurement of water potential, shrinkage, and hydraulic conductivity. And of course, the swelling, if you're in the swelling cycle. This is an intensive process. The challenge is, how do we estimate these properties without having to go through an intensive laboratory exercise? And here are the challenges that, so again, the first challenge that AI is needed for is the challenge in time and effort for soil parameterization. Okay, we cannot do it. We've done it at a limited soil, but we need to scale up this at the mapping and soil mapping scale. Optimization technique do not work. And that's why I asked about pedologists before. At the end of the day, when you estimate these based on an estimation error criteria, you end up with parameters that do not match reality. David mentioned that earlier. But it's not only about the physics of the problem. It's also about understanding the properties and the behavior of soil. So certain combination of properties do not match. And that's the danger in using some of the AI techniques. It's beyond the physics. We need to have the expert opinion. We need to have the pedologist's brain embedded in some of these AI tools. And this is some of the challenges. We need a smart AI algorithm that allow us to reject some of these optimization parameters because they don't exist in reality. If you have a soil that is clay soil and coming up with some of these 15 parameters that gets you a property and the behavior of a sandy soil, the algorithm must reject those. So it's beyond the physics, it's understanding the behavior of the soil. So that's, I'm calling for a new generation of AI algorithms that allow us to embed some of these expert systems. Thank you very much, and exciting to listen to all of you.
Thanks, Robbie. Well, I think we can see probably David's presentation where we see already success of AI in helping us out. And now Robbie looking for all you young people out there to give them some help, to take existing algorithms and to go through. And by the way, I know the problem you're facing, and that is trying to connect what you see on the ground when you go to these bigger regional planning models. And when you just lose all that accuracy, it's very frustrating. So I sympathize with you there for sure. Okay, moving on. Joseph, I hope I say your last name correct. Kwanzaa?
Yeah.
Okay, well, that's close enough. Okay. All right. From Tuskegee, correct?
From Tuskegee.
Okay, there you go.
I'm from Peru. I'm a boiler maker. Thank you all, and I'm glad I'm the last coming after these wonderful, smart scientists have spoken. And Susan spoke about farmers and what she's doing with them. And I'm going to focus on small-scale farmers because it's critical that AI and all these technologies also get to small-scale farmers. I have myself here. There are a few projects that I'm going to present that I'm the lead, but I have a few co-PIs. I also have a few graduate students. 2 of my graduate students are here, Lydia and John, to support what we're doing. Basically, a few years ago, I did research looking into impact of climate change on water resources. And we looked into the mid-century as well as end of century. And one thing that we found was that peak flows are going to be flat weighting. And definitely that is going to impact water availability and water use. So that has kind of informed everything that we've been doing in the past several years. There's a project that currently I'm working on, which is linked to Cairo. Cairo is Cooperative Institute for Research to Operations in Hydrology, funded through NOAA and USGS. And I would want to talk about some of those projects that I'm working on. One is this very project, which is improving modeling and forecast product delivery in agricultural land use. And basically what we're doing here is that we're trying to utilize the national water model and extracting simulations from the national water model, validating those models with, say, USGS gauges, as well as other models like SWAT, and then utilizing remote sensing and field sensors and things like that to be able to develop spatial trends in hydrology, or basically soil moisture within agricultural fields. So this is the national water model that basically simulates near future stream flow levels. What we've done is been able to use some level of machine learning to extract output from the national water model. Basically, we've been looking at stream flow and soil moisture. And the first thing we did was assess to see if the national water model is performing well at a number of gauges. So within the whole of the research area is basically the Alabama Coastal Tallapoosa River Basin, which is basically half of the whole state of Alabama. And when we tested the national water model over several hundreds of gauges within the state of Alabama and within the research watershed, they fared fairly well. We then went on to also develop a SWAT model over the same watershed area and tested over 23 watershed gauges, calibrated and validated them, and they were good. So these are the results from some of the work that we've done. We also wanted to be able to see how we can relate real-time in-field measurement compared to what the national water model might be giving us. So last year we set out to install a number of, during the summer, a number of soil sensors. So we installed a number of soil sensors across some of the black belt, which is basically our clientele area, Alabama black belt region. That's where we mostly work, because in most cases, that's where we have all the limited resource and small scale underserved farmers would be. And that is where we have a lot of, So we installed a number of soil sensors in farmers who are willing to collaborate with us. So some of the pictures of we being in the field are installing those, and some of these sensor readings that you could see there. These sensors are connected to the cloud, so we are having real-time readings of, say, soil temperature, hydraulic conductivity, soil moisture, and things like that. We also did some quick remote sensing analysis of all these fields, try to see if we could relate any type of biophysical products, such as soil moisture index, to what the sensors are giving us, and we realized that there was some great correlation. A second project that we're working on, which is also linked to Cairo, but funded by USGS, is to try to really assess the impact of drought on small-scale farmers in underserved communities. So we are developing at a granular scale environmental justice tools that predict actual vulnerability to these communities in terms of effect of drought and flood and things like that. But we are not just stopping there. We're also trying to quantify the economic impact. So we have a graduate student looking at hydroeconomic, doing a hydroeconomic analysis of how drought are impacting these communities. The question then is, what do we do with all the data we are extracting from the national water model, what SWAT is giving us, what these sensors in the field is giving us, as well as the drought indices that we are developing, the economic impact assessment that we are making. How does this help farmers in terms of underserved farmers? And one thing I might want to say is that the farmers we deal with, probably 95% of them do not use irrigation systems. NRCS comes in to help. but farmers are supposed to be able to pay a chunk of the cost of implementing them, and they cannot because you need to implement these irrigation systems before NRCS would support you. So in the past, we've done a project with NRCS where we did use hydrologic modeling to assess things like aquifers and things like that, groundwater flow, availability of water in these communities as a way to help in developing irrigation management plans, and then to encourage these small-scale farmers to enroll in irrigation. And sadly, most of them can't afford. I think NRCS is now paying probably 95% or so to encourage most of them to get in. But what we are trying to do here is that how can we utilize AI to be able to integrate all these data and be able to develop some sort of recommendation that would effectively help these farmers. We are not into deep AI work like what David is doing right now. We are kind of at a point where we are collaborating with our computer science department and other faculty to see how we could do some of these things. Yesterday, we had Dr. Vic Cram from AI Farms in University of Illinois speak about some of the AI farm projects, and I decided to talk about it because we have collaborations with University of Illinois. We have a project called the iCover project, which is basically aimed at introducing smart agriculture in underserved communities within Alabama. The main aim is to reduce the cost and labor burden of cover crop implementation, and also to allow for rapid low-cost carbon measurement. So one approach that we are using is that we are currently enrolling all these farmers to engage in cover crop implementation. So again, for most minority farmers, they don't do cover crops. So we've come in to do that. But as part of it, there's supposed to be the measuring, monitoring, reporting, and verification, which is a USDA requirement for this project. So we are using a number of tools. We are using remote sensing technology. We are using drones as a means of options to assess soil organic carbon. And then we are using actual full sampling and testing the soil carbon before these cover crops get implemented and during when they've come up. Some of the technologies we are using is exactly what Vikram spoke about yesterday. We are using robotics that would go through these farms, and then just before they harvest them, to be able to plant the different cover crop seeds. Or we are also now beginning to engage in the use of drones to plant our cover crops. But bottom line is that we are thinking of how are we able to take AI, optimize it so that all these sensors we have in the field, what we are doing with the national water modeling and what we are doing with remote sensing, we are able to integrate them to help optimize water use and water management for underserved farmers. Thank you.
Great, Joseph, thanks. We have just about 8 minutes or so for questions because we can't run late, that's for sure. But I just want to thank all of our panelists. And I think we did answer our initial question, that is, how is AI being used? I'll quickly summarize it, I think, by David quite well. It's helping their project a lot. We see challenges from Robbie's project, looking to the future and trying to get a lot of assistance. We see Susan's project, I think, kind of pushing along at a good pace. And then Joseph, I think you're like me, for sure, most of us, we're at the beginning stage and we're just really looking outward for help and assistance, but we know AI is going to really help us in the future, correct? So with that, I'll open the mic. Rob.
Yes. I think to cover a few questions, let's be quick on the question, short, and also short on the answer as well.
Yeah, really interesting work, Susan. I thought that's really fascinating. We talk about the size of the data sets when we measure environmental parameters, canopy, and all that. We can measure that at very small time intervals over seasons. How much can we reduce that data? What do you think is sort of the, we could take 96 measurements a day, or we could take one a day. How much can we reduce that without losing the resolution that we need?
James, that's a good question.
Is there another one?
I really don't know the answer to that, James, since the environmental parameters are so variable in our region, and as you experienced in Lubbock. I can say that the artificial neural networks that modeling that we developed to predict canopy temperature spatially, well, what we have going for us is that we're doing that in the same field. So, and that was done, I believe, over cotton, and we have a number of years of cotton, maybe 5 or 6. So can it transfer to a different location where we've used our system? Probably not. But there was somebody I know, I attended their seminar, and they said, if you have enough data, you can predict. And so I don't know.
Any other question for the speakers, for the panelists? Yeah, Mohanty, okay.
This question is for all the panel members. Anybody can take it. So there are 2 schools of thoughts. One is you can do ultra resolution modeling. That is the new area, because water keeps on moving. And so all your water in the surface, stream water, groundwater, soil moisture, all are connected. So when you take in a piecemeal approach of one item, maybe you are missing out some water balance, what is happening in other parts of this water cycle. So this machine learning and all these tools that are developing here, you can do certain things in a certain way, but whether that can really conserve the momentum, mass, and everything, of course, David presented something that shows a certain improvement, but in a more unified way, can we come up with a solution that can really take care of the parameters, take care of the processes, and still can give you the answer for all the compartments of the water? That is my general question. So if anybody can take it.
Yes, the water cycle is very important, and there's obviously differences in the partitioning of water as you go from one region of the country to another. And generally speaking, ET is the parameter that dominates the whole hydrologic cycle. So getting that one right is very important. And getting the soil moisture storage right is also very important. I think those 2 things are areas which really need a lot of focus. Oftentimes we indirectly estimate runoff based on stream flow and things of that nature at a larger scale, and that isn't always a good assumption that they're connected directly, because you have other sources like lateral flow and tile drainage. So I think we're evolving in our understanding of how to represent the hydrology of agricultural systems in AI models. And as I mentioned, the process or physics-guided machine learning can actually incorporate mass balance, which addresses each of the major components in the water balance. And that relies somewhat on our understanding of the physical governing laws. So if, we are not really in a situation where, there's the classical displacement theory happening, you have preferential flow or finger flow or something else happening, then maybe we need to go to these spatially varying physics-guided nets, which don't always need to have the Richards equation as the governing law. The SVP nets can actually figure out what the governing equation is and give you a kind of idea of how to represent that if you have non-classical processes happening. And I think there's a lot of opportunities for people to apply some of these new techniques in creative ways that we haven't thought about before.
I think we'll close by here, if possible, by giving Dr. Amir Ibrahim, he's the AgroLife Research Director, and I'll the same a brief opportunity for us to, as a plant breeder, also as an administrator.
Well, thank you so much, Ali. Amir Ibrahim, I'm the Associate Director for Texas A&M AgroLife Research and Chief Scientific Officer. And it's great to be here and see this great audience. The level of talks is just amazing yesterday and today. I would like to acknowledge Ali Faris, Rabi, Seth, Juan Landibar, Mahendra Bandari, and everybody who did a lot of work ahead of this conference. This is an area that is going to receive a lot of attention here at AgroLife Research. We're going to invest heavily into it, and we believe that the future holds a lot of promises for it. So thank you so much for coming today, and have a safe trip going back home. Thank you.
Thank you, Jeff. Go ahead and please.
I think we're all set. Just one more real quick to the panel.
Thank you, everybody. Sorry to take a little bit of your break, but after the break, there are some concurrent chess sessions that you will be joining. It was nice having you here.
Really appreciate all you guys do. Thank you so much. Thank you. Thank you, guys. Thank you, Susan.
I'm heading to the airport.
Oh, it's not?
Yeah.
Well, same
I have
time.
a flight around 3. Okay.
Thank you, Jeff. Oh, yeah.
As I'm seeing the I'm envisioning a number that is directly associated between being. So is capable of looking at these standards. The Richards equation is fundamentally wrong. It's construct and size. The
Okay. Yeah, before you start, I'll just, give you this copy of the policy, so we'll have to- I'll give you like 5 minutes.
Okay. Okay, sounds good. Thanks.
Sorry, I didn't give you. That's all right. I was beginning to recognize
Let me just,
Yeah, no
these
problem.
are the size so that,
Howdy, everyone. The next session will start at 10 a.m. We're looking for the last 2 presenters to upload their presentations. Can Zahara Kademi as well as Michelle Ashkani come to the front, please?
Can you pick also?
No. Like,
It needs to be like this. Yeah, yeah.
Oh, yeah, gotcha. All right. Howdy. So we'll go ahead and get started with the next session. So this will be the data method. So my name is Joshua Peoples. I'm an assistant professor here at Texas A&M University. And so again, just a reminder that we want to stay on time as best we can. So each presenter has 20 minutes, including Q&A. And so just like I said, do our best to stay on time. And with that, I'll turn it over to our first speaker.
Good morning, everyone. My name is Jinha, and faculty member in School of Civil Engineering at Purdue University. And today, I'm going to talk about the online platform that I've been working on. We named it as a Data to Science Engine, D2SE. And the initial title of this project, we just came up with the title says Data-Driven Open Science Ecosystem for Sustained Innovation. And if you just make an acronym, because we all like to make a short name for it. And if you look at this data-driven open science, it is in a DDoS, and probably that's not the best acronym you want to use, because this is distributed in a denial of service, which has a bad reputation. So I'm happy with this in a name, which is in a data science. That's going to be something that I'm going to talk about. And I want to start my presentation with some of the survey that is done by Ohio State University. And they did this survey, I don't know exactly when, but say a few years ago. And what they want to find out is what is the 10 greatest invention in the past 1,000 years. And based on this survey, they found that, annotation is in at the number 10. There's a gas-powered tractor, airplane, computer, vaccination, radio and television, telephone, automobiles, and electric light. And all these items that you see, these are very important. Of course, this is something that we cannot live with. And number one, the best invention that we had in last 1,000 years, came out to be printing press. And also, this is the oldest invention that we got in last 1,000 years. And thinking about it, why this is so important or such a great invention. Before this in a printing press, let's say you like to generate information or you like to share information with others. The way how it has been done is that you have to write on a paper manually. And this is a very laborious process. It takes a lot of time. That was the reason why in those days, there's a very little number of people who has access to books. And those people who has access to those books, those are the ones who had the power at the times. And after this printing press was developed, and now we have a way to generate this kind of information in a massive manner. And now we can go to the bookstores, can find books, you can buy books very, very easily. And more recently, now this information is digitalized. Now you can download books, from the, going to an Amazon Kindle store. You can buy books, very, very easily. And all those, text information has been already digitized, and this becomes the main ingredient for the success of, large language model like in a ChatGPT. Because now we have massive amount of, the text information is now available. Now we can build this kind of, AI model to do it. And looking back at, and it looks like this invention that happened almost 1,000 years ago in text isn't happening to us in other the media. One of the first examples is in a mass media, in a video content. Let's say, assuming that in about 10, 20 years ago, I like to generate any video content. This is going to be the setup that you're going to see. We're going to have professional studios. You're going to have professional anchors. They're going to have a professional cameraman, the sound engineers and the light engineers and all those kind of stuff. In order to create this kind of video content, you need huge steps or the professional professional to do it. Not only do this, the video content generation is taking a lot of human resources to do it. And in the back end, if you like to stream or distribute this this video content to other side of the audience, you have another huge group of engineers working in the back, where they're going to be doing all those live productions. And this video content is broadcasting over the wireless the channel. Then you're going to receive this video content on your end. So this used to be, this mass media become the power in old days, where you are the only few who can generate this kind of professional video content. And these days, I'll let you guys know this, but this is set up on my desk office there. I have a camera over there. I have a lighting over there. At the bottom, I have a sound mixer so that I can mix up my voice with the other sound. On the right side, I have video switchers that I can switch it between my camera and the computer screens. And I can also stream this over the network. And the beauty of this is that now, this is almost like we had in a printing press. In old days, in order to create video content, you need to have professional teams. But now I can do those kind of production in front of my on my desk. I can generate this kind of video content without having huge large number of crews. And when it comes to that, now you just created a video content. I like to share this video content with others. Probably in old days, I'm not sure. A lot of you guys know that, what is DVD. I don't think of those younger generation, what is in a DVD over there. But once you generate video content, how are you going to share this video content with others? Stored in a DVD, send this in a DVD over the mail, or, in old days, you have a DVD rental place where you can go and, check out the video, right? But these days, we don't need to do that anymore. We have a YouTube where you can upload your video. Even you can do the YouTube live, and you can reach out to the global audience right in front of the desk, by yourself. And this was almost like in old days when you have before the printing press, you need to have a huge number of people working on hand scribing, writing those text information. You don't need that anymore. You can generate a massive amount of video content very easily. Now we have a way to distribute this information to large audience through online platform like this. And if you look at the video streaming market share, Right now, this is in the statistics of 2024, 98% of media players and streaming platform has covered by YouTube. And if you look at the who has the most subscriber in YouTube channel, the guy that you see over here in the T-series, he has 260 million subscribers. So once you upload your video, you can reach out to this larger audience very, very easily. And when it comes to the geospatial data and remote sensing platform, same thing again, same analogy. In old days, in order for to collect the remote sensing data set, requires helicopters, airplanes, satellite. These are the things that you cannot do by yourself. It requires a lot of huge investment to make that happen. Not only the platform, those sensors. This is example of airborne camera. This is going to cost you a couple of $1 million just to purchase it. We're not talking about man hours, operational costs and all those kind of stuff. This requires a lot of huge investment to generate this kind of geospatial data. Now, this is the photo from my group, working in the field collecting the drone data. Now you can go to the Best Buy, Walmart, buy the drone, costs you $1,000. You can generate very high resolution, high quality geospatial data by yourself. Going back to the printing press, used to be in handwriting. Now you can generate massive information by yourself. But the missing piece here is that now we created the beautiful data set. I'm very excited about it. And how can I share with others? Those other people is not either interested, they know how to access this data set. And to me, this is one of the biggest missing piece here, where we're going to complete this complete geospatial data science, the generation and the data sharing, all those kind of stuff. So that was the reason why we developed, we are studying working on this in a project where we like to building an open source online platform where you can manage your data, you can also process your data, you can visualize it, you can collaborate with others, and you can also publish your data to the public so that others can find the data that you created, that you are excited about, and they can do something creative work, based on the data that you generated. So we are using a cloud optimized data format. This is becoming pretty much the standard in geospatial data science community. And in old days, we need to have the geospatial data server to host this in. But now we call this a serverless data service, where data format becomes a server. So all you need to do here is upload this in a file somewhere online, and anybody can actually consume this data. And we also use this data on the server side, and we're using the dynamic tiler, which is a T-tiler that is in the middle. And on the client side, you're using a leaflet JavaScript library to actually visualize this kind of data set on the client without downloading it. We also deal with point cloud data set, which is also becoming a new standard, which is a cloud optimized point cloud format in a Clarke. So we really like this one so that we can visualize point cloud data inside the browser without downloading it, and we can do different colorization, as you can see over here. And we can also show maps, show the data that we loaded, like you're just showing the Google Docs. You don't send the file over the network. You just send the link to the other party so that they can actually open it up and play with it. And we can do exactly the same, which I'm going to demonstrate soon. And not only we are limiting data access to our online platform, like I mentioned earlier, this will become an open source ecosystem. You can access this data set outside of your the platform they're working on. So, for example, we have D2S, which is an online platform they're working on. You can access this data to QGIS. You can access this to the data to the Jupyter notebooks. And we also have Stack, which is a spatial temporal archive catalog where you can publish your data, and others can actually discover your data from there and they use it on other discovery. So what I want to do is that you may say that I'm crazy, I only have 20 minutes and I'm going to do the live demonstration, but I'm going to give it a try because I have 8 minutes. So the example that I was showing earlier, this is an online platform that you're going to see. I'm not going to go through this. There are many projects you can see over here, but I'm going to just look for the project where PPAC, which is the Purdue Agriculture Center. And I click this, and you can see there is a specific flight that is done in August 20th. If you were to look at this in a data set, once you click, you're going to be able to see this data. You can zoom in to this in high resolution over there. I can just turn on this DSM so that you can actually see the actual DSM layer over there. I can use it in a different color. For example, if I just choose different color here, this is going to be updated automatically as well. And you can check other data. Or if I go to, for example, let me go to the flight where we have a point cloud. For example, if I click this in a point cloud over here, then you can actually see this in a point cloud layer available, zoom in, and you can see this. This is, by the way, soybean trial. You can just visualize it, color it by elevation. So you can just see all this information is available. Going back here, if I go back to that, PPAC again, there is a tool where you can compare. I can choose earlier flight, for example. I'm going to choose June 23rd and orthomosaic on the left and July 25th, orthomosaic on the right. And I can just click it and the zoom in, can slide and left and right so they can compare between those two. So, all the data is available. And there are, many other things that I'm not going to be able to show because of the time limitation. But another example that I mentioned here is that this data set also can be streamed to other, the software platform, which is in QGIS. The example that I'm going to show you is that this is the data collected in Costa Rica. And the reason why I'm not showing agriculture application even in agriculture conferences because, to demonstrate that we can actually stream large volume of data. The example that I'm going to show you is in Costa Rica here. I can actually turn on the detailed terrain model that was generated by the UAB, and we are looking at the tens of gigabyte data that just shows up. And I can just turn on this orthomosaic images over here. It just shows up, and to prove that I'm not actually going to have this in a file on this in a machine, if I just double click here, looking at the layer source, actually I'm streaming from this ps2.d2s.org. So I'm actually streaming this data from the server, not actually downloading the file down here over here. And if I just zoom into certain area, that you're going to see that now I can see this in high resolution images streamed right to your software right away. And I also mentioned that this can be integrated into the Jupyter Notebook. And this is an example where you have programmatic code where I have this URL that I showed earlier. You can programmatically decide that how you want to visualize it. And this is in a DSM example that I showed earlier. You can just zoom in and out, and you can just do further analysis on this in the client side. The beauty of this is that now you don't need to worry about where your data is located. You can programmatically access this data, and you can share this data with others, and etc. So going back to my presentation. So this is how I envision this online platform is going to pan out in the next 5 years. And the example that I showed here is in a Purdue example. And I have a colleague here in the Dr. Anjin Chang from Tennessee State University. I forgot to mention that this is in the Purdue instance. We also have the Tennessee State University in an instance over there. If you click this one, and if I choose the Griffin system here, we can also visualize in hyperspectral as well. As you can see, we see that hundreds of bands. We can handle the hyperspectral data, and we can visualize LiDAR data as well. So the point I'm trying to make here is that this is an open source project where you can launch your own instances. You don't need to do any programming using your the computer infrastructure, and we'd like to have multiple instances and up and running. And the center which is going to be stack services that is going to be collect all this metadata, and that this can be integrated with other open source data set like 3DEP, NASA, Sentinel, all those kind of stuff can be integrated, and that we like to go for the federal funding so that we can keep doing this kind of development. And when it comes to video content, where you go for to upload this data, going to the YouTube. And what I want to do in the next 5 years is that, let's say you have a geospatial data set created. We're going to upload the data to, it's going to be data to science. And it's free to use at this moment. If you'd like to create an account, I can work with you. I can create an account. You can start using it right away. We also generated a tutorial. This is, if you scan this in a barcode, that you're going to actually go to this document where you can actually have a step-by-step process on how to deploy. And we also had the providing a workshop in an NAPPM meeting, and this video recording is also available. And I'd like to acknowledge my funding source, USDA Act2PI program, and also Purdue School of Agriculture also provided internal seed money to do this kind of development. With that, I'd like to acknowledge my collaborators. I'm leading this group, but I'd like to mention that Ben, he's a full-time programmer working on this project. Min-Young, she's on a postdoc working on with the Ben, and we also have UI UX team from Scroll Up from Purdue, so that we can make this website a little more usable. So with that, I'm going to end here, and happy to answer any question you might have.
Awesome. Thank you. Any questions from the audience? We have about 2 minutes for questions.
That was a great presentation, Jinha. I appreciate that. So 2 quick questions. Whenever you're streaming raster layers in QGIS like that, can you still manipulate them as if they were local? Like if you're doing raster extractions or something like that, will it work just fine?
Yeah. It's the same as a local file, but you are not actually having your file on your machine. You are streaming it. So beauty of this is that all those the analytic capability from QGIS, you can apply to this data directly.
So if you do the raster extraction with 300 features for a breeding plot or something like that, it'll just take a little bit longer to pull the data down from the cloud as it makes the extraction? Or
so it depends on how you do it, but if you want to do it that way, probably I'm going to do a clip so that you can only clipping those in a small location that you're going to on a local machine. Or if you just don't mind waiting, then you can just doing this processing as it is while we are streaming. And the probably better way of doing it is that Jupyter Notebook instance that I showed earlier, we plan to provide that in the Jupyter Notebook instance on the server side, so that if you have any Python program, the actual code is going to running on a server where the file is located right there. Then you don't need to worry about downloading big volume of data over there, in a nation or something like this. So there is going to be a lot of flexibility that we can build in here, where we can do this and make it very efficient.
Okay. And my second question was for the D2S platform. So the analytic aspect of it, custom analytics, well-known analytics, are those going to be portable and modular on the platform? So
my vision here is that we like to make this system as an open, so that not only you're going to contribute the data, you can also contribute your code as well. So Jupyter Notebook is an example that I mentioned earlier, where you can contribute your code base as well. And I didn't show that example, but that there are certain built-in analytical capabilities where you can do different vegetation indices computation, canopy height measurement, those kind of stuff. Dr. Landivar's group is developing some of the growth analysis tool. Those kind of can be incorporated in this ecosystem as well, potentially. And if you have anything you like to contribute, we can talk about it and we can incorporate it into the platform as well.
Awesome. Thanks.
Since we're at time, we'll switch to the next presenter, but thank you for your presentation. Oh, yeah, sorry about that. Oh gosh, yes, sir. Thank you. Next, we have Zahara, if I'm pronouncing the name correctly. Was it? It is. Zahara Kademi is. No. But his okay, great. Okay, sorry. All right, yeah, go ahead.
Can you hear me well? Okay. My name is Zhanyou Xu. I'm with the USDA. My topic is confidence learning improve the RASNet 18 prediction accuracy. I'm not sure how many of the audience are doing classification with deep learning. And this is a new method that challenged me. I feel frustrated for many times. And eventually found this way. Recently, we did some tests. So start with the challenges. If you do image classification, you always find when, well, by the way, my background is a commercial breeder with Syngenta Monsanto for 13 years. Right now, I'm a public breeder. So when I talk about those challenges, that may help you to understand the challenge. And so for the breeding, the challenge, for example, we usually have on the top, you have the image from 1 to 5. Basically, our breeder go to the field. We, based on our experience, we give them ranking 1 to 5. And also for the disease resistance, we calculate, well, we use our naked eye based on the incidence and severity. We give them 1 to 5. And eventually we give them high resistance, low resistance, moderate resistance, etc. Also, we doing root system architecture breeding. We gave them branch with a lot of fibrous or tuberous. So we breeding those specifically for different reasons. For example, we talk about the changing climate. We want to develop really taproot that can go really deep, can absorb the water. Or we develop a lot of branches with the fibrous for water and fertilizer use efficiency. And also the bottom figure is recognize the digits. So that you can see from the breeding side, we have a challenge for the language analyst. We also had the challenges. Some of those challenges we call it inconsistency. They're not necessary error just between different breeders, but among different labs. You ranking those differently. And others is you just by accident, there are errors. So how can we address those things? So there are two ways. And to me, if you have a large number of data, you just choose from the two extremes, the best and the worst. You do not worry about the one with the question mark. That's really easy. And if you do not have a large number, then you have to go with those materials. You have no choice. For example, for mapping population, and you have to live with the middle phenotype because those are the one that accumulate number of different QTLs. So you have to have those. You have to have a phenotype call for any of those plants. So what is the way? So confidence learning basically the way to address this issue. Here the example I will talk for this products. We specifically working on using confidence learning and RAS-19. So what you can see here is the contrast between corn and alfalfa. The one I'm specifically working on right now is alfalfa. They are so different. And this is a typical one with a lot of branches and fibers. They're associated with more nitrogen fixation, by higher biomass yield. But when we go to the field, you can see the tabrous, there are variation, and the branches with a lot of variation. When different breeder or different people rating those, whether they're branch with the fibrous and the scale 1 to 3, and the taproot with scale 1 to 3, we really do not have a consistent call, and really big challenges. So then we found a group of geniuses from MIT and Google, they developed a program called confidence learning. And the way confidence learning is, they will using the predict probability, no matter what, like support vector machine, CNN, or random forest, whatever machine learning program you will use. Every image you will have a probability for different classes. So for the confidence learning, the input actually is 2 input. One is the predict the probability with whatever machine learning you are using. Number two is the raw label that with the errors. So the confidence learning in the background is they will calculate the drawn probability. With the drawn probability, they will calculate a threshold called confidence threshold that minimize the false positive and false negative, etc. So this is the threshold. This is a cycle how the confidence learning. So basically, they will start with whatever machine learning. You will find error based on the drawn probability and the threshold, the confidence learning threshold. So once you find that, you will tell the people who label those images or scan the diseases, etc. So you feel those are either error or low confidence, then you ask them either to relabel them, or you ask some more experts to label them, or you could remove them. So after that, you have high quality data or relabeled quality data. You retrain the model, use whatever machine learning, for example, the CNN or random forest. You retrain the model, you will get new predict probability for each classification. Then you recalculate the drawn probability with the relabeled. And you will calculate another level of confidence level that you will repredict. You compare that with the high quality or low quality data, ask the expertise to see whether this is improved or not. And one statement I really like is machine learning really useful for large companies where I work for Monsanto Bayer. So every year you accumulate thousands of images. So basically this year you do not know the truth or you have low quality, low confidence level. You ask them to retest that material. Next year you get higher confidence, and that input will get into the model. They will retrain the model to help calculate confidence level. So that's the beauty from the big companies. They accumulate data every year, and then they go back to the machine learning, to the model, the confidence level improve. So until after several circles, until you feel this is what I'm looking for, this satisfy my need. So we will stop there, finalize the model for that year. And again, next year, you continue to improve the model with the confidence learning. So that is a confidence learning model. Will that really help me? So we have two data sets that collected from different labs. One from my lab in St. Paul, Minnesota. We have 617 images. And the other lab in Oklahoma, in Larry, York. And we want to test whether the confidence learning working well or not. We also want to test whether cross-lab predictability, whether machine learning helpful for that. Also, we want to test if we combine the two data sets, they're genetically not related at all. My breeding program from Larry's 264 is a commercial one, whether since they are genetically not correlated, whether those confidence learning will help on that or not. So we did all those permutation, all the possible combination within each population, prediction before and after confidence learning correction, and cross population, cross material, and also eventually we combine those together to see whether confidence learning help or not. So this is the results. Basically, a lot of information here. We did a whole bunch of analysis. Eventually, we want to tell people, they will improve by some way, like 10% or 15%. They have a different level of improvement. So how can we see that numerically here is we use two different level of use the images. The first level is we have the images. We use a software like WinRiso to scan each images. We got 38 parameters that predefined. For example, root mass, root length, etc. Then we predict, and we before and after with the raw data and the correct label, you can see the prediction accuracy increase from 65 to 0.85. For the 214, they're also improve for the prediction accuracy. And if you see the visualization, you can see here, basically you can see this is the before the raw label. They're better, they are not separated well. Once you use the confidence learning to relabel those, you can see the PCA that can separate by some degree, improved by some degree. And this is the two data set. If you separate them together to see the raw data, to they can separate as well. So the conclusion is for applied confidence learning, we needed to have several iterations combined with the expertise from breeders, readers, and to help improve those. And the confidence learning for our example for the RAS-19 increased from 11 to 13%. And with that, we also developed a mobile app and to address the consistency between different readers, different lab. So you scan the root using your mobile phone, they will tell you what is the root tab and also give you the probability and the confidence level. So with that, I think, acknowledge this is the team, we did the job together. That's all. Any questions?
Awesome. Thank you for the great talk.
Yeah.
Any questions from the audience? We have about 5 minutes for Q&A.
No.
Thank you for this great presentation. So I have just a question related to confident learning. So, I mean, we are training lots of model by using really big data. So, and our big data contains obviously bad data in it to some extent, but we really don't know. So I'm just wondering how bad data has the influence your confident learning. So is there any experience of yourself to illustrate this situation? Thank you.
Yeah. Thank you for your question. Before I answer your question, share my story may help us to understand my answer. So I work for Syngenta Monsanto. We have 20 years genetic phenotypic data. We were asked to use historic data to see you use the first 10 years, predict 11 years, or first 20 years, predict 21 years, that how well the results will be. And the other question is, with all those genotype phenotypic data, whether you can finish the work breeder did in 30 years, you can do it within 5 years because you have all the power from the genotypic and phenotypic data. So we did a bunch of analysis, and eventually the first phase, we didn't get that results as we expected. Then we asked why. So we realized all the data, Syngenta is formed in 1999, coming from 5 smaller companies. Different company use different experiment design, plot size is different, and yield is different, but we will combine them together. There one high yield compared with the other high yield is not comparable. They're really bad, well, not bad, they're really different quality of data. So we realized that then we do quality control. We do not have a confidence learning at that time. We just hire a smaller group of high students to check the process from each experiment manually. Then we do the quality. Eventually we improve the prediction accuracy by some degree. Then back to answer your question. So at the beginning, we do not know how well how high, how low, how bad your data. And from the confidence learning, it gave you your level that, or this data really bad, you need to remove it. Or this data is good, you do not need to worry, or this data needed to be improved. So that is a license I learned. If you have large amount of data, if you have a smaller amount of data, you have to live with it. You need to improve that. Yeah.
Any other questions? So I do have one question. So I've looked at RSA myself. So I'm more on the AI side of things. So you mentioned that you all have to choose like a certain threshold for your method, right? I guess how sensitive is your method to the threshold that you use for your work?
Yeah. So that's a really critical question. When I had my PhD defense in 2020, people asked me what threshold you use and how sensitive to that threshold. So at that time, I do not have an answer, but after my defense, I have the good answer. We needed to do a ROC. We need to calculate the area under the curve. So change that threshold from 0.5. The default threshold for logistic regression is 0.5. We change that threshold, then you have the false positive, false negative curve, then tell you how stable your model is. Yeah.
Sure.
Yeah.
Due to time, we'll switch to the next speaker, but thank you for the presentation. And Chin-Ling is next.
Howdy, everyone. Okay. My name is Jin Lee. I am an assistant professor at the University of Georgia. And before starting the presentation, I would like to mention that this research work was done by a collaborative team. We have team members from different institutes. On the stage, you can see we have team member from Texas A&M, Dr. Robert Strong on the left, and we have Dr. J.N. on the right side. It's my right side, yes. And Ms. Marburger. I want to mention Dr. A.N. will join the University of Florida as an assistant professor this August. And Ms. Marburger is undergraduate researchers. So we unfortunately have a great team here to present this work. And I also want to mention we have team member from Europe. We have team member from the Wageningen University and Research. We also have team member from University of Oxford. So today we're really excited to share this international, interdisciplinary scholarship with you. With that, let's get started. So predictive AI is used in interdisciplinary industry and discipline from business, energy, food, agriculture, and much more. AI's achievement, advancing the achievement of sustainable development goals is well documented. Both the USDA and the FAO have intensified their communications to the benefits and ethical considerations and opportunities surrounding AI. Their strategic plan reflect there's a growing awareness of AI implementations in shaping the future of food and agriculture, underscoring the need for proactive engagement with this transformative technologies. So we use Lankentesh et al.'s unified theory of acceptance and use of technology as a theoretical framework in this study. As you can see right here, this four variables in the left column in this model are predictors of behavior intention, and behavior intention directly predict behavior change. So what are those 4 variables here? Performance expectancy refers someone believe use such a technology can increase their job performance. And effort expectancy is the level of effort to use such a technology. Social influence ties to influential people affect others' adoption or rejection of such technology. And facilitating conditions really are worth it is an infrastructure. And organizations have both human and physical infrastructure to support the use of such technology. Next, I'm going to hand over to Dr. Ann to talk about extension's role.
Thank you, Dr. Lee. My name is Jae An. Let's think about the land grant system. So each state land grant systems or land grant institutions are unique American idea. But what about the future? So we have to think about the future. There are opportunities and challenges, obviously. So like Dr. Lee said, Dr. Lee is from Georgia, and Georgia has 159 counties. In Texas, there are 254 counties, and I'll be soon joining University of Florida. Florida has 67 counties. Each county is facing different challenge and opportunity. So, so how do we think about the future in land grant system? Recently, I mean, there's some wildfire and in Texas, and how can we move or sync up the city infrastructure to Panhandle? So that's another question we have to think about. So let's think about the like a machine or vehicle that is really well balanced. So it's like so federal level, state level, and the local level. So we think globally, we act locally. So it is really important. And then think about the technology or techniques or practice we introduce to farmers. And then how can it be adaptable, or really practical and evidence-based change, and then ultimately evolving a landscape. So that's really important question. So if you think of federal level, yesterday we actually heard from USDA NIFA, it has to be well connected to a state level. So Texas A&M here is a land grant institution, and we have to well connect it to and with federal level, USDA NIFA, and then we have to think about the municipal level and city level and local level. So it has to be synced really well. Okay, so why do we this, and what are the purposes and objectives? So we have to think about the AI. So we are talking about AI, and the AI integration into land grant system and vice versa is really important. And then how we integrate. So it's really the question that we have. And then again, I mean the federal level, state level, and local level. It's really important to share the idea, the data, and the results and methods with the public. So so how Dr. Strong is gonna dive into that. Thank you.
Thanks, Dr. An. It's great to be here with you. And so as we think about the theoretical framework that Dr. Lee shared with you earlier, we use that to support this respective study. Before I go into methodology in detail, I also want to recognize Dr. Ahmed at Prairie View A&M. He's in the crowd. You saw his name there on the cover slide. And so as we think about building a respective study that we can hopefully generalize our data to a large population, this data set included extension agents across the southern region of the APLU in the United States, including Puerto Rico and the University of the Virgin Islands. Okay. And oftentimes, you know, I think it's important. We talk about this in class all the time as we talk about the land grant system. We really need to make sure that and as I'm telling you this, I'm telling myself, we need to make sure that we communicate not just us 1862 institutions, but also the 1890 institutions. And so I've been extremely fortunate in my career to have some solid collaborations with Dr. Ferris and Dr. Ed at Prairie View, and others at Tennessee State and North Carolina A&T. So my point in sharing that with you in detail is that all of those systems are designed, as you know, to develop and train and evaluate extension agents' performance out in the field. So I'll share that with you in detail. And so you see the total number here of agricultural extension agents covering the region, again, including Puerto Rico and the University of Virgin Islands. And so what we did is we did a census sample of all those respective agents. And what we're going to present to you today, this morning, is the final result of usable data that we're going to share, which is 812 responses. I think it's important to recognize that information generated at our institutions is only information until it's actually disseminated and results derived from that in local communities. So this group on our team, we're very passionate. You saw on there Oxford, Wageningen, all of us, of course. Our team's very passionate about not just how research is generated in institutions, but is it actually used with stakeholders out in the communities? And of course, extension being hopefully our better link to making that happen. So I'm going to share with you again, Dr. Lee talked about the independent variable constructs of the UT-AUT. And with this path analysis data, you're going to see dependent variables all on the right, which align with the extension program development model. And so the first aspect of that model is program planning. And so to walk you back on the statistics just a moment, the literature indicates that a path coefficient of 0.3 is good enough. That's in quotes, good enough. However, we attacked this with a much more conservative lens. So we were going to report those that had a coefficient of no less than 0.45. So we're working against a threshold of 0.45. And so as you think about 0.45, as you notice on the screen, look at these that really jump out at you that predict extension program planning efforts as it relates to artificial intelligence disseminated data. And so you didn't ask, but I'm going to tell you anyway, my favorite AUT construct, Dr. Lee, is social influence. I love that one because it tells us that if my peer, if an extension agent in another province, parish, or county that I respect, I have credibility in, if that individual, if she says, hey, Robert, you should do this with your stakeholders, more than likely I'm going to do it, if that makes sense. And statistically here, we proved that in the region, again, all 15 states, Puerto Rico and United States University of Virgin Islands, that was the case. So if our threshold is a 0.45, all of these explained program planning, but look at that 0.84 for social influence. That makes my heart happy. So our next one in the extension program development model is design and implementation. And so here again, you see how some of these factors move and they're different weighted coefficients as they go. But notice here one more time that an 8.6 from social influence directly tied to design and implementation. So we're reinforcing here that in the first two phases of the extension program development model, that agents across the region, Puerto Rico, University of the Virgin Islands, they're relying on each other to encourage themselves, professionally develop themselves. That is not to say that these other coefficients do not matter, because again, we're operating on that threshold of 0.45. So as you digest the data in the amount of time that our presentation has, there's a lot going on here as it relates to the acceptance and use of technology, specifically in this study to artificial intelligence. The third piece of the extension program development model is how agents are able to evaluate their programs and training and what impact that has on their constituents. And so you see again, the variables move and the coefficients are different, okay? And so here, facilitating conditions at a 0.8 on evaluation. Remember, Dr. Lee said facilitating conditions. Does an organization, does an individual have the collective infrastructure that they believe that they need in order to make that happen or to use that to their best ability? And again, social influence guy here talking, look at this piece of social influence connected to effort expectancy, right? But when agents when they believed that AI was easier for them to use and understand, they feel better about how they're going to evaluate their programs and the resulting impacts on their constituency. And finally, I share this one with you because this also does my heart good. There's several people at this conference who do an excellent job of posting their work on LinkedIn or X or ResearchGate or YouTube or all the above. So what we're trying to do here, or is to better understand, is how extension agents are able or feel like they are able to take their reports or their impacts with their constituents and their communities, and not just share that through the pipeline of their institution, but also share that more broadly through a conglomerate of social media handles, i.e. LinkedIn, X, et cetera. So with that said, again, let's drive back to the effect of social influence here in determining the effort expectancy of their peer network, and also that's effect on their actual reporting of their accomplishments beyond what they're required to with their organization. With that, I'm going to turn it over to our undergraduate researcher, Morgan.
Thank you. Like Dr. Strong said, my name is Morgan Marburger. I'm an undergrad research assistant here at Texas A&M University. So some of the conclusions from this research study is that we are looking to take the new data and issues regarding proactive culture of training to help take a more proactive approach towards educating our extension agents on this predictive AI. So extension agents will also need to have a more targeted and persistent approach in order to make sure that these innovations in food and ag systems stay current, especially with other change agentries organizations. When looking, researchers and extension agents need to foster a symbiotic and synergistic relationship in order to ensure that that information that's coming from these researchers is correctly disseminated throughout the data and the actors throughout food systems. I'm going to hand it back over to Dr. Lee.
Thank you, Morgan. So finally, we want to open some discussions with you. As you can see this picture showing again, this stands for Southern Association of Agriculture Experiment Station Directors, also called SAAESD, that aims to encourage collaborations amongst agriculture researchers in the Southern U.S. So we want to emphasize, as Dr. Strong say, that collaboration between each other is important. We want to emphasize the importance how to collaborate these things together related to the AI technology. And we heard what producers say yesterday from the panel. They talk about they need AI, but sometimes they hold back because about those data sharing, they're scared of it, but also they need it. So how we reflecting on the perspective from them, then researchers at the land-grant university, we need to go together and build up developing a multi-state research and extension projects to ensure the impact and the benefit, and that we can share this kind of AI implementation through stakeholders and or with stakeholders and work with them. So we can make sure that through this kind of development of collaboration and relationship, that there can be a real impact and benefits to stakeholders. With that, this is a reference to this presentation, and thank you.
Thank you all for the excellent presentation. How about 4 minutes for Q&A?
Well, I'm looking for a really great talk to ask my following questions. I guess this talk is the best talk I have ever seen related to, you know, the communication and the collaboration. But we are using lots of data, as I mentioned in my previous question. But I'm really wondering what is the best way to share our data and then, you know, to boost our collaborations with the other universities and increase our chance to write the grants, for instance. But my question is related to data share and what are the main ethics when it comes to share the data, especially the big one, because right now our last solution is very funny. We are just shipping our USB to other universities to share our big data. But yeah, what's your opinion about that? Thank you again for the talk.
Okay, you want me to go first? Okay. So about sharing data, I would like to say, like we heard from producers say yesterday, trust. You have to build that foundation of trust between each other. So like you say, you have like this kind of conference is the best opportunity that we share our experience, our research to each other, and to make sure there's a similarity or difference there. And then we can talk about it, open the discussion with each other, and then we can build on with that foundation and then go beyond with that. Yes. So Dr. Strong, you want to add something, or Dr. Ann, you want to add something to it?
So thank you so much. Thank you so much for the question. So data sharing is not really easy, right? So so every institution, land grant institution, has different policy. So to make sure that we are transparent, sharing the data, it's really challenging. So we have to think about that. The other thing I like to add on that is so I'm trying to promote the interdisciplinary approach to tackle a lot of different challenges, and then we talk the different language. So basically, so data have to be replicable, and then it has to be we have to basically have to share after we run the data. We will get the result, right? So we are talking about the predictive AI, generative AI, but basically my experience tells that, I mean, really, we have to, before sharing the data and before sharing to the public audiences, we have to make sure that we talk the same language. So that's really critical point. So yeah, thank you.
Awesome. Any other questions? So I have one. So Dr. Strong, I saw your slide. You all mentioned that you trained a machine learning model for the findings. What model did you all use for your work?
That's a great question. If you'll allow me to go back to the abstract, Dr. Ingram and Dr. Arthropades, Dr. Ingram at Oxford, Dr. Arthropades at Wageningen did that, but I can get that to you before we leave today.
Thank you.
Yeah, thank you.
Awesome. Well, thank you all again for their great presentation. We'll switch to our next presenter.
Hello, good morning. Good morning. Happy to be here. My name is Setiyono from LSU. Also would like to say good morning to those joining online and maybe watching on YouTube later on. I'll be talking about from the user perspective. So we heard about democratizing use of AI. So you guys are looking in an example of one case, and I think we have previous cases as well. So I want to share experience of using the deep learning. So we heard about Dr. Mula about the deep learning for image classification, and this is an example of that. And the specific application is on identification of herbaceous mimosas. So I have a slide to explain a little bit about these because so this is based on a published paper recently in Smart Agriculture Technology. I have the information here, and I would like to also thank co-authors of these as well. So I myself, I'm on the precision ag, remote sensing, and modeling is my expertise, but I'm not specifically expert on these subjects. I have the last two co-authors listed here, Dr. Kun Jun Han, a forest specialist, and Dr. Pittman, Buddy Pittman. So if you have specific questions on the subject, on the mimosa, I will forward it to them, and so they can help me answer very specific. But I also learn about this species because one of the aspects we are looking in the future, actually it's already here, is the climate is become very extreme. So we heard about the drought emphasis in the previous talk, but at the same time, when it rains these days, it comes in a very erratic amount, and then it's extreme. So that means two things: you have more dry spells, but you also have concern about erosions. And so this is my claim of this particular species. Maybe it could address some of these problems in the future and currently, because some of the criteria of this mimosa, herbaceous mimosa, is a deep-rooted species. Therefore, it's good for erosion handling. And if you look at the mimosa plants, it's very similar. If you're familiar with Mimosa pudica, it's the one that if you touch the leaves, it's kind of wrinkle, folding. That folding ability is one of the strategy physiologically to conserve water. So this is a very drought-resistant species. Therefore, it's ideal also for drought mitigations. And it's a legume, so it will fix nitrogen for you. And so there are several applications of these from forage, also for mats of even replacing typical grass, because it is low maintenance and you don't need a lot of water. And so one of the important things is the beef cattle really love this, to graze on this, and it has a very good withstand foot traffic as well as the mowing or the grazing tolerance as well. And for those who are more on the helping the environment, this also have other properties, such as it's inviting sulfur butterfly, because it's also the providing larval food for it. And so that's another benefits of this. Therefore, actually within the southern United States, this is the native of this species, and there's a lot of campaign or a lot of movements trying to promote this particular species because of this great nature, and also it's good to promote a native species. So as you can see, this is something shared around southern United States, something that we have in common, that the species appear native, and also based on these maps, you can see USDA and RCS published the range, expected range, so to speak, and the reported occurrence as usually they update it very recently. So you see it's some areas, in fact, expanded beyond the range, it's spotted, but some area that is supposed to be there is not spotted. So there is also dynamics that you can see from up to date, the information that we find on the public sources here. And that's why when I was trying to work on this particular study, I discovered this, and this kind of discouraged me from going further, because apparently there is already an engine online available, or somebody already published an engine that actually detects a bunch of species. And I wasn't aware about this. There is a global biodiversity information facility. This is the site there. If you're familiar with this site, maybe this will be just a review for you, but they actually have a bunch of AI stuff applied on different species, and this species are actually included in there, meaning that there's also some version of AI that can handle this image of this particular plants and can generate information. And they publish it here on this site, basically showing where it is based on their model, where it's expected to show. But obviously the resolution of this kind of information is not ideal if you want to do a more detailed study at the farm level, for example. And so that's something where we're interested. So this won't help us, right? Similar technology, but not quite there yet. So so the idea is, how can we use some of the technology that we have now, try to map at the farm scale level where the distribution, spatial distribution of these species, by leveraging in this case, a deep learning technique. So at the first step, we are using a close-up image so that we have a very clear photos, images that we can train. But eventually, the goal is to move to a drone imagery that we can also apply similar algorithms. So the use of deep learning started in the mid 2000s with only two layers. The inventions of perceptrons. This is something I learned as I review this subject. But the jump happens really quickly. In around 2012, you can have 5 layers of the neutrons, and that's considered deep learning back then. And fast forward to just 2018, you have to have more than 100 neurons in order to consider the deep layers now. Now that's the numbers that we're looking at, over 100 in order to be considered deep layers. And that's because of the advances in the computation, obviously. So we want to take advantage of this because the way it works is that just like our brain works, the deep learning works by simply dividing the tasks. A simple task first, looking at an image. If you're looking at an image, you first probably look at what stand out, right? So for example, if you have image of plants, flowers stand out. If you see the flower, okay, that's first identification perhaps, but flowers are not just only identification, you have to look at the leaves. So this is the kind of idea where the deep learning can be applied here, because you're gonna ask the machine to look at the subject and start to looking at further detail, and that's where the deep learning component come in place. So some of the methodology information here. So the study side, we have 2 contexts. One is on the so beef cattle forage study. This was in the research station in Red River Station, Bossier Parish in Louisiana. So this was our original site, a research site where we know they actually maintained the population of Mimosa strigillosa there for their study. But while I was studying this, we needed more samples, and I have other unrelated activities in southern Louisiana, in Napoleonville, and there I found actually more population of these occurring naturally on the on-farm access road in the sugarcane areas. So which is fortunate for me. So I collect data there as well. So 2 different study areas, and we collected some drone data. This is in this paper is used to identify or to describe the study area. But the main data for the machine learning come from the handheld one that we kind of customize so that make it easier. For example, we use remote trigger of the camera with the monopod so that it would be easier to collect data with a consistent height about 1.2 meters above ground. All right, so the nature of those image data inputs about 4,000 times 3,000 pixels, and then we splice it into 12 so that we can multiply the number of inputs, because we need this, a lot of number of inputs. And then we also have some annotation rules. For example, you can see here in the image to be identified to have herbaceous mimosa has to have at least 25% in the image. So if you have very little, we ignore that, right? And then if it has a mix, then not more than 15% of that has to be other species. Obviously, if it's completely mimosa, that's ideal. So it's like the figures there, the numbers, labels C. As far as the contrasting the non-mimosa figures, it can be anything, it can be bare ground, as one of the image there. Obviously, any mixture is fine. Okay, so that's kind of the annotation rules that we use. Here's some example of the image that we use. As you can see on the very top, those are all mimosa. So sometimes you have found mimosa without their flower. The flower is pink, as you can see there. It's like a powder looking pink. And then on the bottom, you have other non-mimosa. But as you can see, some of them can be kind of challenging because it's also pink, but it's not mimosa, right? So if you look at a distance, that might look like, but if you look at the leaves, it's different. And that's, we are hoping that the machine will be smart enough to figure that out. So here's the study locations. On the left there, on the right side is for the sugarcane area. This is a farm access road. So you can zoom in closer where we can see that. And oops, sorry, I guess the animation doesn't work here. So on on the left side, that's where the Red River Station on the beef, the cattle beef areas. So here's some of the parameters that when we run this. So this model is in Python, Jupyter Notebook environments, and it's in Conda virtual environments. And we standardize the pixels to 180 to 180. And one of the things that we are doing in this paper is that we want to see how sensitive it is if we drop the number of inputs. Because as you probably looking at the public TensorFlow, some of the example that comes with it always come with about 10,000 input data. That's a lot of images. And the best I could collect was about 2,116. About 70 or 80% of them, my graduate students helped me collect. So obviously it's challenging to get that number of inputs. And so to test how well is this model perform, we just drop the number at different, we run it at different number of inputs, to an extreme low so that we know how well it's going to be performing. So that's the idea of this thing. And then we are using not a very advanced machines also. We only have 16 gigabyte RAM to run this is on purpose because we want to see if it can run in this low configurations computing power, then it should be fine with more advanced computing power. The number of inputs 250 and the batch size is 10. And we have a 3x3 kernel. And 128 neurons, so that's the number of layers required in this one. So the two activation uses, first part is a more simpler linear activation because that way we can more faster computation, but toward the end, a little bit more fine sigmoidal one is used for identification of either 0 for non-Mimosa or 1 for Mimosa. So here's the results. So this result divided into, I'm going to start from the very bottom one, the label G. That's the one that we have the most input. So, and the blue line indicate the accuracy of the validation data sets. And then the red there is the loss of the validation data sets. You can see that we achieve the quite high accuracy and relatively stay stable. And then we drop the number of inputs, and the next one on the label F there is still performing well, and the next one still okay, but there's a little bit more instability in terms of the accuracy. As you can see, at some point it drops. And the next one also still okay, but a lot more instability. But then the last one is just get pretty bad. So based on this, we were able to tease out what is the minimum data required to do this. So then I just compute this because the time might be also an important component, how long it will take. The most data set that we have, it will take about, more than 20 hours to complete. So if time is an important component, you also have that information here on this particular configuration. So not just the accuracy is concerned, maybe if you are in short time that you want to get something done quicker, it's just something to consider as well. With that, I would like to thank again the co-authors for this work, and we hope to continue working and expanding this activity. On probably next step, we're going to be using the drone imagery to do a mapping process. Thank you.
Thank you so much. We have time for 4 minutes for Q&A.
So thank you for this excellent presentation. So I'm just wondering, maybe I missed, but I'm wondering what growth stage of the Mimosa is the best growth stage to map them?
Oh my
Is it the
goodness.
flowering time or vegetative growth or what?
Well,
Thank you. And also, I'm sorry, maybe I missed what data you used in the A and what data you use in the G where you were showing your
Oh,
loss
okay.
and accuracy.
All right,
Thank
okay.
you.
So the second question for that's straightforward. Those are just the number of inputs changes. So the last one, the G has the most, all the data. And then on the other panel, I just drop about half and then another half. So less number as you go over the panel. And the first questions, are you expert in Mimosa? Well, obviously, I'm not. Well, it's a perennial crops. I don't know about the stages, to be honest. So that's but we actually go there when our experts tell us it's there coming out. So the nature of this, at least in the grazing area, is that because the cattle really love the species. So as soon as they open the gate, so that's how they have multiple gates, multiple compartments of the range areas. So as soon as they open, they all rush there. They clean it up. They graze it really low, just the mimosa they pick up, and then they get the cow out and then let it grow again. So usually after they grow again, I don't know specifically what stages, but if it's enough numbers, so I guess typically that's also when they start flowering. It usually depends on the rainfall as well, and then we will go there. Yeah. So since you mentioned about this, when we were there collecting the data, as soon as that gate opened, they actually letting us in to collect the data, but actually the cattle got in first before us, and that's just to show that they really love it. And in fact, Buddy Pittman told us that the cattle want to tell you how they love the species. So we have to rush the cattle out before we can collect, and that was an interesting experience for us to show that they're telling you how they love it, but not necessarily they know what they're eating is actually good for them. We have no idea. But anyway, so yeah, that was an interesting experience.
Hi, nice presentation. Thank you for it. You mentioned in the annotation rules that you had said like if it's at least 25%, then you're considering it as the specific class, which is Mimosa.
Okay.
So have you, first of all, do you think like when you do 25%, the rest of the images, 75% you consider it just as background or not Mimosa, or do you think 25% is enough for the class? Have you tried changing the rules and seeing if increasing the threshold value that you consider as a class within a specified split image affects your accuracy? And the second part is when you said you dropped some images or considered different inputs, I wasn't completely sure what you're talking about. Is it like the data set was removed or was the input size changed?
Okay. All right. Again, the second part is, yeah. So basically the number of input I varied from each of the runs. So each run, I use all the inputs and then I run again, remove randomly. Okay. That's more important piece that I forgot to mention. I have to do random removal of the inputs. And the first questions, yeah, that 25% rule, we haven't really explored how we're going to do. But what we did was, if it's a mix or if it's not enough 25%, we actually just discard it. We don't use those images. But we don't have many of those images. Obviously, when we collect it, we target it specifically. We want area where a lot of mimosa, and the students also did the same. They look only, the area has a lot of dense mimosa. But yeah, there are a few images where we have to remove. This is just a first step, but if you look at the stability of that, this is maybe something for further investigation, particularly understanding how the deep neural network work. Maybe we didn't have time to look at it, but I'm curious to know why the stability changes quite a bit. I wonder if at some point it learned too much and it become uncertain anymore in the process to look at the next image. And bear in mind that the background is very, very noisy in this kind of data sets. It's very different than the typical data set that you have dog and cats. It's very obvious. So I wasn't so sure this is going to work in the beginning. I was surprised it still works, but that noise of the stability of accuracy, sometimes high, but then in several epochs later, you see that drops again. And so I'm still don't know why that is. For those who are expert in deep neural network, maybe you can look at it in detail, what happening there. So that will be interesting. Thank you for the questions.
All right, thank you again. All right. All right, so we had two presenters that weren't able to make it to the session, so we're going to end here. So I encourage y'all to network or go to other sessions. But before we close, we'd like to get a picture with all the presenters in this session up front. So if you can come to the front, but thank you all for attending the session.
Howdy. The man. Howdy. We're getting closer. Third time's a charm. Howdy. Okay. Again, sorry to interrupt the richness of conversation here. A couple brief announcements, I think. We'll skip through that and go to this. So people are going to start drifting off. I mean, we've already got a little thinner crowd than we had this morning. So really appreciate everybody's attendance. But I think we once again want to thank all of the sponsors, especially the various Prairie View institutions, Texas A&M, LSU, and of course USDA and NIFA for the large conference funding grants. So let's give them a round of applause. Unfortunately, we've already lost a number of the conference planning members, but once again, can our conference planning committee stand up? Mahindra, what are you doing? Okay, so let's thank them. Put in a lot of effort. Anna's on here, you know, thank Anna and Ben and all the hotel, of course. So a couple more announcements. Remember, on the back of your tag is a scan for full agenda. That takes you to the link tree. The conference survey is really important. Okay, we don't know who's hosting the next meeting as of currently. Remember, this is the third meeting, first at Auburn, then at University of Florida last year, and now here at Texas A&M. I understand that probably by August we'll know who the next host is, but they will use your feedback for improvements, and it will probably be a somewhat separate conference organizing committee. So if you have any suggestions or things you liked, please make sure you put those in there. For posters, we do have cash awards for posters. Mahindra is the coordinator of that, and we will announce those after lunch, and he will thank his poster judges and all that. So for graduate students and others who entered into the posters, please stick around for that for sure. This afternoon, we have another number of sessions. The ethics one, we will have a discussion. The other two sessions will again be open discussion. And I'm going to guess the crowd will be a little bit thinner for there, but if you want to talk about how we can make progress in these areas, please stick around for that. I think that was all the announcements I was supposed to make, unless I'm forgetting anything. Oh, it'll still be after lunch. It'll be after our next talk. Yeah, thank you. Good catch, good catch. So it's my distinct pleasure to introduce. Is it okay? I'll go to the slide now. That way everybody can read your name. It's my distinct pleasure to introduce Dr. Jennifer Clarke. Dr. Clarke had received both a bachelor's in psychology and a bachelor's in mathematics from Skidmore, a master's in statistics at Carnegie Mellon, and a PhD in statistics at the Pennsylvania State University. So I've gotten to know Dr. Clarke through a number of different organizations over the years. And if one word sticks out for me of the land grant mission, it's service. Dr. Clarke probably does more service than almost anybody I know. In fact, Monday she was writing her own conference grant proposal because she is the lead of the International Plant Phenotyping Network meeting hosted at University of Nebraska at the end of this year. So Dr. Clarke is a professor and a director of quantitative life science initiative at University of Nebraska, where again, she's engaged in an absolute ton of service. She works in a research area encompassing statistical methodology with an emphasis on high dimensional predictive methods, statistical computation, bioinformatics, computational biology, multi-type data analysis, data mining, machine learning, and bacterial genomics and metagenomics. She's extensively published. But what really attracted Juan Landever and I to invite her as one of our 3 keynote speakers was the talk that she gave at the North American Plant Phenotyping Network, which I think was super enlightening for connecting statistics to machine learning to AI. Very excellent communicator. So please, let's welcome our final keynote speaker, Dr. Jennifer Clarke. Yeah. And she's so selfless. She's more concerned about your questions than her own talk. So next and back.
Okay, great. I'll try to. It's like when I wish I was a couple inches taller. Seriously? Okay. All right. Success. I can go home now. All right. So thank you very much for the lovely introduction. Thank you to all the organizers of this event. The talks have been fantastic. And the best part is all the conversations that everyone has had, the posters. I mean, just the content has been fantastic. So thank you. And I'm so glad there's still people here to listen to my talk. Okay. So what I wanted to focus on, because I'm a statistician, is what is the role of statistics in this whole wave of AI, right? So when I started as a faculty member, I thought of myself as a statistician, as a computational statistician. I'm not going to tell you how long ago this was. And then over time, right, then it became, okay, maybe you should call yourself a data scientist because data scientist sounds so much cooler, and I was like, yeah, but I already am a data scientist, right? I'm a statistician. Oh, okay, I'm a data scientist. And now it's the AI wave. So now do you call yourself an AI person? Okay. So I decided that maybe I should spend some time thinking about how statistics fits into all these conversations and some of the ways that statistics and statistical thinking can contribute, right? Because what do I get when I tell people I'm a statistician? I get a binary response. I get either, oh, I love that class. Like, oh, it's so useful. Or I get, I hated that. I waited till like the last semester of my last year to take that class. It almost killed me. So I'm trying to, kind of maybe bring those two together, right, a little bit to understand that, statistics can be useful and it doesn't have to be so opaque, all right, to a lot of people. Okay. So first I'm going to talk about, which seems not relevant, but you'll see, I'm going to talk about Occam and Hickam. When I talk about them, you understand why. Then I'm going to talk about shrinkage techniques in variable selection, and I'll explain what that is. Then I'm going to put forward a hypothesis on how AI works, right? From a statistical standpoint. So I'll talk a little bit about how statisticians think. And then why is that important, right? And how does that give us some insights into how and why AI works, right? Then I'll talk a little bit about identifiability because it's important in modeling. It's important in AI if you're a scientist and you actually want to answer a hypothesis, right? Then identifiability becomes important. If you're just worried about good prediction, doesn't matter, right? It doesn't matter. But if you really have a scientific question, which I think most of you do, and certainly most students do, then it becomes important. And then I'll touch briefly on what are the challenges, some of the challenges we're going to have in AI, broadly speaking. It applies to agriculture, but also applies to other areas. If you have questions, right? Okay, I hate it when I give a talk and I can tell that half the people don't understand what I'm saying. Or at some point, they just, So if you have a question at some point, please feel free to ask. Right? You don't have to wait until the end. All right. Seth has the microphone. So feel free to step up and say, like, could you explain that a little bit better? Right. Because the point is not to leave you behind. All right. So, okay, Occam. So there's a concept in science called Occam's razor. Right. So named after William of Occam. From the late 1200s or the early 1300s. He was an English Franciscan friar. He was tasked by the Catholic Church, by the Pope, to look into what are the theological implications of the church possessing material wealth. Okay. The reason I'm talking about this is because Occam promoted the idea that there's a principle of parsimony, which is important when you come to modeling. There's a principle of parsimony when you're trying to decide which argument is correct, which is the same thing we do in statistical testing, right? We have two hypotheses and we're trying to figure out which one is the correct one. All right. So the way he stated it was, no plurality should be assumed unless it can be proven by experience. What does that mean? That means there should be a reason, like some experimental data, some justification to introduce a more complicated theory or model. All right. So to put it really simply, keep it simple. Right? Unless you have evidence to add something to your model, don't add it. Right. Go with the simple explanation. Right. And this was adopted into science and the way we do science. Right. We tend to go with the simpler explanation that we can justify, right? And if we can't justify one of our claims, we go out and collect more data. Okay, fine. okay, things didn't turn out so well for Occam. He's Franciscan. He went back to the Pope and told him, you know what, the church really shouldn't hold all its wealth, right? It should give the wealth to the people. The Pope wasn't very happy with that answer. So the Pope excommunicated poor Occam and he ended up moving to Saxony. Okay, fine. Regardless, he had a good principle. Okay. And to be clear, Occam didn't come up with this. Like many things in science, this goes way back to the Greeks. It was actually Arab scholars who brought this thinking to the Western world. So we all stand on the shoulders of giants, even poor Occam. Okay. Hickam had another saying. Hickam was a physician in the 1950s. Okay. And he worked at Grady Memorial Hospital in Atlanta. It's a huge, huge hospital, huge medical facility, lots of training, lots of medical students. And what he noticed was that because of the teachings of Occam and because of what they were teaching in medical schools, there was this push to come up with one explanation. Right? So when you're confronted with a patient, you should have one diagnosis that covers everything, right? Sort of this keep it simple idea, right? So he would walk around the hospital smoking, of course, because, hey, what else do you do if you're a physician in a hospital? You walk around smoking. And he would notice the residents sitting in the break rooms, all smoking, trying to figure out, like, what is the one diagnosis that fits these patients, right? And they'd be discussing it back and forth, and they'd be coming up with these completely crazy diagnoses that seemed to fit all the symptoms. And he realized, wait, this doesn't make any sense, right? And so what he said was, a patient can have as many diagnoses as he darn well pleases, right? There's no real medical reason why you have to have only one, right? In particular, what he brought up was that, sure, you can maybe come up with one explanation for this patient's other symptoms, but you have to take into account prevalence, right? If it's something really rare, probably unlikely that your patient has it. It seems like it would make much more sense if they had diabetes and metabolic syndrome and high blood pressure, right? Things that are much more common. And so he came up with this thought of, wait. Okay, there's no real reason why you have to go with only one, right? It could be much more complicated than that. Medicine is complicated, right? So his thinking was kind of a push against this move to, always go with the most simple explanation, right? So he said, hey, it's complicated. Science is complicated. So don't feel so pressured to come up with one. Okay. So we have these two kind of competing theories, right? And I see this a lot in statistics and in data science and in modeling, where student, faculty member, somebody gets super excited about the latest in modeling and decides, I'm going to do this fantastic AI deep learning approach, and I'm going to engage 100,000 CPUs on the cluster. I'm going to run this great model, and it's going to be so exciting. And then I can put all the buzzwords in my title. And I'm like, okay, you could, there's logistic regression. It's been out there a long time. Still works. Last time I checked. But the way we do statistical modeling doesn't answer everything, right? Just like the things that we talk about at this meeting, and there's places where you definitely should use AI, and that AI is the best approach, and there's places where it's not, right? So I think there's room in the whole discussions around AI for different perspectives, different modeling approaches. Okay. So how do statisticians do modeling? How do they approach modeling? Okay, so before I do this, what is statistics? Right? It gets kind of lost in this whole data science thing. Whenever you see the data science and you see the Venn diagrams of disciplines, and they always have like math, stat, something modeling, equation-y, something computer science, engineering, something disciplinary. And it's like, okay, how do statisticians fit into that Venn diagram. All right. So what do we do? There's a three-legged stool in statistics. All right. The one is inference. Okay. We're always trying to infer something about the process based on the data, right? So it's, you bring me your data, I probably will try to run if you try to hand me your data, but you try to explain to me what you're trying to solve, right? And you're asking me something about a property of the population, right? So if you're in agriculture, you might be interested in, okay, what is the average yield of this new variant, new maize hybrid, right, compared to others, right? So you're asking me a question about what is the average? We don't really know because I can't collect data on every single plant of this hybrid that's out there, right? So I have to take a sample, right? But that's what I'm interested in. I'm interested in inferring something about the population from the data you give me. And I want to make good quality inferences, right? So I want to be able to give you information, give you an answer to your hypothesis that is going to stand up, whether you go out and collect more data. Right? So should remain its truth. Okay, that's one part. Other part is estimation. Right? You want a good value for what is the mean yield. You don't know what that is. You want to know exactly what it is. Okay, so inference is it bigger than other hybrids? Is it if I put more water on my field, am I going to get more yield? Am I going to get economic benefit? Is it going to be better than not? Right? It's always a comparison. But then you might ask me, okay, I need a number. I need to know what I can expect in terms of yield. And I'm going to say, okay, that's an estimation problem, right? I want a good value for that. Okay. And then the other part is application, right? There's lots of statisticians. We spend a lot of time talking about methods, talking about how to fit models. But that's a limited value if you don't actually do something with it, right? So those are the three areas, right? If you talk to other data scientists, mathematicians, engineers, computer scientists, they focus on other things, right? They're not thinking necessarily estimation inference, right? They might be thinking, how efficient is this algorithm? Does it compute quickly, right? Can I code it faster? Can I make it do something different, right? So everyone has their own skills to bring to it. This is how statisticians think. All right, so why is this important in the AI space? Okay, what do? When we're doing modeling, we have three goals, and unfortunately, they don't always lead to the same answer. So, goal one, you want your models to be expressive, right? You want them to capture what's the underlying process, right? So during this conference, we've heard about a lot of very complicated natural systems, right? Weather and, soil health and carbon sequestration and, climate change, big problems, right? Very complicated, right? So you want your model to be expressive enough you can capture the richness of the data, right? Effectively. So that's always pushing you to more complex models, right? Okay, not necessarily a bad thing. Except goal two, all right? You want to control statistical complexity because you want to make the most use of your data, right? As we've heard, there are some contexts in agriculture where you have a ton of data, and there are some where you have hardly any data. So we talk about, AI, and we have all this data. Yeah, well, depending on your question, you may not have a lot of data, right? And you want to make the best use of it. If your model is too complicated, then you don't have enough data to do good estimation or good inference. And it's like, I can fit that model, but, right? So when people come to me and ask me things like, well, I have this question and I need to compare groups. Is N of 2 big enough? No. But, if they come to me and say, what should my sample size be? I'm always going to say bigger. So I'm probably not always the greatest person to ask. But these are some of the tensions, right? Especially if you're working in contexts where data is expensive to collect, right? So you want to make the best use of your data, which means you really want simpler models. And goal three is you want computational efficiency, right? So You can build the latest, greatest model. But if you're in the research arena or if you're in the exploration arena, you want to be able to try lots of models relatively quickly, right? And exclude the ones that don't work. And if every model, when I was a graduate student, and this will date me a little bit, it would take me a week to run a model, right? Very complicated models, had to be complicated. Okay, so literally I would set it running for a week. And this was back when, you didn't have a computer you could take with you. So I had to basically like commandeer one of the department computers and it would just run for a week to give me an answer. Now, if you need to do that, great, but it's not very efficient, right? And what you're trying to do is try lots of different modeling techniques. So you want them to be relatively fast so you can easily exclude the things that don't work and focus on the stuff that does. Okay, so here you go. Okay, you have these three things. I'm not going to go into the comment underneath there because it's more for statisticians, but the point is that you want your models to be complicated enough to capture the underlying mechanisms. That's great. But simple enough that you don't run out of data and that you can still do good inference and good estimation, right? If you don't have enough data, what happens is you can fit a model and it might do really well. And then you go out and collect more data and it doesn't do well. And then you go and collect more data and it says, oh, this model is actually better. And you're like, what? Like I'm trying to answer a scientific question, a scientific hypothesis. And every time I go out and get more data, the answer changes. That's not good. That's not good, right? So that forces you to simpler models. Okay. You'll notice in the AI space, especially with a lot of the presentations that we listen to, there's a lot of data, right? So, you can overwhelm the model with a lot of data. And in that case, yes, you're more likely to get stability in the model because you have a ton of data, but you don't always have that luxury. Okay. Do I want to talk through this? Yes, I do. Okay. Hang with me. Okay. I know this is an equation. It's not everybody's equation friendly, but I will talk you through this. Trust me. Okay. So you have data and you have a certain number of variables. We call data size N, we call number of variables P. All right. When we have lots of possible variables, right? And not a lot of samples. You'll say, okay, I want to fit a model. I want to know what variables are important. But I have more variables than number of samples. This is tough for statisticians. This is tough for statistical modelers because all of the theory that we built up over many decades for modeling assumes that P is smaller than N. Right? And if P is smaller than N, great. All the standard statistical methods work. Okay, so what do you do if P is bigger than N? Okay. You try to do variable selection, right? Pick the ones that matter, then do the modeling. Or if you're really lucky, you can do variable selection and modeling all at the same time, right? So there are methods that will take in more variables than samples and do selection, okay? And one way we do that is we call it shrinkage. We shrink the coefficients for variables and some of them will drop out and become zero, okay? So for probably a decade at least, this is what everybody in statistics talked about because we got flooded with data sets that had more variables than observations. And we all went, what are we supposed to do? All our usual statistical tools don't work very well. And so the options were try statistical models with shrinkage. So does some variable selection. Great. So your actual P that you're using in the modeling is smaller than N, right? You're doing variable selection. You take advantage of correlations between the variables, right? So that, yeah, okay, I have P variables, but many of them are very highly related to each other. This is where things like principal components analysis come from, right? You're trying to find predictors that combine your original variables so you have a smaller number, okay? That's basically the approach. Or you can do machine learning, right? Of all the machine learning techniques, a lot of them have good statistical backing. And then you just have to figure out how to interpret them, right? The nice thing about statistical models is they're relatively interpretable. So if you're a scientist, it's very friendly. It's like, ooh, I fit my model, I get the coefficients, I see which ones are big and important. Those are the variables that matter, right? Once you move into the machine learning, bigger AI space, it just gets more complicated, right? Okay. So this was one of the things that statisticians did was shrinkage. Okay, and we felt very happy with ourselves for doing this. So we published a lot of papers in this area. There's lots of debates over what's the best way to pick variables. It's great. Okay. Let me skip that one. Okay. So, okay. Neural network. I was really happy this morning. David talked a little bit about neural networks and what they are, because can't assume everybody knows what these things are. So as a recap, right? Neural networks, they came out of the way the brain works, the way your neurons are all connected with each other, right? So the idea was, we're all smart, brains work great. How is our brain structured? Well, your brain has neurons in it, and they're all connected to one another, right? They're sharing information with each other, and they're probably processing some of that information before they pass it on to another neuron, right? So the idea was, okay, we'll set up this model that has these neurons, and data comes in on the input layer, and then they all share information with each other, and they do some transformation of the data, and they pass it on to the next layer, and the next layer goes, oh, that's super interesting. They do the processing, they do some other transformation, they pass it on to the next layer. Eventually, you get the output layer, right? So it's kind of like the way your brain works. You hear somebody talking to you, your brain processes it, evokes all kinds of memories, all kinds of associations, and then eventually you respond, right? Okay, so this is how neural networks work. Now, you can relate a deep learner or a neural network back to linear regression, right? So we're all kind of familiar with linear regression, right? It's, you have an output that you want to model, you have input variables, right? So what do? You take your input variables, you put them into a linear model, you have coefficients that weight the different variables depending how important they are to the outcome. You get a fairly simple model, linear model. Okay. You can think of each node in a deep learner as its own little linear regression, right? It's taking in all the variables, right? It's doing some combination of them. It's estimating what the coefficient should be, right? It's putting weights on the variables. Then it's doing some kind of transformation on the output, like same way that you go from a linear regression model to a logistic regression, right? You have a linkage function. It's the same kind of thing. You do some transformation, and then you pass on the output of that linear regression to the next layer, right? And the next layer does the same thing. And then the next layer does the same thing. So the more layers you have, the more complicated it gets, the more transformations you're doing on top of transformations on top of transformations. And that's why it makes it really complicated and difficult sometimes to interpret what the outcome is. The upside is the model is super flexible, right? And can model lots of complicated responses, right? That's the plus, right? So the plus is you get flexibility, and you get the ability to model stuff that you wouldn't be able to with the standard linear regression. The downside is you lose interpretability, right? And usually you need a lot more data, okay? So nothing's free, okay? So when the whole deep learning wave happened and everybody went, oh yeah, neural networks, right? Gosh, yeah, I used those a while ago. Okay, they're coming back. What is this? What is this deep learning? I love the language, right? The language around AI. I mean, I got to hand it to computer scientists. They have the greatest language. The things they call stuff, I'm just like, oh, where did you get that? I mean, statistics, we do the same thing, right? What do we talk about? 95% confidence. It's confident. We're confident. I mean, it's great, right? The choice of language just sets us up to think this is so fantastic, right? It's like, okay, it's deep learning. Ooh, everybody goes, ooh. All right. To the statistical world, the success of that was a little bit of a surprise, right? Okay, why? Well, mainly for 2 points, okay? So So first one, which I'm not going to cover because it's a whole nother talk, but I wanted to mention it. First one was simple gradient methods. For those of you who do optimization and are familiar with gradient descent things, okay, here's a simple analogy, right? You want to find the lowest point in a surface. Great. So if it's a simple convex function, you can stand anywhere, right? So imagine a field with like a big gully in the center. You can stand anywhere, roll a ball. It's going to go right down to the minimum. And you're like, great, I'm done, right? That's gradient descent. If you have a very complicated field, lots of hills and valleys, doesn't always work as well, right? You probably end up in a valley, but it may not be the deepest one, right? And there's no way to get out. Right? You just rolled the ball, it's stuck down there. You're like, oh, okay, now I got to walk down, pick it up, bring it back up to another hill and try again, right? So we knew theoretically that gradient methods didn't give you the global optimum, but somehow deep learners use gradient methods, right? To find the weights and estimate all the parameters. And we're just like, that shouldn't work, but it works. Okay. All right. So that's a whole nother talk. The second one that I will talk about is that despite giving near perfect fit to training data without any obvious explicit ways to control complexity, you get really good prediction. Okay, that's the one that statisticians as a group just went, what? Like that shouldn't be possible, right? If you go back to the goals of statistical modeling, right? It was make the model as complex as you need to, but not too complex, right? And so we're always concerned about too many parameters in the model, over parameterizing, right? If you expect the model to estimate too many things, you run out of data, right? How many times have you gone to a statistician and then they're like, you don't have enough degrees of freedom. You don't have enough data to estimate all those parameters. So you're going to have to get rid of something, right? Neural networks don't work that way, right? There are some models that have billions with a B, billions of parameters. We're all like, how can you possibly estimate all of those, right? It makes sense if you have a gazillion data points, but it's still like, okay, you have a model that's so enormous. If you fit it to training data, it's going to overfit. It's going to overfit. And then you should not have really good generalizability. Right? That's what we always talk about, the overfitting problem, right? What do we mean by overfitting? That means you fit a model, could be an AI model, doesn't matter, any kind of model. You fit it to your data, it does great, performs really well. You're super excited. You're running down the hallway to your advisor's office saying, oh man, I got to write my manuscript and submit it to science. This is so great. And then your advisor says, well, why don't you try it on this other piece of data, right? That's the same, supposed to be from the same area. Maybe it's a different field, maybe it's a different year, whatever. You go and try it and it bombs. Okay, because your model was so complex that you captured not only what's generating the data, right? The thing you're interested in, but you also modeled all the noise. That's probably specific to that field or that year or whatever is represented in your training data. So when you try to go and use it in a new context, it crashes, right? Somehow neural networks escaped that, right? And that was the part that everybody went, wait. Like, how is that possible, right? From a statistical standpoint. So a bunch of statisticians decided, let's try to figure this out. Right? Let's try to figure out how neural networks are so successful at predicting, right? Even though they seem to be overfitting on the training data. Like this seems like this conflict. This doesn't seem to make sense. How can you have both of those, right? Because we're so trained in the statistical goals of modeling that it was just like, I can't figure that out, right? Okay, so how do we do this? All right, so I'm going to walk through these. I know that these are complicated, but I'm going to walk through it because I think it's important. The concepts are important. Okay. So if you want to do linear regression, right? And you have more variables than data points. Okay, what's the goal of your modeling, right? Usually what you're trying to do is find the values of the parameters. This is what a neural network does, deep learner, any kind of deep learner. Find the weights, find the parameters in the model, find those values that minimize your error. Really simple, right? So you're trying to find the parameters, which usually statisticians denote with theta or mu, all those Greek letters that you're just like, why Greek letters? Anyways, mu, sigma, all those things, right? You're trying to find the values for those that when you use them in your model, you minimize your error, minimize your loss, right? However you define error, right? It could be squared error, it could be the absolute value of error, it can be your F1 score. I mean, it can be however you want to measure it, right? But you're trying to get the best by how you define it. All right. Since P is bigger than N, we can't do that, right? We can't run a regression model and estimate all the parameters because we don't have enough data, right? You run out of data. Okay. So we're like, okay, well, then a statistician would go, all right, you need to control your complexity. Your model's too big. You need to make it smaller because you don't have enough data. Okay, great. What a deep learner does is says, don't care. Doesn't matter. I am going to interpolate. Right? This is what all deep learners try to do. They try to interpolate the training data, basically go through every point. So if you're looking at, like an X by Y plot, if you've ever been in a basic stats class and they show your X and Y axes and they show the data and they draw a line through the data and they say, okay, regression is like the best fit line. Everybody goes, okay, I like that. A deep learner basically goes, I'm going to draw a line through every single point. Right? I'm going to do a scribble. Okay, great. So you did a scribble. All right. And then you get a different solution, right? You do get values for all your parameters. There's really no concept of like the best fit line, right? You're just drawing through all the points. Okay, fine. So why does this work? Why does that still work? Okay, so these are theories. So this is a hypothesis. What I'm sharing with you is not the truth, right? This is work that's happening right now in the statistical world, right? For trying to explain how deep learners work, right? Okay, so the idea was, suppose you have your data. It's super complicated. And because it's complicated and has lots of parameters, it's living in this very high dimensional space. Humans do not do this well, right? We work in maybe 4 dimensions, right? We've got the 3 dimensions for space, 1 for time. That's about it, right? Okay. So just imagine that your data is in a very high dimensional space. Like the example that I've given before is you have data in 3 dimensions, right? X, Y, Z. Somebody hands you a cardboard box and it has your data in it. Great. Got a nice 3-dimensional cloud. And they tell you, okay, I want you to take a piece of paper and try to get the piece of paper to fit your data, right? The paper itself is 2-dimensional. It's a lower dimensional surface. Your data is 3 dimensions, right? It sits in a box, right? So somebody gives you a box, it has data in it, and they say, here's a piece of paper, find the piece of paper, move the piece of paper around in your box until you get it to the point where you think it fits your data best. Okay, now, notice that when you're working in 3 dimensions and you have a piece of paper that's 2 dimensions, there are many, 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 many ways you can fit that piece of paper into the box, right? There's a ton of ways, right? You could, every time you move the paper, you get a different model. You can keep moving okay, if we take our data and it's in a very, very high dimensional space, we have a ton of flexibility in terms of our model, right? Imagine a piece of paper in 4-dimensional space, right? You could, every time you add a dimension to the space, you can fit lots and lots and lots of models, okay? So imagine your data is in a box, it's 3-dimensional, you're given a piece of paper, you're trying to find the best model, right? Now, the idea behind this tractability thing is, yes, you're working in 3 dimensions, okay? So your model space is very big relative to 2, okay? I'm working in 2 and 3, okay? I'm not working in 2 and like 3,000 because I can't picture 3,000 dimensions. Okay, so the idea is that if you can find a way to put your piece of paper in the box so that it captures most of your data, right? Nice and smooth. It gets close to most of the data points. Okay, then great. What you've essentially done is you found a lower dimensional subspace that explains most of your data, right? Great. That's what you really want, right? You want the piece of paper to put it in a way explains most of the variability in the data, right? Okay, so this is the concept behind why deep learners work from a statistical standpoint. The idea is that there's a low number of dimensions that actually capture most of the variability in the data. Now, when I say low, in my example, my low is 2, okay? Deep learners work in millions and billions of dimensions, right? So low is always relative, right? But the idea is that not all of those dimensions matter. Not all the data matters, right? You collect all this data, not every variable you collect actually matters, right? If you can find a lower dimensional subspace, a lower number of variables that explain most of the variability in your data, fantastic. Okay, then you ask, how do you get perfect interpolation, right? I mean, unless I'm an origami wizard, I can't take my piece of paper and get it to go through every single data point. Like, not going to happen, right? Okay, the idea is that because a deep learner is working in such a high dimensional space, right, has a ton of flexibility, it can essentially take your piece of paper, right, and it can add little hairs to it. Right? So think of like a buzz cut. Right? Think of a buzz cut, right? Person's head is like the surface of the paper. You have all these little hairs. They can reach out and interpolate and grab every single data point, right? So you've got something low dimensional piece that's like your piece of paper, and then you have a high dimensional piece that's all these little hairs, right? And I'll show you a picture in a second. All these little hairs that give you perfect interpolation. Okay, the reason that kind of model, it will work on your training data because it will interpolate everything, okay? As soon as you go to new data, okay, those little hairs aren't helping you anymore. They're basically creating noise, but they don't capture a lot of the variability. It's the piece of paper underneath it that matters. So as long as your piece of paper captures most of the variability, as soon as you go to the predictive setting, you're still going to do pretty well, right? It all hinges on finding that lower dimensional subspace. And that's what deep learners and AI methods, they do that really well, really, really well. So the way that the deep learners work is, instead of explicitly doing variable selection the way statisticians do, we do it very explicitly. We build in the variable selection into the loss function, right? So whatever function that we're trying to optimize, we put it in there explicitly. Deep learners do it implicitly, right? They're searching around the space all the time, and they're throwing out variables that don't matter, right? And they're combining ones that are correlated, right? And they're doing lots of things under the hood, right, implicitly, to control the dimension of the solution, right? Even in high dimensional spaces, right? So it's just an implicit versus explicit, right? So here are examples of where you can overfit from the standpoint of a statistician. You can overfit and still do well or bomb terribly, right? There's different types of overfitting, okay? So the picture farthest on the left is benign overfitting, right? What happens is you see the curve, right? There's a dashed line there, the curve, that's like your piece of paper. It's explaining most of the variability, right? Fits everything really well. Then you have this green squiggly line that it's trying to follow the piece of paper as much as possible and just has little peaks, right? To make sure that it's interpolating, right? So you get the crew cut type of model, right? Where you have a underlying surface and you have all these little ups and downs, okay? That type of model can interpolate, fit all your training data, and do well predictively, right? It will actually do well in a predictive setting because those little bumps, they don't really add much to the model, right? The real power of the model is in the dashed line that's there. Okay. You can have in the middle, you can have tempered overfitting. That means it's not great. And there are methods that will do tempered overfitting. Kernel methods will do it. It's not great. It's not a disaster, but it's not as good as a deep learner because kernel methods are not as flexible, right? It's just a question of how big of a model space are you searching, right? The picture on the right is terrible. It's catastrophic. That's what polynomials do, right? Polynomials have curves in them, and it's very difficult for polynomials to wiggle unless the power of the degree is very high, right? So when you try to fit a polynomial, you tend to get these big swings and terrible overfitting, right? So the different types of overfitting, some of them are not bad, right? Some of them are terrible. So most of the AI methods that we're using are in the left hand. Why? Because they're very flexible. They take advantage of very, very high dimensional spaces. They're able to find lower dimensional subspaces where they put most of their effort. And then they add a little bit, it's kind of like icing on the cake to get really good, basically interpolated fit, like training error of 0, right? And still do well predictively. Okay. What's the downside, right? There's no free lunch. Okay, so you fit this huge model. It's great. It does perfect with interpolation. And then you go to predict and it still does well. And you're super happy and you still want to run off to science. The problem becomes that the model is not identifiable. What do we mean by that? I can fit the model. Okay, that's not identifiability. I can fit the model. I can tell you what the parameter values are. The problem is that because it's in such a high dimensional space, so flexible model space, I can bet you that there's probably 100 other models, deep learners out there that will do just as good. That's the problem, right? So from a scientific standpoint, right, I want to know what variables are important, right? Because I want to know what's in the black box, right? So I want to fit the model and then I want to go, oh man, what makes that thing work, right? I want to know something about weather. I want to know something about climate change. I want to know something about soil health and microbiome, all these things. I want to take the model apart and be able to explain how it works. Like, what are the important things that I'm putting into the model? If the model's not identifiable, that means you might have 100 models that all do the same, just as well on your data and just as well predictively. Then you're in a pickle. If you're just predicting, great. Right? You're good, right? But if your goal is to do inference or estimation or answer hypotheses or try to understand the underlying process, you might have another problem, right? So some of them, there's been conversations earlier in this conference about things like, can you add constraints, right? Could you add constraints, right? We've seen deep learners where you add what you know about the underlying processes. You add a physics constraint, you add a mathematical model, a differential equation that explains the underlying science. And you basically say, look, I'm happy for a deep learner to go and solve this problem and give me a good predictor, but it has to make sense scientifically, right? Which means it has to meet certain physical constraints. And so I can put those in the model. Okay, so that's one way to make your model identifiable, right? You add constraints to the model so that, yeah, okay, I might without the constraints have 100 models that can solve this problem. They all do well predictively, right? But you want to find the ones that scientifically make sense, right? And so you can add constraints, and that's where all of your scientific knowledge and all the stuff that you get when you're sitting in class and trying not to sleep and studying for your tests, right? That's where all that knowledge comes in, right? Is you can incorporate in the model. So you put constraints in, right? That also helps you with, yes, you need lots of high quality data to do the deep learning because it's very flexible, right? And it will go after anything, even garbage, right? The garbage in, garbage out problem still exists. Sorry, we didn't get away from that. But adding constraints will help you, right? So I put some examples up here because I do a lot of work in genetics. And I talk a lot with people who want to link their traits, like phenomics traits, back to genetics. So they're trying to inform animal breeding or plant breeding. And they ask me things like, okay, what I'm used to doing genomic selection. Most of those are statistical models. Why would I do AI? Right? Why would I even do that? What if it can't explain, right? At least the models I'm using, I can explain. And I'll say, that's true, right? What you're saying is correct. But there's probably contexts where your model is not doing well, right? You're not getting good results. It's a more complicated genetic situation, or the link between genome to phenome is more complicated. You need a more complicated model, right? So try a deep learner, right? Do an AI approach. If you haven't already done a machine learning, try an AI approach. And you can put constraints, genetic constraints into the deep learner. And that will help you with explainability, right? That will help you with the identifiability problem, right? Where you don't try to present your results to the plant breeder and the plant breeder says, I don't know what the heck you're talking about. And this doesn't make any sense to me. This isn't helping me because it doesn't have any genomic information, right? By putting constraints on there, you can help explain it, right? So use the knowledge that you have, right, to make your models more tractable. Okay. Challenges. Oh, okay. Where do we want to start? One of the biggest challenges that we have in the AI space is training enough people to do AI, right? I mean, and really understand what they're doing. Right? So, and it's the same in statistics, right? I can show people how to run statistical models. I can explain it to them. I can describe it, but they need to have a certain amount of background knowledge so that they can understand what they're doing, right? So when they use a model, they can understand how it works, or they can explain why it doesn't work, and they can come up with other scenarios, right? Other approaches. So we have a huge training need. And expertise needs. So, events like this help, right? But like if you're a student, encourage your friends and family come learn about AI because there's going to be lots of opportunities and we don't have enough people is the bottom line. Okay. We have a trust problem. We still have a trust problem with AI. This happens, if you think back about other scientific technological changes in the last 10, 20 years, right? What happens? Something comes out, super exciting. Everybody gets excited. Everybody jumps on AI. Everybody has to put deep learning in their title of their abstract or their paper. They get really excited. The whole community oversells it, which we always do. And then there's the realization that, oh my gosh, like AI isn't going to solve everything for us. So disappointed, right? And then you get the crash, right? You get loss of trust, right? People start going, oh yeah, AI, yeah, that was big like 5 years ago. Everybody promised everything. So we have a trust problem, and particularly we have a trust problem because most people don't know what AI is. It sounds scary. Right? I mean, if you're my age, you think Skynet has become active. This is bad, right? This is bad, right? It brings up connotations that are a little bit, so there's a lot of hesitancy, right? And there's the concern of the oversell, right? So we as a community have to work really hard to explain what we're doing, communicate, right? Not overpromise, right? Be realistic about what we can achieve, what we can't achieve. That doesn't mean, you shouldn't shoot for the stars. Like I love it when students want to do something amazing and they come up with their dissertation project and it's like, this could take you 30 years, but I love your excitement, right? I love the fact that you want to try to do this. That's great. But, let's try to make it feasible, right? Let's try to break it down so you can do something that you can accomplish. And then you can, yay, great, you can graduate and go on to your job. And, it's a win-win, right? So trying to be realistic about what's achievable. We also have an equity fairness issue. So yes, I agree with everyone's earlier statements about how AI is a great equalizer, right? It will make things fair. And that's true, assuming you can get AI and the promise of AI in the hands of everyone. Right? So if it's a tool, right, or it's an irrigation scheduler or a planting algorithm or something like that, and you can make it widely available, great, right? It will be an equalizer, right? At the same time, right, we've heard talks about, foundation models and that they have a lot of promise, and they do. They absolutely do. Okay, but who has the foundation models? It's not you or me, everybody in this room, right? Those things are enormous. They take an incredible amount of resources and time and knowledge to build and develop, right? And so we have like a yes and no thing going on. Like, yeah, AI could be a great equalizer. And I think if we push hard to put it in the hands of everyone, then absolutely, right? It can benefit everyone. However, AI models to train, and this was said by some of the keynote speakers, right? To train those models takes an incredible amount of resources, way more than anything anybody in this room would have access to, right? So we need to be careful as a society, as a community, to make sure that the things that we do are actually accessible to everyone, right? Okay. So these are some of the challenges that we have, just like in any other discipline. There's nothing new, right? It's just because AI has so much promise and can be used in so many different contexts. It can do a lot of good, right? But it can also exacerbate a lot of the inequities that we already have. That's just the way it is. Okay. Before I quit, or before I take lots of questions, I did want to mention this conference. So Seth mentioned it. It's focused on plant phenotyping. It's going to be in Lincoln in October. So you guys are all close. Nebraska isn't that far away. Still the Midwest. Nice and comfortable. We will have, and I think Sumik mentioned this during the panel yesterday, there'll be a pre-day AI, machine learning, cyber agriculture, machine learning and cyber ag systems conference that's going to happen the day before, right? Same location. So if you're working in the AI space, you're doing imaging, like I saw a lot of posters doing imaging, doing trait capture. We all welcome you to Lincoln. I'll keep this in my slides. Okay, now I can take questions. Anything you have to ask me. Thank you. Thank you very much.
So thank you very much for this inspirational talk, Dr. Clarke. So I have just a question. Right now we are using a bunch of different data sources as a predictors to predict our trait of interest. So let's assume that our trait is grain yield of corn to predict, and we are using genomic data and the image data and weather data, and it all can be a potential kernel for us to use. I'm just wondering, because when we look at the last 30 years technology, as you mentioned, we are using the genomic data to predict, but recently drone entered our area and then we are getting the data from it. So, and then I'm just wondering their effect. So when we use all of these three data source as a predictors, we are just using them as they are, we are creating the relationship matrix. Should we use any weighting factor for each of these factors, just because some of them is very old and some of them is very new? And yeah, so this is my question. Should we use a weighting factor for each of these matrices?
Yeah, that's a good question. Okay, so the question was, okay, you have lots and lots of potential predictors. This is what we call the multi-type data problem, right? Instead of all of your variables being the same structure, essentially, you have video and you want to include that with genomics, and then you want to throw in your imaging, and then you want to throw in the weather, and you've got all this data. How do you decide what to put in the model and how to put it in the model? The reason, one of the reasons this is an important question, important consideration, is that no matter what modeling approach you take, a deep learner, machine learner, regular statistical model, doesn't matter. Though all of those techniques will get confused if your variables are highly correlated. Right. So if you have variables that are highly dependent on each other, your model can't tell them apart, and it gets really confused. And then you don't get good estimation, you don't get good inference. So I think part of it is trying to pre-process your data so that you can make your input variables as independent as possible, right? Independent information sources. We used to do this with like, make your matrix orthogonal or do standardization of your variables, right? So what you're trying to do is clarify the information sources that are coming from the different variables so that your model can then more easily separate them from each other, right? And tell you which ones are important. You're right, data quality is definitely an issue, right? Some data is more reliable than others, right? So what we usually do is you can weight your variables, right? You can weight them by the quality, right? Some data has much more variability than others, right? And so like, I can't really rely on that one as much as I can my others, right? So you can do things like inverse weighting based on the variance. That's important. I think it's less important. It may be less important in a deep learning context because the model's so flexible. If the data is bad, it hopefully will ignore it. But I can't guarantee that, right? There's no way to check that, right? If it gets led astray, well, you get what you get, right? So yeah, but yes, that's a very important question, is that helps with the garbage in, garbage out problem. Yep. Thank you. Okay.
Well, thanks for the inspirational talk. I'm not in an AI world, and I learned a lot. Just sort of philosophical question. You mentioned early on that there is a space for AI and there's something is not for AI. And I wonder if you could elaborate on that a little bit.
Yeah.
And most of the talks that I've seen today and yesterday are about using data to predict something based on the data. Is AI good for creation of new knowledge? So I just want you to.
Yeah. Okay. So I'll split those into two questions. One is, I made a comment that AI isn't for everything. And so where are things where you might not want to use AI at this point? And the second one was for predictive purposes, right? So does AI predict well, or can it be used? Was that the question? Can AI be used for creating new knowledge? Great. Okay. Second one. Okay. So the first one is, I made a comment about how AI isn't for everything. And I still believe that, because there are certainly situations where something as complicated as an AI model just isn't necessary. It's just you don't need it, right? I see a lot of people who say, I really, really want to use AI, but I only have can I use AI if I have 10 observations? And I'm like, well, you can, but I mean, why? Why would you do that? You really don't have enough information to support a model that's that complicated, right? So what I usually say is start with something simpler, right? And see if it works, right? If it doesn't work, great, right? I mean, there are lots of complicated problems out there where you need something that is super flexible, right? You need something that's like an AI model. But in many contexts, right now, we don't have the data to support a super complicated AI model, right? And then you have the problem of okay, how do I explain this model, right? Okay, so there's this trade-off, right? So for simpler problems, right, where you don't have a lot of data, where interpretability is really important, then I would say, okay, AI is not the first tool that you want to grab, right? Try something else. Yes, maybe eventually the AI will be the right thing to do, but it's not a one thing fits all, right? Solution. Okay. The second one, can AI be used to generate and find new knowledge? My answer is yes, absolutely, right? So the fact that we're using AI models successfully to do quality prediction in problems that were considered intractable, right? That we couldn't even approach, right? That all existing models had failed, right? They might have failed because the data was bad. They might have failed because the model structure was wrong. Like there's lots of reasons why modeling goes wrong, right? But we've seen that AI can predict well in contexts where we couldn't do it previously. So it's capturing something that previously we were missing, right? We just didn't quite get it, right? So I think there's been a lot of recent approaches on explainable AI, right? Being able to open the black box, right? See at least what input variables are the important ones, right? And then that gets our brains going and we start thinking about like, why are these the variables that the model seems to be telling me are the important ones? Like maybe I never thought about those ones before, or maybe I was thinking about them, but not in the right way, right? There's some connection with the output that I was missing, right? So it gets all of our scientific brains kind of going because it's like, okay, there's something that I hadn't thought of before. It's doing good prediction and it's telling me these are the important inputs. Like why? Right. And then everybody who's a scientist is like, okay, now I'm super excited because now I have a problem that I didn't know the answer to. I don't know the answer. Now I got to go write a grant proposal and I got to go publish. Right. So yes, it does. Either the model itself indicates things that we didn't know were important, or it spurs us as scientists, right, to go re-examine things, right? And then we discover new knowledge. So yeah, absolutely. Absolutely.
Well, thank you, Dr. Clarke. I think we're out of time for right now. So let's give her a round of applause.
Thank you.
So I think she'll be able to stick around through the coffee break for some questions. But before we go on coffee break, Dr. Mahindra Bhandari has the awards of our posters. And I think he's got a lot of judges and other people to thank. So Dr. Bhandari is on our program planning committee.
Thank you, Seth.
Ben, do you have a drum roll queued up?
Good afternoon, everyone. So we are on the most exciting part of the conference, and I was coordinating the poster session of this conference, and we decided to do a graduate student poster competition as well. And the first prize is $500, second prize is $300, and third prize is $100. And in total, we got 57 posters, very good posters. And we had a judge panel of 12 members. If you are here, please stand up so that we can thank you all. Thank you so much. And just to give you a brief about how we did the judging of the poster. So the first component that was ranked is based on how the poster looks, like, how it is formatted, layout, and all those things. And then second was the content of the poster, brief introduction, results, how the results are presented. And then third one was the presentation skill of the presenter. With that, I'd like to announce the third
place, third winner of the poster competition. It is poster number 8, Brenna Brussels from North Carolina State University.
Yeah, we'll have them all come up and get a picture.
Yeah. Okay. Yeah. And then the second place goes to poster number 36, Aksheta Mohan from Texas A&M University.
Up second place.
Yeah, that was the second place. If the advisor is here, maybe we can invite them as well. Okay. The first place goes to poster number 54, Poya Sorabi Por from University of Arkansas. Thank you all. That was my job. And I think Anna will follow up with you all on the prizes. Thank you.
Thanks a lot, Mahindra. So if the PI or the department head is here for the second place winner, come on up. And judges, if you want to get in a photo too, that'd be fantastic. We're gonna go on coffee break, and then we're gonna come back for an exciting industry panel. That'll be the last formalized activity before ethics, and then an open discussion.
Yeah, there we go. I like it. Okay. Great. Hey, guys. Yeah, thank you. Okay. Okay. Yeah. Perfect. Yeah. Congratulations. Yeah.
Then we have new methods.
What's that? Nathan. Oh, did you? Russ, it was on. Did you find it? He's got it. If you bring it to the AV corner, when you get it, he'll cue it up for you.
Yeah, we should have said half hour. Right. Being careful. Like Xerox or just the one was worse than the rest. Yeah. We have friends. No, I'm actually not. Why don't we say hi on that? Oh, yeah. We're looking forward to the order of the slides was what John said. I'll try and do that. Yeah, yeah. So
John, Riley, me. I can get some of ours. That's where they want it. John, nice to meet you. It's okay. If you could go out and get one of those spinner boards, spin it around and tell them good talk here. Maybe. I just thought, I'm just thinking on the fly. Yeah, exactly.
Of course, there were still a few people out in the hall.
Yeah, I think so. I think cards are all sitting over in my. I think we're on.
Great. I think LinkedIn.
I think we're on LinkedIn, but there you go. John, I already got your.
All right. Actually.
Scooching? Scooch one more?
Like poured over everybody.
Okay.
Duration of it. So let's see. Should. Because we got it online first. I think we got that. Riley, grading? Yeah, and it's Nathan again. Did you have a card?
I do. It's over in my backpack.
Connect up again. Okay. All right. Me. Remember the panel, the podium adjusts, so. Yeah. All right. Well, we're about to get started with our final panel of the day. I know there might be a few folks in the hallway, but thanks for sticking around. We're really excited about this. I think this will be a good way to wrap up, especially after hearing from the farmers yesterday. I know it's been a long conference, but I wanted to kind of frame our discussion a little bit. So I've got just a few slides. See if I can, the pointer works. So this is from McKinsey Consulting, and it's a few years old, but it shows productivity growth in a variety of sectors in the US economy versus a digitization index. And that's a bit subjective, but it's mostly a measure of how much information and communication technologies these sectors use. What do we see about agriculture? Well, for those of us that are scientists and data analysts, it's an outlier, right? It's a bit ways from that regression line. We've been highly productive, had lots of productivity gains, but it's not very digitized, right? I don't think that's a surprise. What's driven our productivity? A lot of genetic improvements. That's GMOs on the crop side, genomic breeding on livestock side. But we still have, I'm optimistic. I'm a technologist, right? There's lots of room for growth there because we haven't really taken advantage of that. Now, what I do is I'm on the faculty here at A&M is a lot of technology. Precision ag is one area. If we're looking at some precision ag technologies, this comes from the USDA adoption data. We've got two competing technologies, are really complementary. Variable rate technology, which many of you may be familiar with, looking at variable rate application of any kind of input. And then auto guidance, where the tractor drives itself. I like this comparison. You've got to note the scale. They look similar. This adoption rate is 40%. This maximum one here is 80. If we recall the farmers yesterday, they all wanted an easy button. That's an easy button. This is not an easy button. So I think that's kind of a key point for discussion that they really highlighted yesterday. Finally, kind of in the investment environment for ag tech, and this comes from Ag Funder News, which is a kind of venture capitalist fund that also puts out a lot of reports on it. We see that, recently the ag tech sector's investment's not been so great. And some of this is broader economic trends. Particularly, and this is some of the downstream sectors, things like retail, e-grocery, they've really dropped off. What it does highlight, this line down at the bottom, it seems pretty insignificant, but it's showing steady growth. That's farm robotics and mechanization. So, that's still a sector where we're seeing some growth. It's slow and it lags behind some of the other ones, but really, I think there's a lot of opportunity there. We've got some big issues, right? And the farmers brought some of this up. So one, I don't think we have anybody from Mineral, which is a spinoff of, Alphabet, Google's parent company. They claim that they've got data from 10% of the world's farmland. And we had a lot of discussion about, what happens to that farm data? Whose is it? Who owns it? Who profits off of it? So people may not be aware of that, but a lot of that is satellite, but some of that is from the rovers, from input suppliers they work with, other things like that. And finally, this is from a research journal. We talked about some of the broader societal issues, and this is maybe a bit alarmist, right? Is it solving the food problem? Or I hope people in here are familiar with the trolley dilemma. You can probably Google that. It's a social experiment, to ask, the trolley's going down the tracks. It's going to run over, say, 5 people and kill them. So you can throw the switch and switch it to the branch line. It'll run over 1 person, but you've got to make that decision. So it's kind of a thought experiment that, psychologists like to do. But it's a little bit alarmist, but is it really asking, are we solving some of these broader societal problems, things with hunger and nutrition, or are we just, building more technology for someone to buy? So a lot to think about. One may be employment, and maybe my job's redundant. ChatGPT might be able to replace me. So I thought I'd propose what I was sending to our panel here, and it didn't do a bad job. We've talked a little bit, maybe it's not so specific, right? But it did a pretty good job at suggesting some questions. So with that, I'm gonna stop talking and turn it over to the panel. I'll briefly introduce them. I also want to acknowledge Mahindra Bandari from our Corpus Christi Center. He really set up the panel and contacted a lot of our great industry participants here. So I'll go from left to right there. And our first speaker will be John Gatula. He's with SAS. He describes himself as a forester, a farmer, and a girl dad who has a data and AI problem. He's the principal AI advisor at the SAS Institute. He's also on the affiliate graduate faculty at North Carolina A&T. He has degrees in horticulture and plant pathology and has been in industry for 10 years. So he's certainly has an ag background, and I guess you could say you somewhat stumbled into the AI field, right? So it's learning AI and biostatistics on the job. And he's been leading collaborations in North Carolina's multi-million-dollar agricultural analytics platform initiative. And he's going to tell us a little bit about that today. So with that, I'll turn it over to you, John.
All right. It's a great pleasure to be here and an honor to be on this panel here today. I'm going to introduce or reintroduce SAS Institute to all of you and tell you a little bit about what we do. So technology is changing extremely fast. AI, digitization are all enablers of new communication. And the path is not necessarily linear. Think about all of the new technologies that we're getting today. Drones are now spraying chemicals on fields, tractors are driving themselves, farmers are using augmented reality for their purchasing decisions, medical diagnoses are being made through AI or with the help of AI. GPU processors process enormous amounts of information today. And this technology is increasing at an exponential pace, increasing knowledge at an exponential pace in a way that at times seems downright dizzying, leading to a proliferation of information. And this proliferation of information is beyond human capacity to be able to process, which has implications both at the people and the organizational level. Yet, for those who are able to use AI to help process this information, it presents an incredible advantage for us to be able to use and make the most of our data. And that's why I was so interested to join SAS Institute about 5 years ago, because I see no greater capability than for SAS Institute to be able to actually effectuate these things in agriculture. At SAS, we're so much more than a coding language. We are the founder and future of data and AI and analytics, and we are a cloud native AI company. How do we do this? We do this by working in the analytics lifecycle, which manages information from data to deployment, including modeling, with no code functionality throughout this process. We do this through productivity, performance, and trust, the three pillars of our enabling capabilities here. With respect to productivity, it's being able to automate creation of models, tracking the data lineage of models, and in model deployment. We integrate not only different data sources, but different coding languages, allowing people of different skill sets and user types to collaborate effectively together. When it comes to performance, it's all about speed, scalability, and maximizing cost. 80% of IT managers say that they overshoot their cloud budget, and a third-party research firm has found that SaaS Viya is 30 times faster on the cloud than other commercial data and AI platforms and open source, which results in 86% lower operating costs on the cloud. So SaaS, the cloud is cheaper on SaaS. We heard a lot about trust in the farmer panel yesterday, and that's absolutely at the core and the heart of what we do, with 100% of life science companies using us and several thousand agricultural researchers and government using us. How do we bring trust to these AI models? We make sure that they're explainable or interpretable, that they are transparent, that you can track from the decision back through the model to the originating data sources, and that they are fair, that there's automated bias detection and ability to identify personally identifiable information and things like that. We do it through integrating all of these different features in our AI process and no code integration of various statistical mechanisms to detect these things that are available right out of the box. So a brief word about what have I been up to lately. Lately, I've been working with land grant institutions, including North Carolina A&T State, to help fulfill their missions of research, teaching, and extension. And so with respect to teaching, you know, we're not talking about training students to be better coders, right? Because ChatGPT can generate pretty good code for us. We're talking about working with students to deal in the concepts of AI and statistics so that they can ask better questions and become data science leaders in their own right when they go into industry. Applied research, repatriating data from hard drives from researchers and turning those into actionable recommendation systems for growers in weeks, not months or years. And then for extension, being able to track extension progress and effectiveness, focusing on outcomes instead of outputs. And so by focusing on productivity, performance, and trust, we are working with land grant institutions to further their mission and to help create AI collaboration systems that are useful for everyone. So with that, thank you for your attention, and I look forward to having a lively discussion here today.
All right, our next speaker is Brady Klein. Pulling up my notes. Mr. Klein has over 25 years of applying software and data science to address challenges with federal and international governments in both civilian, intelligence, and disaster response applications. The past 12 years, he's focused on ensuring spatial data is enabled for building actionable intelligence and course of action analysis. Mr. Klein currently leads Esri's business development for advanced analytics, which supports across all sectors. Prior to joining Esri, he was part of the leadership team of an AI startup, leading global sales, business development, and marketing. His focus broadened to include commercial and financial industries, and adapting artificial intelligence tools that had previously only been available within the intelligence sector. So with that, I'll turn it over to Brady. Yeah.
I think next slide.
You should be good.
Yeah, that's me. Okay, cool. So I'll talk a little bit about me. I'm gonna raise this up a little bit. I'm a little bit taller than most. Let me follow on a little bit more about me, and then I'll get into Esri. You may be saying, why is a defense and intelligence professional up here on stage talking to a bunch of agriculture-focused data scientists? So I'll go with my past career. With the startup that I had left to come to Esri, I was working mostly for two of the organizations that I think the world kind of thinks is evil, national government and the hedge funds. So the question came up. I walked into a meeting at a hedge fund. It's a very large, data-focused, I guess quant-focused hedge fund. And my title on my card actually at the time had said Director of Intelligence. And the analyst came to me and looked at me and said, why the hell are you here? And I said, oh, I thought we were looking for things that we want to identify things before other people identify things so that we can make a decision so that we can act on it. If that's not what you guys do, I'm fine to leave. We're good. And then we sat down and talked for about 5 hours about how we can bring spatial intelligence into the hedge fund world. And a lot of it actually was around agriculture and predicting crop growth, crop yield. One, I wanted to look at, I'll be honest, I was looking at less than favorable nations that were putting out numbers. And sometimes you can't trust a national government to give you its economic output. So you have to actually create a proxy for that output. We were developing that proxy through remote sensing. So when I say remote sensing, I'm not just limiting myself to satellite-based collections. I actually had people on the ground in unfavorable countries that would collect actually crop information from various fields, because I need to validate all of those things and all of those findings. So a little bit that gives you a kind of a feel for some of the data science work and the AI things that I was doing. I also like to say I was doing AI well before we called it AI. We had said course of action analysis. Like I said, I usually talk about things like warheads on foreheads and shortening kill chains. So I get to talk about much more exciting conversations here. But it really was about lessening the cognitive burden to officers in the field, specifically land officers for militaries across the globe. So not just US, I was actually focused on NATO and international missions, and actually a lot with drug counter narcotics. So got a lot of time in South America. That's me. So a little bit unique, a little bit different. Who do I represent? I represent Esri, which may be the biggest software company you never heard of, or you know exactly who they are. It's kind of like these two camps that I get to work against. Esri is a private organization. You know, you can read it as well as I can that roughly 90,000 different organizations globally that use our software, ArcGIS, to solve their spatial problems. I sat through a few of the sessions, and some of those sessions were using our software, some weren't. I think the next thing that I get to say is we're not an AI company. We're a GIS. But you can't say that today, because there isn't a company, there's not a software company out there today that doesn't have to use artificial intelligence in some way, shape, or form. It's really in the operationalization of artificial intelligence that makes it valuable, right? We need to be able to use the outputs from artificial intelligence. So we said my previous startup, a lot of computer vision, a lot of identifying and classifying pixels from remote sensing. Great, what's that doing? That's just creating new data. So I'm using artificial intelligence. That didn't actually give me the answer. That just told me, hey, there's likely cars in this parking lot. It's what does that mean, right? So what's the context about that? And we didn't really start getting into contextual artificial intelligence until we really kind of cracked open with ChatGPT, almost 2 years ago now, on large language models, and really generative AI. So creating those contexts around those answers. So that's who I am. That's a little bit about who Esri is, kind of why we're here specifically in the ag space is we have USDA as a very large and important customer to us. So why does that matter to you? Well, as you can kind of read through, it's really about automating and streamlining those workflows for users, whoever those users happen to be, whether they're government users or farmers out in the field collecting data. It's about a common platform for data and services, meaning to give you those transparent and meaningful results. So transparent and meaningful is only useful if you can share it. So it's the collaboration and the multi-use of those workflows that becomes important. At the end of the day, everything comes down to decision-making, right? Every bit of data that you've collected, every piece of analysis that you've done is so that someone else can go make that decision. So for us, it's about empowering that leader, whoever that leader happens to be that's making the decision. So a little bit about all the systems and types that we work with. It's a lot, right? You can see, again, a lot in the remote sensing side. In remote sensing, I will lump in imagery and IoT mostly into the remote sensing, because to me, remote sensing is anything that is I can collect that is more than just data. So my team and what we do, we work across all of the sectors, not just within national government, to bring power of graph analytics, big data analytics at scale. And you know, I always love when people talk about big data, because it's the first question should be, what do you mean? Like, what do you call big data? Because I can talk to the city of Albuquerque, which I have, and they were like, we have this data set. We've got 900,000 rows of data. I'm like, cool, so you're going to process it on literally your laptop and it's going to be fine. That's not big data, but for them, that was 8 years worth of collection of that data set. That is big data to them. It's the biggest data that they had. 2 days before that, I was working with 16 billion rows with 180 different fields per row. Now we're talking about big data, right? I'm talking about every cell phone ping that happened in an entire country that day. That's a lot of data. So to me, there's big data. To City of Albuquerque, they've got a different concept of big data. I'd say I'm in the geospatial world, so everything's big data, right? And we get down to the imagery or the even vector can become extremely large. So what it comes down to is building this foundational platform for the USDA. I won't bore you with going through all of these things. I feel like you can read. I really doubt that you're here and can't. So lots of different programs. I think, are we making the slides available to everyone? Yeah. I mean, because we can. Nothing here is special. It's not my other side of my job. So really, I want to talk a little bit more about the helping the decision making, because that to me, that's my driving, that's my North Star. That is what I drive towards, is helping decision making. So it's for first responders and analysts and policymakers and executives and public affairs and engineering and what's the last one? Economists and scientists. So I also have a very deep love and hatred for economy and econometric modeling and really just understanding the data and data science. But it's supporting all of these really to inform those stakeholders. Every bit of this, the engagement, the detections, the suitability analyses, it really goes to inform those stakeholders. And for USDA, the stakeholders, you guys are all the stakeholders. So we're here to help inform you and give you those data sets and make these fundamental and foundational data sets that are available to you. I hate that I'm going to have to walk you through this, so I'm just going to put everything all up at one time because I don't like moving slides. Lazy, mostly. How do we do this? And this is really this is the backbone of what my team is here to do and support across all of Esri. And we've been doing it with USDA I've been with Esri for the last 5 years. I've been doing it literally every one of those last 5 years has been supporting USDA as a customer. it's every lens of that analytical workflow. You always start at the data collection side, then you have to go into the data engineering and ultimately prepping your data for analytics, right? Most data is not analytics ready as you get it. You have to clean, you have to modify, transform, and then load. It's the big data analytics, whether that's geospatial analytics at scale or big data analytics. We also help bridge that gap so that we meet the data scientists to where their tools are, as opposed to forcing them into a platform where I'll just go ahead and say, if I were to try to push a data scientist into ArcGIS Pro, they're mostly going to yell at me, and then they're going to say, that's not how I do work, and I'm not going to use that. So we have Pythonic libraries that allow you to bring in those spatial algorithms and those very, Esri focused and Esri owned proprietary algorithms are in there as well, so that you can use all the best tools of the open source, but you can also bring those tools to a non-spatial user within the data science community, empowering spatial to that data science community. So we bring into that to do those things of those advanced analytics of, say, site suitability. Again, we're back at network analysis or graph analysis. I know my colleagues yesterday talked a little bit about graph analytics. I can go for probably several more hours on graph and where it's important and how to use it and where to use it and why do you use it. Ultimately, getting back to the thing that I started with, which is it's all about the context. I don't care about your point on a map. I care about what that point on the map means to all the other points on the map and the things that aren't on the map. How do those points relate to things that I can't necessarily say are spatial? I have a document. It tells me what a crop forecast is. That inherently means that document isn't necessarily spatial, but it's filled with spatial information that I need to go enrich some point on the earth. So GeoAI is our geospatial artificial intelligence, and what we describe that, I will tell you that I look at that as the science of it. It's not special algorithms that we have gone and created. It is mostly sourced from the open source, but it's allowing those tools for the science side of this community to build their answers. Because here's the commercial company guy saying, if I go build you something that's generic, if you're another commercial organization, guess what? You don't want anybody else to have it. Again, back to my evil people over at the hedge fund. If they can find it, that's their signal. That's their alpha. They do not want to share alpha. They want to hold alpha. They want that competitive advantage. So if you're looking for that competitive advantage, you need to be able to build it yourself. So you need all of those tools to build the answers yourself to create that finite answer that you're looking for. I usually kind of do this foot stomp moment with visualization because I think a lot of us downplay visualization more often than not. We downplay it because it just doesn't sound valuable. It's like, oh, well, you made it pretty, so that's great. Wrong. I made it so that somebody could interpret what I was thinking so that it could be usable at that next level of decision-making. Visualization is how decision-making happens. We do the hard things as the analyst to then get it to someone else that is our boss. Sometimes they don't actually know what the job is. They are put into the position for some other reason. So I need to make a visualization that is meaningful enough that they can make a good decision from that data. Don't underplay the visualization piece. Does it look a little bit easier? It actually does look a little bit easier, but it's important. Modeling and scripting comes off into this user experience side, and it's a weird one because modeling and scripting is taking those visualizations and the data sitting behind that to drive new models and new simulations of that workflow. This is where I usually stick in I love that it's linear. Doesn't everybody wish that their workflow was linear? Because it's never linear. This is much more like we're looking at impact where it's a graph. I start at one point, I've got relationships all over the map, everywhere my data is. And sometimes I have to go back to those and start all over again and say, I actually need to go all the way back to collecting more data. Coming back to the previous presentation, the biggest challenge that I've always faced as a data scientist and for my customers has been they come up with really great ideas, super great ideas. Do you have data to help me find that? No, but could you go predict it? No. Have you seen it occur ever in existence? No. Okay, cool. So no, I can't go predict it. I'm not a magician. I'm not a soothsayer. All of those things sound really awesome, and I can make lots of important things out of data that you do have, but I got to know what your data is before I can do that. So, and then the last piece is the sharing and collaboration, and then I'll stop babbling. Again, we talked about the importance of the sharing and the collaboration. No single point of failure. You have to have that diversity of thought and leadership so that you get the inputs that are necessary to get correct decisions at the end of the chain. So I think that's the end of me. Ezra.
Right, ready? Oh, yeah. Thanks, Brady. And we've got a wide variety of sectors represented here. So we've gone with two big software companies there with SAS and Esri. Now we've got someone really from a startup, right? So Matt Donovan is our next speaker. Get him pulled up here. He is the CEO of Agriculture Intelligence and the lead product officer for AgriView, a patented award-winning cloud-based artificial intelligence platform that spun out of the University of Florida. His deep roots in cloud-based software, had 15 years of executive leadership and a successful exit in his prior venture, and he co-founded Agriculture Intelligence with Dr. Yannis Ampazidis from the University of Florida. Ag Intelligence is an agricultural science software and analytics company combining remote sensing, computer vision, and artificial intelligence to provide cloud-based precision data for specialty crops. AgriView provides proven results for tree and gap count per tree health metrics, including height, canopy area, and leaf density index, and recently rolled out a full field nutrient analysis. So this should be your slide. So come on up, Matt, and we'll turn it over to you. And if you need to lower some more,
yeah, slightly.
So in about 48 hours, I quickly learned that when you come up to one of these things, you say, howdy. Now I'm from Gainesville, Florida. No booze, please. That's usually instead of howdy in Gainesville, it's a go Gators, but well, there you go. They're everywhere. Well, I appreciate your time today. I'm excited to be on the panel and hope to really address some of the questions on where the rubber really meets the road, where the technology development that everybody here is working on and the technology development that I've been lucky enough to partner with and license through the University of Florida meets industry's needs. So I think he covered me pretty good. Been doing this for a while. I ran a software company. My primary job every time I get up in the morning is to go out and deliver a solution that makes an impact. We all want value out of anything that we buy. The growers that we're serving are no different. Doesn't matter if they're a tree grower. Doesn't matter if they're in row. Doesn't matter if they're counting cattle. They need value. We heard that, abundantly on the producer panel yesterday. But that's my mission in life. And when I'm not doing this, I'm out racing mountain bikes. So if anybody likes cycling or racing mountain bikes, see me outside. If there's some local trails, please let me know. When I'm back in the area, I'll bring my bike. Good intro for AgriView. Here's kind of a quick video on actually what it does. And it takes UAV data, low altitude plane-based collections. It pulls all of that data together, stitches it all together using a lot of the different orthomosaic engines that everybody's familiar with. Then it runs various models to determine inventory levels, per tree health metrics, height, canopy size, area, and then it provides a visualization. Thank you for the lead in, Brady. The visualization is important. In what is essentially, I'd call it easy button plus. Idea here is that this kind of visualization really pairs with the intuition that the grower has or the producer has. We heard yesterday, there's an error rate in this. but this is pretty good. It's, you know, it's gone through the process. ASABE named it to the top 50 global products a few years ago for a reason. But you got to pair the realities that the grower, you know, intuits with some of the visualizations that you see here. Using a multispectral UAV, AgriView also provides for citrus. This is a citrus only product right now, but the idea here is driving towards identifying deficiency. Deficiency is one of the key areas to improve your yield. If you have a deficiency, the tree's not getting the nutrient it needs, it's in poor health. No matter what the crop is, it's not going to produce the quantity or quality that you want. So by identifying deficiencies, putting it in management zones for nitrogen, phosphorus and potassium, as well as 8 micronutrients, we're able to kind of, again, connect the grower's intuition about they think something's going wrong with a full field, non-sampled approach to leaf-based nutrient analysis. Now, I'm very happy to report that what you're seeing on the screen here has been a product of phase 1 SBIR USDA grant. We completed the initial aspects of the visualization that you're seeing here. And then our phase 2 is about extending this technology through the Generate Nutrient Report link there, pulls up a calculator or a precision fertility map where for each of those different management zones, you can create different application rates. And that file, or that precision fertility map can be downloaded to a shape file that can be used by variable rate spray systems, drone spray systems, so that you can have precision agriculture in action, which is what it always should be. So we've made some progress in the phase 2. We've actually delivered the first version of the downloadable file so that it can be paired with a variable rate spray system. So as it hits those zones that have a deficiency, then the sprayer can spray at a higher rate. Or some of the drone technologies are a little more promising. They can onboard the same file. They're a little bit more pinpoint. They can go straight to the area, address the deficiency. And if nutrient values are higher in excess, they may just let it be, which is, again, a shift and an innovation in nutrient management. And it's important to note that this leaf-based nutrient analysis is aimed at trying to be a more complete view. One of the many issues that growers face is the cost of doing sampling, the human labor costs that are associated with data collections, the cost of shipping it, the cost of actually the lab completing the analysis. Not to mention, all of these methods are all human-based. This approach is a system-to-system solution. So from the data collection point of view, utilizing a drone imagery or a drone as the system, and then, of course, all the way through to being a full field representation. And by doing so, we remove out the sampling errors that are naturally part of, getting a lab-based analysis. This is crucially important in Florida, but certainly in other areas where there's irregularities in the inventory. Florida, I think many people know, is dealing with the Hualongbing citrus greening disease that has really devastated the Florida industry, and it imperils its future. But, citrus greening is everywhere in the world. That irregularity that's caused inside the tree inventory makes sampling approaches that much more precarious. So you can, have nutrient values from a drone that looks at all of the tree's values, then clusters the tree values together with the aim of trying to demarcate management zones. It's precision agriculture in action. We recently took a second license from the University of Florida on a ground-based sensing system that we called AgroSense. It's an onboard AI with LiDAR, multi-frame per second cameras on both right and left side of the vehicle. It confirms tree presence. It confirms much more accurately than a UAV or other type of imagery data set because it's kind of a ground truth eyeball of what's going on with the tree. It also, the 100 frame per second camera, I think it's 100 frame per second cameras, the multi-frame per second cameras are counting the visible fruit that you can see. Doesn't count inner fruit, but it gives a count and it measures every one of those visible fruits using some of the popular object identification tools. This is actually a data collection sensor, but it also can be attached to a variable rate spray system and can actuate the variable rate spray system. So the data can be downloaded from AgriView, or the UAV data can be loaded onto a variable rate sprayer. And the onboard AI is also looking at the actual conditions as the sprayer moves through the field, and then it will adjust. I think it stopped there, but if you saw that at some point or another, when the slide stopped, the sprayer, when it sees a gap, stopped spraying to reduce, the input on the field. We all know these technologies. The integration here, I think, is that we can pair UAV-based images, a quality leaf nutrient analysis, so that when they're in the zones, then the rate will automatically be handled by the onboard system. So this AgriSense sensor is still being brought to production. We're been talking to some of the hardware makers that are, in Florida, because that's where we're from. So another exciting aspect of this is, as a data collection point, it's again a system. It's not a human collection. It can be put on a tractor that's running at around 3.5 miles an hour, or there's a hitch mounted solution when it's just doing data collection. You put on a truck and you can be running it up and down the rows at 12 miles an hour. So the speed of data collection is still part of the focus, to get the speed of information into the grower's hands as quickly as possible. So as the nutrient analysis takes drone data and does a full field nutrient analysis and visualizes it in front of the grower and pairs it with a fertility and precision fertility map, replaces the weeks that it might take just to get the lab results back. This approach is another way in which we can collect very high quality ground-based data that can be paired with imagery from above, where things like the exact tree health, if the at-risk or the dead aspect of a perennial tree crop is still difficult to detect with a UAV, this data set is clear as day. And of course, it's all geolocated. So both of those data sets can use that as a common point to say that tree in the UAV was looked at risk, and the ground-based collection can be like, no, that's dead. That tree is dead. So then the visualization for the user can then be enhanced. So when they look at their field, if they have these two data sets from the air, from the ground, and of course, we talked about it, Jennifer talked about it before, the 4D aspect of over time, which we know is so crucial, creates that relative understanding of change. So I think these are the kind of systems that we're excited about. Some of the other projects that we're going to be working on in the future are oriented around data ownership. Our company, Agriculture Intelligence, was named not just because this is a really groovy AI tool that, visualizes things and connects intuition and drives at that. Our main missions are to increase the revenue for a grower, to increase their margin. Now, we can do that by helping them make their crops more healthy so that they meet their sales contracts. And we can try to do things like helping them, informing them on where they can plant, where they have missing, trees. They can be pinpoint about going about that so they have inventory in the future. But some of the exciting prospects are in whole new markets that can be developed. And so our team is working on a couple of these aspects, but it's all still driven by, let's find ways to give growers more revenue or more revenue reliability, to open ways in which to help grow their margin. And all of these technologies for growers, or we work with crop insurers, also will reduce the risk. We heard yesterday on the panel very clearly, it doesn't have to be perfect, although I think they jested and said they always want 100%, but I think everybody in the room got a good laugh out of that. I did. But if it's good enough, and if it's something that helps them reduce the risk, that's a crucial aspect of what they need. And then as a small business partner or a small business, we're trying to be as responsive as we can because we have a small team still. We get to, try to focus on accommodating that as much as possible, and then still rely on all of the existing, larger platforms like Esri and some of the other larger architectures that we're all using too. So that's sort of our platform, what we're doing, some of our philosophy, and I think, hold your questions. We're going to get to those in a little bit.
So our next speaker is Nathan Dorn, and we've been on the software side. And of course, everybody in this area, there's always a software component, but actually developing some hardware here. He's the lead for ag business development at FarmNG. And I know we have some customers of theirs in the audience. He's got to start as a farm kid in Nebraska. He also has worked as a custom harvester in wheat. And served as a nuclear machinist mate in the U.S. Navy. Previously on the ag tech side, he was the CEO of the data capture and science company for specialty crops, Food Origins. He's also worked as the director of knowledge and innovation at Ryder Berry Farms and was a technical manager for Gallo Coastal Vineyards. So with that, I'll let Nathan get started. And there's his first slide.
Thank you. Thank you. And thank you all for having us. I appreciate being here. I like coming to Texas. So mine will be a much shorter and simpler discussion. We build Legos for farmers. And most of you guys have a box of Legos at home or had a box of Legos at home and you didn't put it together like the picture, did you? The idea there was you had something in mind and you did it something different. And so this is kind of what you see here. You see 4 wheels, electric, battery, a chassis, a harness, and you can change it all around. Simple 1.5 inch metal. You can change it to a different shape. Here down in Gulf Coast here at Texas A&M Corpus Christi, they're going over the row so that they can capture data on their corn for a period of time. We're also co-founded by some of the big believers in open source data. So one of our co-founders is Gary Bradsky, the founder of OpenCV, and all of our platform is open source. We have basically a Jetson NVIDIA Xavier NX that you can code on, you can build your own stuff. It can be your own proprietary knowledge. We put on top of that a few data collection cameras. You can add to that, change that, do something else. Enable a little bit of autonomy, mostly teach and repeat, and data capture with the Luxonis Oak D cameras. So we can gather RGB and depth and other stuff on top. The platform we've put into the hands of probably 60 to 70 universities and 120 farmers. Truthfully, it's not a tractor. We're not competing with tractors. We're competing with the jobs that you do walking. I mean, and that's what wears out a farmer. That's probably what wears out a data scientist. I haven't met a researcher yet that's decided to give up because he's walked too many miles, but I'm sure if I had hung around with you longer, I'd have heard it. But the walking, carrying, doing the heavy lifting of your daily job, that's what we do. And what we're trying to do is make it in the format you can do things. We've made these in a lot of different shapes, a lot of different sizes, trying to service a lot of market. We're servicing farmers doing weeding, seeding, data collection. We've got tons of data on how lettuce is grown so that the next guy who comes and picks lettuce is going to build the right robot right away before he ever gets into the field. We can go immensely slow. We can go about 12 feet per minute, or we can go about 500 feet per minute with this platform. Carry about 1,000 pounds for 8 hours on a rechargeable or interchangeable battery swap. We've towed sprayers and done harvesting and other things that you do on an everyday basis as a farmer. Really, there's not a lot to tell you other than it's just a tool for you to use as you're in your next thing. I mean, this is me carrying it home. I used it carrying those rocks out of the sheep pen where I reached down and I was on my hands and knees and throwing them up. Still requires the guy to be there doing that daily, everyday work. It's not that super exciting. We're not quite in the defense industry or anything else. We're here to help service data capture and farmers for research. Thank you. I can talk more later.
And our final panelist is online, and that's Nitin Nahata, and he's with Bayer. He is a seasoned technology leader, currently serving as the Senior Director of Engineering at Bayer. He leads engineering for Bayer's collaboration with Microsoft, which is focused on advancing data interoperability and bringing advanced data analytics solutions to the ag industry. Previously, he spent 15 plus years in the tech industry with roles at Apple, Twilio, and Akamai. He's currently based out of San Francisco and holds a master's degree in computer science from USC. And he's passionate about leveraging technical innovation to solve large-scale, real-world problems. So with that, I'll turn it over to you. Thanks for joining us.
All right. Thank you, Dr. And hello, everybody. Hopefully everybody can see and hear me. Okay. Give me a thumbs up if that's the case.
Yes.
All right, thank you.
We can all see it.
Thank you. And thank you for having me on the panel. I'm very glad to join everybody. Apologies for not being able to join in person. But appreciate everybody's presentation so far. Very exciting panel. This is. I don't actually have any slides to present, but I would love to talk to you a little bit about, what we do at Bayer. Hopefully, most of you are familiar. We are, quite deeply and quite, heavily involved with agriculture across many segments, right? We think of, our mission as, pretty ambitious one. It guides us across everything that we do, right? So let me introduce, the mission that we have, which is hunger, health for all and hunger for none, right? I work in the crop science division, which is focused on the hunger for none aspect of our vision. And that pretty much guides every aspect of all the work we do. We think of, the work we do in primarily like three broad categories. One is, of course, we are one of the largest providers of agricultural inputs in form of seeds, traits, and crop protection chemicals. So those are the two pillars from the input side. We have pretty significant presence in digital and precision agriculture as well through our FieldView platform. And now more recently with our partnership with Microsoft, while FieldView is more sort of B2C, SaaS focused, our partnership with Microsoft is more focused around B2B, which is really about enabling others in the ag industry to leverage what we are building together with Microsoft. And we're bringing together all the expertise and all the knowledge that we have learned with decades of experience in digital and precision ag to offer that to all segments of the ag industry, starting from growers on the upstream side to, downstream, companies like CPG companies and everyone in between who's involved in, logistics as well as management of the farm produce. So that sort of is a overview of sort of what we do. And as Dr. Harden mentioned, the focus of some of our work is really to solve some very critical problems that I think many of the panelists referenced in their presentations, which are around data availability, data interoperability, and then being able to drive actionable and timely insights out of your data. So we're trying to tackle all three of those aspects through the platforms that we have. FieldView, which offers a lot of rich visualizations, as somebody called out. Those are super important. And then with our partnership with Microsoft, providing a backend or a B2B platform and advanced solutions that are available through a B2B marketplace that anybody can leverage as out-of-box solutions ready to be used.
All right. Thanks, Nitin. So now we'll kind of go into the question and answer format here. So I've got a couple questions, and these largely came out of the farmer discussion yesterday, right? So one, we've heard a lot about what the farmers need, and then we've had a lot of great presentations from the students and the researchers. So really, what do you all see as the biggest barriers or challenges to developing AI solutions in agriculture, in the next few years? I encourage you to think broadly. This can be anything from, technology, data, workforce. Go ahead. And whoever wants to take it can go first.
All right, I'm here, so I'm going first. All right, so we're at a university. Let's call it out. Education. So my biggest barrier is finding data scientists that have knowledge of the work that they're working against. Generically, I'd say data scientists are trained in ultimately computer science and statistics, which is great, but it's having that foundational knowledge of agriculture that brings value to the understanding of what they're building, right? The math can be great, but if you don't understand the contextual reasons as to why you're doing or trying to get to the answer, I need more of that. The other one that I would view as kind of challenging, and I think the rest of the panel can talk to it, would be cost of compute versus value that is derived by whoever that end customer is, right? And by compute, I mean storage and process. We talked a little, I was talking about it at lunch today, so it's just very top of mind as well, because if it, and I'll look to you because I think what you brought forward in your presentation is really good. How do I minimize my costs so that I can be a more profitable farmer, right? That's really what it comes down to. And I think we were talking about it at lunch a little bit today, and we forget about the value of money when coming up with answers. So I'll leave it to you because I think you're answering some of those questions anyhow.
I mean, I think the biggest challenge, it's somewhat related, is that the researchers have a very clear and focused understanding of the problems that they're trying to provide solutions for, and that the solutions that they develop and the research that they do has to meet the material world. That's a big challenge, and maybe that's been a challenge for years, and maybe it'll continue to be, but science should continue to be pursued for science. But when we're talking about practical applications for all of the different types of aspects of agriculture, it has to have a practical focus. And I know that that's true. I'm not accusing anybody of not. But I think, that is a mindset that needs to be encouraged. And I know that it is, but it needs to be the speed in which that we're now working, the focus on practical solutions that are defined by very real problems that have a somewhat skeptical audience to adopt. So if the research that comes out has a very clear understanding of the real problem that exists, then it makes adoption impacts easier, because that solution is likely to increase the revenue or increase the reliability of the revenue or decrease the risk of trying something. Cost cutting really doesn't move the needle the way that you'd think it would be. So, and it's a mix. If a solution hits that touches on 2 of the 3 of those, or some of these real impacts that the producer panels and the producer voice gives you every time you talk to them, that's a win. And so it's both the problem and an opportunity here, is that the problem is to have a continued real focus so that the solutions that researchers come up with are market ready, or at least a much more adoptable by the grower community.
Yeah, and if I can add to that, I think that's a super important point. And goes back also to your first slide, Dr. Harden, which was about the digitization index and where ag as an industry sits there, right? There's a reason for why ag is not quite, caught up to the curve of digitization, right? One is it is extremely, CapEx intensive, right? So anytime you want to actually do something, right, you would have to, start from scratch in most cases, right? So you have to figure out how to bring the data together. Then when you are able to, because, ag being such a diverse and such a big ecosystem, there are many sort of subsegments within ag, and all of them have like different sets of standards, different sets of data formats. So it's really capital intensive, resource intensive to first just to figure out how to get all of the data. And really, as we all know, right, the quality of the insights you can get depends on the depth and the breadth of your data. So there's not a lot of standardization in the form of ready out of the box sort of infrastructure that can solve that problem. So that is certainly one challenge, and we are trying to tackle that as part of our partnership with Microsoft, certainly, right? Because all AI and the efficacy of the AI outputs and the predictions depends on the quality of the data, and then being able to leverage that data in all layers of data. Today, the challenge is everybody in some ways is trying to reinvent the wheel, right? Having worked primarily in tech before my current job, right? One of the ways like tech industry like moves faster forward is because they're constantly not rebuilding, but like building on top of what was done before, right? That is not quite true just yet in ag at a very broad and large scale. It is happening in some smaller, micro sort of segments, but needs to scale up to a level where it's happening, where people are not trying to redo the problems and resolve the same problems, but rather building on top of that.
All right, thanks. You got anything to add to that, John?
I could throw a little bit in there. I think so. I think the most important quality I bring to this is I was that Nebraska farm kid, and I've had a chance to see a lot of crops around the world and different places. When we did that wheat harvesting job, it was pretty common. We would brag that our case combines threw off about 4% if you operated them right off the back. The guys running the gleaners were running about 11% out the back. You can't capture that with a satellite. That's data that is gone from what is coming out of the yield. Wine grapes last 10 days before we harvest them, we shut them off from irrigation. Why? Because the winemakers want higher sugars so that you can, and how do we do that? We turn them into raisins, most of the way into raisins. That's all mechanical error. That's stuff that we do. You can't see that from a satellite. All you can see is how healthy the plant is. In Oregon, they prune to 3 tons an acre every day. I mean, if you produce more than 3 tons an acre, the winemakers don't want it because they don't believe the growing season's long enough to allow that to happen. In California, you can grow 11, 12 tons an acre if you want it, unless you're in Napa, Sonoma. In strawberries, if you've ever done something, take a group of your friends out and competitively pick a box of strawberries with some Hispanic guys in Watsonville. I do that all the time, and you'll see all sorts of mechanical variation. You will walk twice as far, maybe 10 times as far to fill a clamshell because you won't get a box done by the time they do. And you'll pick 1/8 of what they did in that distance. That's mechanical variation. And when you go back to the table, the gal that is inspecting your box of strawberries will throw out 90% of what you picked because she said you didn't do it right or you picked crap. That's variation we can't see. Farmers know that, and it gets to the next thing I put on here, and it comes, we've repeated it over and over again. Farmers know that, and we still come to them every day and we say we're going to take data and we're going to solve their problems. And that's a lot where their trust question comes in. They're like, I know you can't solve this, but I know I need to know something more. I mean, it isn't completely a trust issue in data, because they all have a cell phone in their pocket. They all know that they went 80 miles an hour on their way here, and they know that Google or somebody else knows how many minutes they were over the speed limit, and they could have gotten a ticket the whole time. So it's not that they don't trust and they don't think we think we're all going to do nefarious stuff. It means that they don't think it's actionable and they're going to make money from it. So the skepticism comes about, and I don't have a fix for it. I mean, I'm not the theologist that can fix that. I just remember doing this over and over again. One of the things that we do in our company that help work on that is we had that farm robotics challenge where we've sold our machines to universities, and we've asked them to have student groups, the innocent of you, we appreciate you, go out and meet with farmers and ask them what their problems are and go back and solve it. You get 4 months. You don't necessarily get it all done. Farmers get it, but at least you get a shot at it, and you get to hear what's going on, and you get another day in the field. And there's a lot of computer science, data science, roboticists that were farm kids that would be, their families and their friends are happy to just see them back for a minute and seeing that stuff. So, I think that's the problem, not helping at all with the solution here.
Yeah. No, and I didn't ask for solutions yet. So that's a whole nother conference, I guess. So I was going to follow up and reframe that a little bit. And then we started late, so we'll go late so y'all can have some opportunity for questions. And that's the trust issue, right? So the farmers mentioned, we'll give our data to the university extension personnel because we trust them. But if you're in private industry, we know you want to make a product to sell us, and there's a barrier there. But of course, AI models, big data, we need lots of data for a good model. So how do we address that? What do y'all see as possible solutions to that? And I'll let John start off since he didn't get to respond there.
All right. I'm also a Nebraska farm kid from a custom combiners family, and for some reason when I went off to a fancy East Coast school, I somehow became suspect in a way, and I sort of lost the trust by kind of venturing out and going to college and being corrupted and through a university. I would say that many of the issues that growers experience were articulated on the panel yesterday. Companies aren't doing their research before approaching them. They're making claims that are unsubstantiated, and there's certainly a lot of history of that in agriculture and AI, and a lot of kind of very public fails that have happened. Right? It's estimated that 85% of models aren't operationalized. All of that decline in funding wasn't because agriculture, the funding of those agricultural startups was too successful, right? So there have been billions of dollars wasted on non-operationalized AI models. Unused sensors are littering fields of farmers' operations, and that's not lost on the farmers, right? Our goal at SAS is not to monetize farmers' data, right? No, we have no issue with those who do, but where we are placing our chips is with the entities that have a long track record of success, having built up trust over many years, and that's agricultural extension with that 150-year track record. So we believe that the best way to implement AI in a trustworthy and equitable way is to work with agricultural extension and those agents who know the farmers, know what matters in the region, and know how to communicate it in a way that's effective.
If anyone else wants to add a little to that, I'll
I'll just do
Let you go for a
a
minute or so.
super short one. Again, we defined that I came out of an intelligence background. So tell me if you heard this one before. Trust but verify. So what we really mean by that, and John, I love it. I love everything that you had to say, because one of the biggest challenges that I've seen in the AI models that have come out are, where's the independent verification and validation of that model? Who is validating your model that's not you and is not connected to you? So it's interesting because, I'm speaking as a commercial company, building out those models. I need somebody that is not linked to my company to validate that the output that my model puts out, or that I claim puts out, back to your 80% operation or 85% operational AI. I think there's lots of R values that are out there, F scores that are maybe a little wonky, or I usually love this model is 95% effective or accurate. Okay. I also need to know, is it accurate in the geography that I'm working in? Because there's a good chance that it's not. It's a good chance that it's not localized to that geography for whatever it is that I'm looking for. So I think, again, trust but verify, and provability of the model by someone outside of yourself or the data scientist that built it.
I'll just add one comment to that.
One quick response there. We'll keep it quick so we can get some questions from the audience.
Yeah, so I was I think you touched upon a very important point, which is like ag is extremely complex. Unlike, again, going back to my tech background, right? Now working in ag, I feel like things in ag are way, way harder because tech only deals with everything digital. Anytime you have digital and real world meet, right? The level of complexity just goes like exponential. And just to summarize that, right? I mean, nature is just one variable in ag, right? And we use supercomputers to predict just weather, for example. So to your point of like, models need to be effective in the localized environment, right? That's a variable that's not very easily controlled.
Yeah. All right. Do we have any questions from the audience? I'm sure we've got several there. So I think so. Was there first?
Hi, Josh Peoples, faculty here in the Department of Electrical and Computer Engineering here at TAMU. I think y'all make great, excellent points about what we can do, particularly for education. And so my question is, what are some ways that y'all, or mechanisms that we as academic institutions could collaborate with y'all, particularly for, getting students connected with actual problems that will enhance their education?
I brought out the challenge for us, and really, I had a call from India, and this guy said, do you build something that would help me like do yield prediction on rice in India locally? It matters a lot to us. And I said, I have none of that tools. I just have a platform that you can drive around and capture a lot of data. But I'm sure that you've got some brilliant local kids that can spend hours with you and take a lot of data over and over again and really look at that problem deep. The next platform that I should be selling this week is going to go to a cranberry farmer in New Jersey. I mean, it's the problems of ag are just like you grew up in it. I mean, it's everywhere you go, it's something different. And I like to start out my talks at conferences by asking how many people here are scientists and in the ag community, and you don't have to raise your hands because I know all of you. But then I ask them, how many of you believe that farming is still an art? And almost 3/4, maybe 90% raise their hand every time. And I mean, like, that's counterintuitive to why we went into this career. It's getting you engaged, just hearing out the problem, creating that thesis, and doing what that poster did is all I can say we can do to start by bringing you in.
And I think we'd probably just add in all of the normal things, like everybody on this panel, we need quality talent. All the businesses that we're in, because it's still an art and because it's an advanced science also, We need the best and the brightest. We need people with, that are willing to be part of a team that, can understand that they can contribute. And, that's for younger people that I don't know if that notion is going to soak in with them too well. Maybe for your ag researchers, it's different, but it's just quality people, I think, is still what it's needed. And we do what we can with internships and, job fairs and all of those kinds of things. I'm sure everybody up here and Bear probably has an entire summer series, but I think it still comes down to finding good people, and we're always open for that. I guess I'll probably just hopefully speak for everybody on that.
I think so, yeah.
And
I mean,
one thing as a recommendation, maybe if I can add, is like for students and, researchers is like, this is probably feels like the right time where like, a lot of digitization is going to like, accelerate in ag, right? So if you're really want to stand out, right, you would take sort of some of the same algorithms and, AI models that you would use just in a purely digital world, say, for example, image detection, but, solve it for an ag problem, right? It will be harder than just to solve it in a purely digital context, but, that would also help you stand out.
Thank you.
Thank you. Very interesting perspectives. I'd like to get into a topic that we haven't heard much in the last 2 days, is about statistical risk and the risk taken when we make decisions. So typically in everything we've seen around here today, last 2 days, a lot of some of the predictions are to help predict what's going to happen and get prepared, but there is no direct consequences. If we make prediction to spray, let's say, Carolina geranium with the right pesticide in the field because we've trained that machine how to detect, how to recognize the Carolina geranium, it's right 95% of the time, which means that there are times it's going to miss one, which maybe is not too bad, but maybe be a time where it's going to think a tomato plant is a Carolina geranium, is going to kill a plant. So my question to you all is, in all your applications, do you look at the cost of the errors that inherently, even if we don't recognize them, inherently all those models make?
That's a great question, right? So all models are wrong, and most of our historical decision making in ag is based on some level of risk and acknowledging what happens when things go wrong. So how is that being addressed, or is it?
So right, back to when life and death matters, we have to make good decisions. So I was introduced to a term that I think many of you have probably heard, human in the loop, as far as a method of using artificial intelligence and machine learning to have a human interact and intervene. So that means that the human intervenes within the decision cycle. I was introduced to human on the loop, which is same concept, but allowing the loop to run and then having creating that decision or that prescription or that prediction, however you want to look at it, right? We do predictions so that we can do prescriptions and then we can act. Having human on the loop changes that paradigm a bit. Right now, we're not prepared to do a whole lot where a human isn't the one that's making the statistical jump. So if I have a 5%, let's go in sorry, I know it's not ag, but if I make a decision and I have an algorithm that decides that I'm going to have a kinetic event at some point on the earth, right? Something's going to blow up. 5% is not a good variable for me. So if I know that I've used all of those other resources to get down to 5% of error, I will use every resource available to me to mitigate that 5%. So I'm going to stick to human intelligence because I trust it, right? We're back to trust but verify. I will let the trust of the human expert mitigate my risks for me. So I think if we just kind of dial that back for ag, we have to start measuring what's the risk of that 5% and measure and decide whether that is one that we want to mitigate or not. So it does come down to that risk versus that reward against the algorithm that we've used and whether it's worth 5%. For the most part, it may not, it could be. If you're talking about, I'll use no expertise here, but if I'm using a chemical and I want to make sure that I do not have an overspray into a water table that would be bad, obviously I'm going to human involve myself into that decision. If it's no real risk, that 5% error is not really an issue. I'm satisfied enough at 95% effectiveness.
Earlier, when we, because typically the AI systems are sold that they work all the time and they make better decisions than you do. And when the rubber meets the road, it's not always true. So I think we need to be a little bit more, when we sell a system, maybe we'll be a little more balanced and not oversell it. Because if we tell somebody, okay, you got to have somebody sit on this machine to recognize every Carolina geranium, the farmer is going to say, well, I already have Manuel do that. And so I don't need your system.
So yeah, go ahead.
Well,
I've got stuff on that.
compared to that humans always do it flawlessly. I mean, the mechanization that exists, the decision making that's been in the field for hundreds of years, they make these mistakes too. And again, I think the human in the loop and human on the loop is a way in which that you can produce more and still have a decision maker that can try to avoid the additional errors that, might not be accounted for, what are proven algorithms. And are they're operationalized and they're proven, to Brady's point. So again, I think relative to humans made these mistakes too. So, I think it's a transition and they're new tools, but I think we can incorporate the same human intelligence and someone who's in the field that can, be a corrective action and mitigate, any problems. And maybe Nihit might have a he's on the input side.
Right. Yeah, so I was going to add, I think absolutely agree, right? I think, humans make a lot of errors as well, right? And AI is really about automation and getting precision right. And I think to the point of like the person was asking the question, right? I think there is also an opportunity here for new types of business models. So when you're selling AI-based solution, right? There is some kind of like risk sharing. That's a new business model that can scale and emerge, right? Bayer is actually, trying this out, where depending on the outcome you get based on following the recommendations provided by Bayer's AI system, right? There are innovative sort of business models that Bayer is trying to share that risk with the grower. So that's another sort of dimension here, which can scale larger in the future.
So I was just I know we're super over time, but I love this topic. And I actually love that you asked the question because it's a great question. So the next question would be, automotive industry. Why aren't there more level 4 autonomous vehicles on the road? And if anybody actually needs to know the answer, it's because of the risk as to who owns the risk of making that decision. So Tesla, Ford, GM, BMW, it doesn't matter. Pick your brand. Right now, as the laws say, and this is why you do not have it, right? You do not have full autonomous vehicles because of this simple reason. They don't know who's going to take the risk. Yeah, exactly. It's the liability risk, the insurance risk for that vehicle. It is no longer the human because I can't insure you as a human. That doesn't make sense because you're not driving the vehicle. I actually don't even care about all of the risk factors. The actuary tables that were built around understanding the risk of a human are now null and void. I now have to look at the actuary table for your model for autonomous vehicles. And none of the car manufacturers want to say, hey, you know what I'm going to do? I'm going to sell you this car for $30,000 and I'm going to inherit all the risk for every time you get behind the wheel. So what they want to do is they want to push it to the model maker. So that model maker is saying, well, I'm willing to take that risk for what value? I want $50,000 per vehicle for that risk because, well, ultimately I may have to insure life limb for every single person that's impacted by that. And the decisions that my team of, 1,000 engineers went and made. So again, we're back to this like standoff. Who's going to own the risk and where's the risk import?
Let's get one more.
So we're pretty over time here. We got 2 questions left. 2 questions, 1 and 2.
Okay. Yeah, and I was going to add, we see auto guidance. That tractor is autonomous in the field, and we've seen concepts, but there's no tractor that drives.
And I see more Waymos in San Francisco driving around with nobody in them, and it's illegal to drive a tractor autonomously in a field in California. I don't understand it. Don't know the answer.
Hello everyone. I'm Yash Zamre. I'm a master student at Texas A&M. My question to you is regarding the last part where we discussed about the validity of the model. So I am a researcher. I am developing a model. The way I choose to validate is because it is a vision state-of-the-art model. So one of the highest aim that I could do is presenting and getting my work published at a top-tier conference. So isn't that a good enough validation for industry experts on the other side that how efficient our model is, or is there some other kind of validation is the industry looking from the students right now?
I'll refer you to Dr. Clarke.
So again, that's a question about validation and really what's needed, right? Is, as researchers we publish and.
Yeah, I think there's the scientific validation, which sounds like, you properly should pursue that. Market ready solutions in this space must have that. And like our platform that we licensed from the University of Florida had been through peer reviews, published in major, journals. It got the ASABE award it was validated in an additional step out of sort of the scientific space and into the industry space. And then there's the further validation, which is the most important, which is the grower's validation of them saying, yes, this is actually working. So I would say those are just, in short, that's the 3 things: the scientific validation, the general industry sort of external validation, and then the ultimate customer validation. We'll keep it short, I guess.
It's all right. And we had one more question, I think.
Yes, I am Charlie Williams, and I'm with the University of Arkansas at Pine Bluff. I assist small landowners. What services can you help sustain their operations? I go out on their farms and I provide them resources to help sustain their operations. Any of your AI data good for vegetable crops, pastures, forestry, all of those resources, all of those land uses, we assist them with providing them resources to improve their functions. Who can assist me? Thank you.
I love that you got that question in. That was ChatGPT also thought that would be a good one too, but that's a great question. We've had a lot of discussions at the conference regarding, how do we serve some of the smallholder farms and maybe specialty crops and small landowners that aren't the big corn, soybean, wheat farms. Go ahead.
Well, I'd certainly love to connect with you, and I mean that aligns very well to the work that I'm doing with NCA&T, for example, who primarily serves smallholder and minority farmers and specialty crop growers. I would say just in general as a broader concept is the needs of smallholder farmers are by very definition niche, and so you can't really look to giant companies who want to have a streamlined portfolio to support their needs. All the more reason to deploy these insights and technologies through agricultural extension, through the groups that are already serving these growers. The second thing I would mention is that just because it's vegetable crops or sort of unique business operations doesn't mean that doesn't lend itself to AI. The cool thing about vegetable crops and horticulture and specialty operations all around is that you have a low sample size, not a lot of data points, but a whole lot of variables that go into it. And that is precisely the situation that lends itself to AI and machine learning.
Okay, we'll give someone else a shot on the panel if they want to.
Well, I mean, I want to talk with you later too. Go ahead.
Mentioned since you mentioned sort of, big players. Actually, Bear does operate in the smallholder space as well. So for example, for India, we have a app called FarmRise, which is focused on smallholder segment in India. And the solutions for smallholders will of course be different from like large, corn, wheat growers in North America, right? One of the things that we have observed is like a lot of crowdsourcing is a very powerful thing for smallholders. So knowledge sharing through crowdsourcing and making that available, very easily, through app like FarmRise, that can be very low cost but very effective mechanism to support smallholders. And then the second, since we are talking about AI here, right? I think the cost of AI, has to come down to be able to service all segments, right? Today, like if you think about LLMs or ChatGPT style latest models, right? It costs like 100 million plus to build the foundational model, right? But this is how technology evolves, right? Like 20 years ago, like there was huge billions of dollars of investment put into fiber cables under the sea, which were not quite utilized at the time. And we had the dot-com bust at that time. But what we have today, right, is actually built on top of all of that investment that happened in the past. So some like technology has to catch up to kind of bring the costs down, but there are in the meantime like solutions that are very effective, like crowdsourcing and other things.
All right, I think that's probably a good point to wrap up on. Did we have? Were you gonna?
No.
Did you have a response? I couldn't tell if the head nod was ready to say something or I don't want to talk over you, but I think it's great to wrap up with, in that we mentioned, how farming's more of an art and that we really have a lot of knowledge there, and the crowdsourcing idea and how we go forward and capture some of that farmer knowledge in developing these models and utilizing that, I think is going to be important. And hopefully some of the new technology that's out there will allow us to do more of that than just using data from satellites or sensors. So with that, I think we're on to the next one, right? Seth, or you? We'll give everybody a hand. Thanks to our panelists. I love it.
Thanks, everybody. Bye.
Thanks, Nitin. And again, to Mahendra Bandari for setting this up as well. I don't know if he was in here earlier when I called him. So thank you.
At the risk of potentially losing some people, we should probably take a little coffee break here. There's coffee out there and water, and then Dr. Ali is going to lead us in a little discussion on ethics, and then we'll see where we're at. So go get some coffee or water or tea or drink of your choice. For the students that are left, now would be a good time to take down your posters if you haven't taken them down already. Otherwise, they're probably going to be thrown in the trash. Yeah.
I would say. Yeah. Oh, I was building a fight. What a great quality. All right, thank you. No, and I built something like that years ago. I have a lot of like that's not what I was thinking of doing here. You'd be you being honest. Yeah. It's not going to do everything, but for the next part of it's going to be a lot. And good reality, it's the work thing we all need to do. Tell everybody there's an inverse relationship between your quality. If here you are, the more qualified you are right away. Brain. Okay. You don't even need a brain.
I think we can start. Let's get together and in 1 minute so that we can have a quick discussion about ethics in AI, and we'll call it a day. I don't want to hold you more longer.
I am good. I know you've been busy. I didn't want to bug you. Oh, thanks.
Good, good. Everything is fine. Thank you. So how is Tom doing?
Tom's doing good. Tom moved on to run or we got funding to start the Dissemination study on living. For 25 years, we have administration. A lot of work with Zhanyou Xu
and Kelly Morgan.
Kelly is retired.
Retired?
Yeah.
Wow. Yeah. He did a good job.
He did well.
Yes.
Where were you?
Yeah, I'm a graduate. Also, I make up the University for 5 years. Ashok Alba, he was there, and Larry Parsons. Like the discussion gonna be.
I know.
I don't. Yeah, we can come over.
Start.
Yes. But it should start right now. So we'll just. I'm in Peru. I was back in this. Yes, we were in the. Were you guys used to that? I decided I can pass. Yeah, I think it was in what you call one of the training. We were together. Yes. Yeah.
So the challenge is we're live streaming. No,
So we should be.
So anything we live stream is going to be on the mic. So we could at least start it. You could introduce the topic. And
Okay.
we'll
Sure. Great. Well, I think this is the last session. It's going to be quick. It's going to be something informal. It's a discussion type and a topic that is really of great interest to many of us, which is ethics in AI. So ethics are needed in all what we do, but especially they are more relevant to AI because for many reasons, as we will see, part of the discussion we will be having. So I think with that, I would like to maybe, I took some notes. I have a brief overview of the topic. So when we talk about AI, ethics in AI, we talk about few things. One of them, fairness. How can we adapt AI techniques, adapt AI models that are fair? And so and they are the opposite of how can we have AI models, AI techniques, AI procedures that are not biased and fair? I think that's one of the area of that when you talk about ethics. Also, transparency. How can we have a transparent AI models or AI techniques and so on that are clear in understanding of what we are going to achieve and how we are going to achieve those. Another important thing is accountability. Okay, human oversight and responsibility in this topic. Okay. The other thing is, and I think many of, and I like what the discussion, especially the last part of the previous panel, is about data integrity. I think it came up several times during this meeting. Compliance with laws and regulations. How can we be compliant while we are using these powerful techniques? Okay, and this has been quite interesting, I think, with the launch of ChatGPT, and you heard about students using them and others, and I think a couple of weeks ago, that singer, that country music singer, I forgot what's his name, it made the news a couple of weeks ago about they thought that he was the person singing. It's not. It's generated by generative AI, especially. So reliability, AI solution should be consistently operational in accordance with their intended purposes. So I think it's, how can we assure that? Security, who should safeguard AI solution against misuse? Privacy, how can we, and I think the farmers and others basically raise that question about privacy. How can I keep my data private and not to be shared with others and used against me as in a competitive way or any other way? Safety, AI solution should be designed and implemented against harm to human resources, animals, anything that you safe in general term of safety. I think there is another one of sustainability, equity. How can it be used not to treat people equitably, but not to use it to discriminate against some people or some type of ethical group or things like that. And ethical relevance, which is, similar, to what we just has a lots of overlap with equity. So at least these are some of the thoughts that I found in the literature about ethics in AI. So I think maybe the question would be to generate some discussion here. It's not going to be a monologue, it's going to be a discussion. So what do you think about the topic? How is ethics, or are ethics important in AI? And maybe from your experience, can you share some of why is it important? Why it's not important? I can see you're nodding your head, so I.
Yeah, so I think it's an interesting topic. Yeah, sorry, yeah, thank hello everyone. My name is Josh Peoples. I'm a faculty in the Department of Electrical and Computer Engineering here at Texas A&M. So I've had one project where we looked at bias in AI during grad school, and I thought it was really interesting. Like I said, I come more from the core AI development point of view, and so I always ask people, can we look at quantitative metrics, right? So like my question is, how can you quantify, bias, or how do you quantify something's fair? What kind of metrics can you look at to say, okay, my algorithm is fair, or what is fair enough, right? So those are some of the thoughts I have about how can we define things, at least from an AI perspective, in terms of quantifying these notions of ethics in AI.
Sure.
Howdy, my name is Sarah Nielsen. I was having this conversation at lunch. I believe it was yesterday, may have been the day before. I was using AI to create a training for farmers in how they can use AI to accelerate their communications via social media by creating both imagery and language. And when I asked AI to create images of diversity for me, it took the skin tones of various people and painted them onto the bodies of white people. So I brought this up to the table with whom I was discussing the issues of AI as we have them right now. And someone asked the question, well, my issue is the people who are building the internet may have implicit bias. Is that being measured? And is the internet, and as a result, AI, are they being held in check against those implicit biases? And so the question that someone else raised at the table was, should AI and should the internet be representative of the economic reality of our world as it is, and the social reality of our world as it is, or should it be representative of an aspirational future? And so that's a question that I've been pondering, and I have a feeling, but I also have at times represented underrepresented communities. So that's where I'll leave it. It's something to ponder. Should we aspire to a greater and more inclusive future with this opportunity? And if so, how do we do so, especially legally and ethically?
Thank you. Yes.
I do not know your name, but I'd just like to concur with what you just said. We are resource providers for small landowners. We aid them in finding resources to install conservation practices on the land. But when we get to actually installing those practices, and I know it's an economic concern for the vendor who is going to install the practices, whether it's land leveling, whether it's tree cutting, and all, when it comes to the small landowner, it is hard to get these vendors, because of the smallness of the tracts, to actually perform the work on the land. We have to batch small landowners together, and we haven't been in this business but a couple of years of doing the consulting work that we do. So we are getting better at it. However, when it comes to AI and what I've heard here, it just didn't get down on the level. even many of the AI people. So we're working on how to maybe make this apply locally. So is ethics involved in that? Of course, if you can, we'd hope that if you make enough money off the larger guy, spend some of the resources on the smaller guy. Yeah.
I hear you. I hear you. I mean, that's equitability, how to make this technology, equitable and available to different small, different size farmers, and especially the ones who don't have the means. Yes. Any other? Sure.
So just everybody knows we're using the mic because theoretically there are people who are listening. So probably at some point we'll cut off the mic and maybe we can have a smaller discussion if those people in that corner want to come join the rest of the group, Amanda. But so all great questions on ethics, and like so many things in ethics, there are definitely more questions. There are clearly wrong things, but then, way more questions than right answers. It's much more of a philosophical conversation. But I think one thing I didn't hear you say, that's probably one of my biggest ethical concerns is, the, again, consolidation and corporate control of, I work in plant breeding, so GMOs became a big issue. And, one of the biggest factors that wrapped up people's concerns with GMOs is, they confound large company and corporate control of food systems with the actual technology. And if we look at most of the AI tools that people are prominently using, they are from extremely large companies. And if anybody, has a cell phone service and never had any problem and had to try and get a hold of one of those really large companies, it's almost impossible, right? So that will increase people's frustration. So I think when we talk about democratizing AI, there's, is it going to serve the smallholder farmers? But it's also, is there a landscape of small companies that are providing services rather than we have two companies that own everything? And, can you access them? Do you have a voice in how they do business? It's a lot easier if we have a landscape of small companies. So I'm really looking forward to more people starting up things that will compete with, everybody loves OpenAI right now, but in 10 years, OpenAI will probably be perceived as the bad guys, right?
Yeah. I think that's a great comment about this topic as well. So.
Yeah, I was just going to follow up with Seth's comment. And it's not just, right, the big companies selling a product. Some of it, this AI can be open source, a lot of it. Developing a foundational model takes a lot of compute time and money, but, my grad students download them and run them, right? This is not, but there still needs to be some sort of ecosystem for that. And maybe that's the point of kind of alternative business models where, there is that out there. And we did have some panelists that, maybe have some solutions, but, so I think, and that's kind of a broader thing in the technology community, right? Open source versus, more proprietary solutions. So be interesting to see how that plays out.
I think since, you brought a good question about small holders or small farmers and limited resource farms, etc., and the model that could be applicable to basically not to be left out about AI. I think I'm going to pick on my extension colleague here about. I think the extension has been leading in this area, in the area of helping limited resource through what we call cooperative operations, right? Maybe do you think there is an opportunity here for such what you call it model to work to help the needs of the small farmers?
Thank you, Dr. Forrest. My name is Saqib Mukhtar, and I serve as the Associate Dean for Extension, Ag and Natural Resources in the University of Florida. That's a good question, but I think I want to step back and also talk about how AI has become a buzzword on campuses. But when you go off campus, the extension agents and educators who have the pulse of their counties honestly have no idea what we're talking about here. We need tremendous amount of education and in-service training of those agents. In fact, we did our very first in-service training for our agents in Florida 2 weeks ago. And before that, as good extension educators, we did a needs assessment. And we asked people, what is your current knowledge of AI? And people were saying, oh, I know Chat GPT, I know Chat GMT, I know Chat whatever, because that tells us that there is, and there were people who have done courses out of Stanford and MIT. They are certified, but very few. So there's a big gap of true understanding of what are some of the needs out there of their clientele, and how are they going to meet those needs by first educating themselves. And very quickly on the big companies, to me, they're like cookie monsters. As you create those small cookies for me and you, they're going to gobble them up. So that's another major issue that we're having in this space right now. So unless we train our trainers, we're not going to be able to be very successful in meeting the needs of the underrepresented and small farmers in this regard.
I think that's, one of the things, maybe going a little bit to the next session, which I don't know, the program, which is what to do next. I think in one of the discussion we had, a strong presence of extension is needed in this type of meeting. Because if you look around, from the industry panel to yesterday's the growers or farmers panel, these are the end users. And some of them the providers, the industry. So I think part of the discussion should be with the extension colleagues present here, because they are the people who's going, the boots in the ground, as they say, who going to deliver the information, who's going to also convey the needs of these stakeholders that we are supposed to develop a solution for their needs and so on. So I think another extension colleague here who might maybe also see if she can also enlighten us.
I guess I could try. I know that, well, for those of you who aren't from Texas, we have 254 counties in Texas, and every county has at least one extension agent. And those agents, they don't all work in agriculture, but the ones, many of them do, and the ones who do, they are the ones who are more closely tied to the community versus me. I'm a specialist. And so we have like beef cattle specialists. I'm a livestock sustainability specialist. We have pond specialists. We have feral hog specialists. And so the agents go to us, the specialists, for specific questions that they have. And most of us specialists, we know about our niche area: dairy, beef, livestock, guard dogs, etc. But even us specialists don't have a lot of working knowledge about this specific topic. And then in turn, the agents, who are the ones who are close to the community and close to the producers, they are also quite swamped, and they're expected to be a jack of all trades for every topic. So it really and that portion, I guess, comes down a lot to state funding of extension and just needing more resources in that area. Kind of tying back to what you were saying, I think the beef industry is a really interesting example or an interesting case study, because the beef industry is one of the only industries in the US, at least, that still isn't vertically integrated on the livestock side. Most of our beef producers in the US they have 30 or less cows. And so the question of what is a small producer at that point? Well, a small producer is actually the average producer of beef. And AI, as I see it, could really help them gain access to many different types of markets, but they don't know about it. And a lot of that involves the word traceability, which a lot of beef producers really hate that word. I'm not going to get into why, but So extension education is going to be, I think, a major portion to help them gain access to those markets, especially because beef producers we have a lot of pressure from just society at large on reducing our greenhouse gas emissions. Even though we don't produce as many as a lot of folks think that we do, there are value-added products available out there that have a claim that say, this beef product was produced with 10% less greenhouse gas emissions than the average beef product out there. Well, the only way that you know that happened is if you can trace it all the way back to when that calf was born and trace it all the way through the supply chain. And really only large farms have access to that type of supply chain. And so anyway, just some thoughts. Yep.
Those are very good comments. I'm Luis Tedeschi from Animal Science here at this university. I think one of the questions I hear, all of the problems of extension, not just say extension, I think it's a lot of folks that don't really understand about AI, don't really know about it, but they may actually have a comment or what they want to say about it. But I actually have to think about this even here within the university, and I'm pretty sure many other universities, for some time ago, and I don't know what is the rule right now, we've been telling the students not to use ChatGPT. I don't even know if that rule is still up or not, don't quote me. And I know other universities have done the same thing. And the other question we have to answer, or I'm asking the question is, when you're teaching and you pose a question or a take-home type homework or exercise, would you accept an answer from a ChatGPT when the student said, I did ask this, I asked that, or did I ask that? Or would you accept an answer when the student says, I used an AI to solve this problem? And knowing that AI is not going to tell you how it got solved, only the solution for the problem. So are we, the faculty, the university, willing to accept AI when we actually need to train and teach the students how it works and how it is done so they know the concepts? So this is what I'm trying to do here is we're kind of there are two routes here. One is we need to make sure that they understand the concepts, and we're telling them you cannot use AI to get an answer. But then on the other hand, we want the students to learn AI and get to know what AI does and things like that. So what is our position? What is our university position in terms of teaching? So when you mention about those figures, the pictures, did you ask AI, why did you draw this? Why did you put these on these? And that might be something we need to ask is, okay, draw this, but then now tell me, why did you do this? I think, and then we can actually, I think then at that time is then we can actually think about, yes, that AI does have a problem. But going back to the point is about the teaching.
Yeah, I think you bring an excellent question about teaching and the question about GPT and how ChatGPT, how to use it. I think what we are trying to tell our students, and especially AI is great, use it, use AI. We are doing all these techniques and RNN and CNN and NNN and all those techniques, but we are at the same time we're telling them not to use ChatGPT. I think we need to and for many reasons, I think for obvious reason, in my opinion, that was said no, because we don't know that it's unknown to many of us. I'll tell you honestly, I didn't use ChatGPT yet. I didn't have time to explore it, But unless we know what it is, unless we know what it does, I think we need to know what is it, ChatGPT or any other generative AI technique that can do. And we can set the bar. We can say, hey, these are things that you can do with ChatGPT. These are things you cannot do it. I think we all ask our students to seek help, okay, from other sources, right? But we don't. We know that we tell them not to have someone else write their thesis, for example. It's not acceptable, right? But we ask them to seek help from other and get help. So there are some red lines that we can say, hey, this is permissible, this is not permissible. And unless we know generative AI, what it does, how it works, in my opinion, it's very hard to say, don't use it or use it, because we don't know what it is. What's this animal? For many people, I mean, we know certain types of AI, but we don't know as a whole. I think one thing is important here is how to educate the educator so that they can really convey the right message to the students, because we're training these people and they're going to use AI, all the time, like it, or they like it or not. So we're training them for the future. So we'd better know how to train them.
Yeah, I just wanted to add to what you have said and also about teaching. So I believe that the students should use AI to help them to learn, but not to solve the problem. So for example, you can use ChatGPT to find resources, to help me to find resources for this problem, not to, this is a problem and try to solve it. For example, if you are a student writing a code, he can use ChatGPT to find where is the error in the code, but he has to learn how to code, how to start to write coding. Yeah, because at some point you would need to understand the code to develop it, to add to this code. But at this right now, you can just give the problem to ChatGPT and okay, generate the code for me, and it will. And even if you try to run the code and you get an error, you can go back to ChatGPT. This was the error. What is how to solve it, and then it will. But in this case, the student won't learn anything about coding. He will be able to become a prompt engineering.
Yes.
Very quick example of this ChatGPT business, very quickly. About a year ago, our communications department sent out a notice or a communique stating that we're not going to oppose you using ChatGPT, but make sure that these are the rules. They gave examples of where somebody had written a blog. We have about 8,000 blogs and growing at UF on different topics related to ag and natural resources. But this was 2 years ago where ChatGPT had helped them create the blog, but also created some references that were not even in existence. So if I am writing the blog and we created the references that don't even exist, and I don't take the time to look at what I just created, that's a big no-no, right? You're going to be misleading people in so many different directions. But they were proactive in saying, we're not going to stop you from using ChatGPT because nobody can, right? It's inevitable. But these are some of the constraints, and you have to acknowledge that you've created this content by using this AI support.
Thank you. We have a comment here.
I guess mine is more in the form of a question now. Are there any AI resource providers that has services that can be available to basically all landowners? Of course, I assist small landowners that are making your service available, especially to USDA Natural Resources Conservation Service, that could be funded through the Farm Bill. I heard it spoken earlier that is how small landowners can get resources to help them install conservation practices on the land. And that would take small out of it. If you made it fundable through the Farm Bill, then anyone could use the services. So is that any work being done in that area?
Anybody knows? Okay.
Their name, but there was a speaker talking about how they have uploaded many articles from every state extension agency into their AI platform.
The Illinois one.
I believe it
It was
was.
Oklahoma State.
Okay.
That's the one here.
Oh, okay.
It was Jeff.
Okay.
The extension bot.
Okay, so if someone can write that down for this gentleman so that he has access to that resource or that individual, that would be would that be
Jeff-
helpful?
Jeff Vitale, Oklahoma State University.
Actually, so no, Dr. Vitale,
Uh-huh.
Dr. Vitale had one and he had far fewer resources because he was asking for contributions. So he had, I believe it was 12 or so entities working in conjunction with him. There was another representative of a university here who had already uploaded all of the data that he could access from extension across 50 states. So it was a much larger enterprise.
Yeah, so maybe you noticed that Texas A&M was.
Yes.
So we are also at kind of the mercy of our higher bodies, what they would like for us to do with our essential materials, how they would like people to access them. So.
That's a question of ethics, isn't it? Sorry.
Yes and no, because let me just. We
If you
have
don't mind.
all of these extension fact sheets that are in the cloud or in the internet land. Some of them may have been already obsolete. Just because we in UF archived them because we don't have anybody to revise them or review them, doesn't mean that a very old version lives somewhere. And I don't know if the current AI capabilities are there where it says, this is older information. We're not going to bring it to the user. How do we do that? Because there could be some very old information that says, somebody was asking the question about weaning of weeks of calves, of weeks versus months. So that, I don't know, that could be a major issue, a major contradiction right there.
Okay, I think we're getting there. I think we're having a good discussion and we're having a very nice discussion. I think it's the question is would be what do you see done at least in ethics or in, I think it's the broader aspect of ethics in AI. To close out, I think what anybody who'd like to have a volunteer here.
I love volunteerism personally. So two things. One of the individuals discussing neural networks this morning had a concept of a forgetting clause. And so it is possible within the AI system to compare data, validate, and then delete. This needs to be brought in and utilized when we are creating stores of data and caches of data and comparing, especially when research is ongoing. Beyond that, I would argue that anything that is published within the extension by its very origin, according to Abraham Lincoln, in its original purpose, belongs to and is for the people and should be accessible to them, period. I believe that AI is creating that opportunity. It is imperfect, but in a very dreamy sense, I think that it is a beautiful opportunity. Finally, I apologize because this is a devil's advocate question, and someone else's question, it wasn't mine. Where in Bloom's taxonomy does recall sit? Sorry? Slightly above knowledge, but where is that? Is that really high up in the hierarchy? It's at the bottom. Very good recall there. But it was someone else's question, and I think about it a lot. Are we responsible for the recall, or is AI an encyclopedia?
It's a good question. Yes, Seth.
Yeah, since I teach this in my graduate education and leadership class, I use Bloom's taxonomy to talk about AI a lot, because as we think about the lower level, the lowest level, which is knowledge, recall is another way of putting that, I guess. That's what Google replaced, right? And if we think about what education used to be, it used to be to train knowledge and recall, right? What I think AI is already helping with is a few higher levels, right? Comprehension, right? But the very highest level, I think, at least for the short term, which is, I'm trying to remember now. Yeah, it's way at the top. It's above synthesis, analysis, and there's another one. I should pull it up. Those are still at this point human-based skills. And so as we think about education and what we need to be training our future workforce for, I believe only the top level of Bloom's taxonomy will be relevant in 3 to 5 years. And so training students on knowledge is probably, they need a foundational knowledge, and this is very controversial. I know many professors would disagree, but I also make my students use ChatGPT to write their thesis. I say, if you don't use ChatGPT or some AI tool to write your thesis, I will not approve your thesis, because I think they need to be training for the future, not for the past.
I think that's yes. We sometimes we forget that we're preparing the student for a future market, for future time as well. So not for the past, a little bit for the current, but more importantly, to be effective in the future. I would like to thank you all for this very impressive discussion, and I'll hold thank you all, for everybody, and it was a pleasure moderating this session. Thank you.
We're done. You can close the meeting. Unless there's other things people want to discuss, I think we can officially close the meeting.
Anybody has anything to say before we close? If you don't, I would like to, on behalf of the organizing committee, I would like to thank you all for your time and for traveling, those of you who travel distances, and for your contribution. And your presence is very, very important for the success of this meeting. Thank you, and I'll let Seth say the last. Well, so then thank you very much. Have a great rest of the day. Safe travel for those of you who are traveling, and please fill up the survey. We need your opinion. We need your input, and get active on this meeting for the next meeting. And yes, thank you very much. Have a great rest of the day.